লগ আউট করতে হবে ইনস্টেড। এখানে আমাকে ভালো স্ক্রিনটা শেয়ার করতে দিচ্ছেন ইনস্টেড ডেস্কটপ থেকে।
Okay. We still have 5 minutes.
ওকে
সায়ন
হ্যাঁ বলো।
একটা জাস্ট কোশ্চেন যে এখানে যে প্রোগ্রাম টাইটেল অ্যাবস্ট্রাক্ট ডিটেইলসটা আছে না,
হ্যাঁ
তো সেখানে আমি সবার নাম অ্যাকচুয়ালি পাচ্ছি না।
কোন ওই
সরি ওকে
পেয়েছো?
হ্যাঁ
ওকে
ঠিক আছে।
ওকে, তোমরা কি দেখতে পাচ্ছ স্ক্রিনটা আমার? দাও একটু দাও।
হ্যাঁ পারফেক্ট।
Full screen করো, full screen করো।
হ্যাঁ দেখাচ্ছিল?
হ্যাঁ
ওকে অলরাইট। একটু দাঁড়া, আমি এটাকে কয়েকটা এক্সট্রা জিনিস খুলেছি, সেগুলো ক্লোজ করে দিই।
Yeah, we are streaming live, huh? YouTube.
Okay, we are streaming live. Okay, yeah.
Okay.
Shananda, please check if it's working, the YouTube.
Yeah. So, good morning, everybody. We are in the 5th day of the Virtual Math Fest 2020.
Wait. Arey, 10টা বাজেনি ভাই।
Okay.
Right.
Okay. I have to wait. Okay.
লোকজন আসুক একটু।
Streaming is working fine. Yeah, I just checked. Yeah, it's working fine. Perfect. Yeah, let's wait. Let's wait for 2 minutes.
I think
By the way, what
now
is
I
the-
can start, right?
Okay.
Yeah, we can start.
Yeah.
Just I have a quick question before I start. Okay.
Yeah, please.
What is the actual time? 45 minutes or 1 hour?
No, 45 minutes for your lecture, for delivering lecture, and 15 minutes, last 15 minutes for question and answer.
Okay, good.
So, welcome everybody. Welcome to the 5th day of the Virtual Math Fest 2020. So, the chair for today's session is Professor Jyoti Prakash Saha from either Bhopal. So, over to you. Yeah, thank you.
So pleasure to welcome all of you to the very first talk of the session. It's a pleasure to have Professor Om Prakash Das, who will speak about minimal model program or Mori program for birational classification of algebraic varieties.
Okay. Thank you very much for the invitation. It's always a pleasure to talk in front of young people. Okay, I mean, I'm also young. At least that's what I would like to call myself. Okay. So let's get on with this thing. I'll start. Okay, let's see what is going on. Okay, so I'll start very simply. So everything that we'll talk about here will work over arbitrary algebraically closed field. Okay, so I wrote here, for example, take a complex number, but you can take the algebraic closure of the finite field. Okay, so it will work over positive characteristic as well, almost all of the result. Okay, I'll be more specific where I need to be specific, where some result work only in characteristics zero. Okay, so let's just start very simply, okay, with the definition of algebraic varieties. We all know, so just repeat it anyway one more time, that algebraic variety is nothing but a common solution in Kn if K is the field in terms of vector space Kn of multivariable polynomial equations with coefficients in the field K. We'll call a variety projective if it is a common solution of a homogeneous set of homogeneous polynomial equations in some projective space Pn. Okay. Now see, in any geometry, be it algebraic geometry, differential geometry, or any other related remaining geometry, there is always one common goal in geometry, that is to classify all classify all geometric objects. Okay, in differential geometry, you try to classify them different up to diffeomorphism. In topology, perhaps up to homeomorphism. So everywhere you want to classify all geometric objects, okay, but almost always that is not completely possible. Okay, you will never achieve that goal, that you completely classify them. So what you do is that you weaken your classifying condition. For example, in topology, instead of trying to classify them homeomorphically, you try to classify them homotopically. Okay. Similarly here, in algebraic geometry, we would like to classify, of course, we would like to classify them in the best possible way up to isomorphism. But of course, that is not possible. So you weaken the condition. There are several ways to do this weakening. Okay. So one of the weakening that works remarkably is called birational classification. Okay. So let's define what is called, when do we call two varieties are birational? Okay. So let's say x and y are two varieties. We call that x is birational to y if they have like one open set u in x, one open set v in y. They are both Zariski open sets, so that u is isomorphic to v as quasi-projective or quasi-projective varieties. Then this kind of then we call those two varieties are birational. So basically, I don't expect the varieties x and y to be isomorphic, but they're open. Each of them have open sets which are isomorphic, one open set from each. Of course, non-empty open set. Equivalently, birationality can be expressed in terms of algebra. Okay, so if you take x, y are two varieties, take their function field k, ky. So function fields are, so kx is basically, if you think of x as a affine variety, then go to its coordinate ring A of x, and that's cosine field of that one is the function field. In general, function field variety is basically a set of all rational functions on x, that's called function field. Okay, so for n, the function field is a quotient of all polynomials of an n variable x1, x2, xn. Okay. Okay, so these are two equivalent conditions. Two varieties have isomorphic Zariski open set if and only their function fields are isomorphic as K algebras. Okay. So let's see some examples of birationality. If it is the affine space AN, so AN has the coordinate, the points looks like A1, A2, AN, right? So I can give an isomorphism from AN to an open subset of PN. That open set is, let's say, U0, where U0 is represented that the first component is 1 is to A1 is to A2 up to AN. Now see, since first component is 1 in this coordinate system, I can allow A1, A2, AN, all of them to be 0 at the same time. That's not a problem. Okay. So therefore, I have in this U0 is literally like very easily isomorphic to AN. Okay. So AN is always isomorphic to an open subset of PN, and PN is open subset of itself. Or sorry, yeah. So or AN is open subset of itself, and it is isomorphic to an open subset of PN. Therefore, AN is birational to PN. Next is, in general, if I take any variety, okay, and just take an non-empty open subset, it is always birational to its non-empty open subset. Obviously, from the definition. None of these things are actually important. First important and interesting result that comes is this. Let's take a variety X, and this is a subvariety of X. Okay, you take the blow up of X along the subvariety Z. So if you do not know what a blow up is, don't bother at the moment. Okay, it's not going to be particularly important, okay, for the rest of the discussion at all. Okay, but I'm just saying here because that is an interesting example. So if you already know what a blow up is, it will be interesting to see this is that this is actually a birational relation. Otherwise, it's not important really for the rest of the talk. Okay, so if Z is a subvariety, you take a blow up of X along Z. Then let's call it X tilde. then blob always gives you a birational variety, okay, birational to the original variety X. Okay, okay, so that's like it's like a natural surgery process which creates birational variety. Another like a pictographical example would be this. You take let's say we are in A2, the affine plane, okay, and you take the line y equal to x, the node y square equal to x square into x plus 1, or the cusp y square equal to x cube. Okay. All three of these curves, they're birational to each other. Okay, so seeing them through open sets, like that they should have Zariski open set, would be a bit difficult here. Okay, so what you do it instead, you go use the algebraic the condition. Okay, that their function field must be isomorphic as K algebras. Okay, and that is not so hard to actually see. Okay, so for the first, and this is as I said, their function fields are isomorphic to kt. So t is being the variable here. Okay, and k is the field, the base field. So you might be thinking why this is isomorphic to kt. See, for the first one, y equal to x, it's very easy to see that it's kt. Okay, you take basically what k of xy quotient by y minus x. So replace y equal to x, so then you have the polynomial ring kx as the coordinate ring of the affine variety, and then this quotient field is the k of round bracket x, which is same as k of t. For the node and the cusp, you need to go to their parametric equation. Okay, so the parametric equation of node is what? It's x equal to t square minus 1 and y equal to t times t square minus 1. And for the cusp, it is x equal to t square, y equal to t cube. So use that parametric equation, you can see that their function fields are exactly kt, isomorphic to kt. Okay, so they're all birational to each other. Okay, so you see that birational varieties could be very different from each other in terms of singularity, right? That the first one line is a smooth, second one is a singular, third one is singular. Okay, so it does sort of like give you kind of counterintuitive that why birationality is a good thing, but we will see later. Okay, soon actually. Okay, see, an easy corollary of the definition of birationality is that if two varieties are birational, the dimension must be equal. Why? Well, dimension can be achieved algebraically as well, right? Remember, two varieties are birational if and only if their function fields are isomorphic as K algebras. Now, if you recall something from Hartstone or any other book, wherever you learned your basic algebra geometry, the dimension of a variety is also same as the transcendental degree of the function field over the base field K. Okay, so well, if they have same function field, therefore the transcendental degree are equal over the base field K. Therefore, the dimensions are same. Okay. So since we know that birational varieties has to be of same dimension, so let's fix a positive integer n and consider a collection of all varieties of dimension n. Because if you consider birational varieties, I know that their dimension has to be fixed. Okay, dimension will be same. So let's fix the dimension first. Okay. Now within this collection C, we're going to define a relation tilde. Okay, we say two variety x and y within C are related by tilde if and only if they're birational to each other. By the way, let me just clarify one thing. I'm sure it is obvious, but just to be sure, okay, just to be clear, okay, the two varieties of equal dimension are not necessarily birational, of course, right? Think of it as the elliptic curve and the P1. Okay, both of them are curved. Both of them are dimension 1. Of course, they are not isomorphic. P1 has genus 0 and the elliptic curve has genus 1. Okay, so sure. One direction is only birationality implies equal dimension, but equal dimension does not imply birationality. Okay, so that's why you're collecting all varieties of same dimension in the collection C, and then within that collection define a birational relation x to y. Okay, so yeah, so we say two varieties are related by tilde if and only if they're birational to each other. Okay. Oops. Okay. Now you can actually show that this is an equivalence relation. It's not really hard to see. Okay, x is of course birational itself, and then it is symmetric and it is transitive. Okay, so it's equivalence relation. So of course, when you have equivalence relation on a set, then you can you can have a induced partition. Okay, partition by the equivalence classes. So let's pick a variety x from this collection and look at the corresponding equivalence class, the square bracket x. What minimal order program or minimal Mori program, like at a very basic sense, wants to do is this thing, that it aims to find a minimal representative within the equivalence class with good singularities. Okay, see, when you take equivalence class, it has infinitely many elements in the equivalence class, right? So all of them are representative for the class. So I want to choose from each equivalence class a representative that is minimal in an appropriate sense and has good singularities. It may not be smooth, it could be singular, but then has to have a reasonable singularity, not too wild singularity. Okay, so that's what the aim of the minimal order program. Okay. But how to do it? That's a very different question. So now let's start this thing. Let's start with the very simple. Okay, we'll start with dimension n equal to 1. Okay, and see how does this classification work. What is the minimal representative? What does it mean to have a good singularity? Okay, so that's what we will do next. Okay, classification in dimension 1. Okay. So let's see the projective curve. Then of course you can have singularity like the nodal curve or the cuspidal curve. Okay. Okay. So let's do the normalization C tilde of C. Okay. Then we know immediately that the C tilde is a smooth curve, and normalization is always a birational process. Okay. This normalization morphism is always birational. Okay? So that means if I look at the equivalence class of C square bracket, within that class, I already have a smooth curve C tilde. Okay. Not only that, it is a very specific thing about dimension 1 curve that for any two projective curves, the smooth projective curves, if they're birational, they're isomorphic, which means that the C tilde is the unique, the only smooth projective curve within that equivalence class. Okay. For example, that the previous example that I gave you, y equal to x, cusp and node, within those three curves, if you so they belong to all same equivalence class. Okay, and the y equal to x, that line is the unique member that is actually the smooth. If I projectivize it, of course I have to projectivize it. That's all I find. So it will be projective. Okay. So this is it. The C tilde has a smooth, unique smooth curve, projective curve in the class of C. So we just simply call it, this is the minimal model in this case. Minimal model in the equivalence class of C. Of course, this is a temporary definition. We're going to have a very specific definition of minimal model later. Okay, this is just a temporary definition. Okay? So this is it. For a curve, we are done in dimension 1 in this sense that we want to find a minimal model. Okay, and in this case, this is actually smooth, the C tilde. Okay. So what do we do once we do find a minimal model? Okay. So next job is, once we find a minimal model of something, for example, the C tilde here, we want to know the structure of this C tilde as explicitly as possible. Okay, so just saying the C tilde is a minimal model doesn't give us much, right? So we want to know what are the possibilities for this minimal model. Okay, like really classify this minimal model now. Now see, if you go to the complex number field C, then you know that every smooth projective curves are correspond to compact Riemann. So they're nothing but compact Riemann surfaces. Okay, so consequently, as you know, the compact Riemann surfaces are completely classified by their genus. Okay, the number of holes within them. Okay. So the smooth projective curve C tilde that we found in the previous slide, if that one has genus 0, then I know that it's going to be P1 by classification of compact Riemann surfaces. I mean, over complex number. If it is of genus 1, that is elliptic curve. If it is of genus greater than or equal to 2, then for each of these genus 2, genus 3, genus 4, there is a curve called curves of general type. Okay. So this is it. For curve, we know exactly what the minimal models could look like. Okay. Of course, there could be more than two elliptic curves, of course there are, which are non-birational to each other, non-isomorphic to each other. So they belong to different equivalence classes. Okay. So what I mean is that, let's say that we are in the second case, the genus of C tilde equal to 1. That does not mean all elliptic curves live in one single equivalence class. That is not. What I mean here is that if say the genus of C tilde equal to 1, and then you look at all these kind of equivalence classes, each of the equivalence classes, the minimal model is an elliptic curve. Okay? But they could be non-isomorphic, non-birational elliptic curve. Keep in mind that for smooth projective curves, they are birational if and only if they're isomorphic. Okay, so birationality is same as isomorphic in case of curves. Okay, but the point here is that we know explicitly how they look like, the minimal models. Okay, so these are the two objectives of minimal model program. First, find a suitable minimal model, and then try to classify it as explicitly as possible. Okay, that you want to know exactly what they are. Okay, and moreover, apart from this just genus classification, you also know the modular space of each of these curves due to Delling and Mumford, that MGN and those spaces. So this is it. So basically, for curves, we know everything that there is to know in terms of minimal model program. The next thing is surface, dimension 2. Now let's go to dimension 2, n equal to 2. Okay. Let's start with the projective surface. Okay. Now, unlike this curved case, if you normalize S, that is not a smooth surface. Okay. Normalization does not give you a smooth surface in case of dimension 2. Okay. So what we do is take a resolution of singularity. Okay, so the resolution of singularity is there's a process of taking it by blow up and stuff. I'm not going to that detail, but the point is that it exists. Okay, resolution singularity of surface exists. In fact, resolution singularity of any varieties in characteristic 0 of any dimension exists due to Hironaka. And originally for surface it is Zariski, Abhyankar, or Hironaka combined. Okay. So now S tilde, this resolution singularity is by definition is birational to S, original S. Okay. But here's the very bad thing about the resolution of singularity. Okay. See, resolution of singularity is not unique. Okay. This S tilde is a very non-unique. It's a smooth surface, but it's not a unique class in the equivalence class of S. Okay. In fact, if I take any point in S tilde and blow it up further at that point, this again you get a smooth surface, S double tilde. Okay, that is birational to the original surface S. Okay, so that means, in other words, within the equivalence class of S, there are infinitely many smooth surface in that equivalence class. Okay, so in this case, like in this sense, like we have like a good singularity, like in smooth, no singularity at all for representative, but there is no unique choice of the representative. Okay, there is no minimal choice of the representative. That is part of the problem. So remember, we want the minimum model to be minimal in some sense and also good singularity. So good singularity part is actually we have it here. We have a smooth, okay, but we do not have the minimality part here. There are infinitely many of. There is no way to choose minimal. Okay, for curves, the minimality part we said okay, it's the unique curve. Therefore, that is the minimal. Okay, there is nothing else to compare it. Okay, so what do you do next? Okay, so let me just go. Yeah, so we know that there's an infinitely many choice for this resolution. Okay. So we have a good representative in terms of singularity, but not minimality. So in the late 1920s, the Italian school of algebraic geometers, they tried to classify surfaces. Okay, so what they realized at that time was that a smooth projective surface contains lots of redundant informations. Okay, and we need to remove these redundancies before we can start classifying them. Around the same time, 1920s and 30s probably, Castelnuovo proved this following very important and useful theorem. Okay, he said that he showed that if you take a smooth projective surface S that contains a -1 curve, okay, a curve is called -1 if it is isomorphic to P1 has self intersection -1. Okay, so I'm not going to the any detail of what does that mean. Okay, but anyway, if it contains a -1 curve, then that curve will be contracted by morphism f from S to S prime to another projective surface, smooth projective surface S prime. Okay, so that f of C becomes a point in S prime. Okay. This is possible. Okay, that you contract the -1 curve, still you get a smooth projective surface. Okay. So you can see that you can repeat this process, right? If there is a -1 curve, contract them. Okay, then repeating this process finally many times, you will eventually you will arrive to a surface. Let's call it S min. Okay, such that this S min does not contain any -1 curve. Okay, this is what we would like to call a minimal surface. It's actually called a minimal surface, not that I would like to call it. It is called a minimal surface. Okay, it does not contain any -1 curve. Okay, and temporarily again we call this is our minimal model. Okay, although it is not minimal model in a precise sense that we'll see later. Okay? So minimal surface. Okay, okay. So now again, once we have the minimal like candidate for the minimal model, we have good single. S min is a smooth surface, and it does not contain any -1 curve. So this is our choice for each equivalence class. So this is what I'm going to do. Take a starting surface S projective. It could possibly be singular. Go to a resolution singularity S tilde, and from there start doing the Castelnuovo's theorem. Okay, that if S tilde contains a -1 curve, contract it. Okay, so eventually go to a curve that is S min that does not have any -1 curve. That is our candidate now for the good representative. Okay. It's a minimal surface, and it does not, it's smooth. Okay. The minimal surface can, just like the curves, minimal surface is also classified. It can be classified. Okay, it is already done. There are 8 different classes. It's P2 minimal rule surfaces, elliptic surfaces, abelian surfaces, K3 surfaces, Enrico surfaces, Boyle surfaces, and surfaces of general type. And the modular space are known for each of these classes. Okay, at least over complex numbers. In positive characteristic, at least the subset of general type is still not known. Okay, the modular space of that. So, yeah, otherwise we would have very good control about this thing. Okay, in dimension 2. So what about the higher dimensions? Okay, in the higher dimension, we would like to dimension 3 and higher, we would like to do the exactly same thing. Contract the bad curves. By bad curves, I mean something that resembles -1 curve. You see, in dimension starting 3 and higher, the -1 curve does not make much more sense. Okay, so but we'll call those are like those type of curves are bad curves. The curve that needs to be contracted to go to some minimal variety sort of things. So we'd like to do exactly similar things in dimension higher dimensions as well. Okay, contract bad curves and go to a minimal variety. Which we will call a minimal model, and then classify the minimal model as explicitly as possible. Okay. So before I can go say anything about higher dimension, which is the main part of the heart of this talk, I have to actually we have to go through some definitions first. Okay. So let me go quickly over this definition. A non-value set X is a normal algebraic variety. A Cartesian divisor is called NF if the divisor D intersects every curve non-negatively. An example is that if you take P2, it's a curve of degree D is an F divisor, because it by Bayes' theorem it will intersect every other curve of degree D prime, okay? Because all the number of intersection point is D times D prime. Okay? So that's an F curve. It is in fact ample more specifically. In general, any ample divisor is NF. Okay? And finally, if you want something that is an ample but that is NF but not ample, just take a proper morphism and take a pullback of an ample divisor from the base Y. Okay? So H is ample divisor, if upper star of Y is a NF divisor, which is not ample. Okay? So it's explicitly NF but not ample divisor, and all NF divisors are ample edge. Okay. Next, let's go to something called canonical sieve. Okay. So you have a variety projective variety X. Look at the omega 1X, that is the differential 1 form of this thing. Go to its top exterior power. That is a sieve of rank 1. Okay. Actually, here you may need to take a double dual. Okay. I forgot to write that down here. Sorry, there's a typo. Okay. Okay. So anyway, this is called a canonical sieve. Okay. And this corresponds to canonical sieve of rank 1 actually. So it corresponds to a divisor, non-canonical divisor, although non-unit divisor called a canonical divisor. We are going to denote it by Kx. Okay. Now here's the first definition. This is the actual definition of minimal model. Okay. So variety with mild singularities. So I have quote unquote mild singularities. I'm not going to specify what mild singularity means. So it's totally not possible. Okay. But just assume that singularities are good. We have a good control over the singularity. So for now we simply assume there is no singularity, it's just smooth. Okay, no problem. Okay. So variety with mild singularity is called a minimal model if the canonical divisor is NF, i.e. the Kx dot C is greater than or equal to 0 for all curves C. Okay. Okay. Now, if X is a curve, then what does NF being means? Okay, if X is a curve, then Kx being NF is same as what? So if X itself is a curve, then intersecting Kx with the X itself simply means take the degree of the canonical divisor, Kx. Okay, so Kx being NF translates to degree of Kx being non-negative. Okay, so that means in this definition of minimal model, only the elliptic curves and curves of genus greater than or equal to 2 are minimal models, because they have degree elliptic curve has degree 0. The curves of genus greater than or equal to 2 has degree 2g minus t. So g greater than or equal to 2 means it's greater than or equal to 2g minus 2 is also greater than or equal to 2. Positive. Okay, and P1 is not a minimal model in this definition. Okay. Okay. For surfaces, if you take either abelian surface or K3 surface, then Kx is linearly equivalent to 0. Okay, therefore it's of course a minimal model. In general, if you take a hypersurface of degree d in Pn, so that the d is strictly bigger than bigger than or equal to n plus 1, then that is actually that HD is actually minimal variety. It's a minimal model, okay, of its own. Okay, because K of HD canonical is actually an F. You can see by this adjunction formula. Next is okay, few more definitions, then we'll go to the main part of the minimal model program. Okay. So now the next definition is called something called a Fano variety. Okay. Yes. So if variety X with mild singularities, again you may assume it is smooth. Okay. It's called a Fano variety if minus of the Kx is ample divisor. Okay. So the anti-canonical divisor is the ample divisor. A simple example is Pn. Okay. If you take the Pn, you know that the canonical sieve or the canonical divisor for Pn is given by the structure sieve O of minus n minus 1. Okay, so that if you take the negative of that, so O n plus 1, that is ample, right? So Pn is a Fano variety. Okay, in general, if you take any generic hypersurface HD, so that D is now strictly smaller than n plus 1, then that is a Fano variety. Okay, because of this adjunction theorem again. Next, the last definition, hopefully, no, actually, okay. So yeah, a Mori fiber space. Okay? A Mori fiber space. What is a Mori fiber space? Again, it's a variety X is called a Mori fiber space if there exists a fibration, that means a morphism, a surjective morphism with connected fibers from X to Y, so that the dimension of the base is strictly smaller than the domain, and the fibers now are Fano variety. The variety X itself may not be a Fano variety, but the fibers are Fano varieties, okay? At least general fibers. And see, of course, a Fano variety is of course a Mori fiber space because the Y is a point in case of Fano variety. Okay, so Fano variety can be thought of as a Mori fiber space, no problem. So one example of Mori fiber space is that take any smooth projective variety and take a EB and vector bundle and take the projective bundle. You know, the projective bundle, the fibers are all Pn, right? Okay, or of n is appropriate of n is going to the rank of E minus 1. Okay, so that's a Mori fiber space. Okay. Okay, so here's the thing. Okay, yes. So in terms of, so you're almost there. Okay. Okay. So in higher dimension, in dimension greater than or equal to 3, one of the main difficulties of finding a minimal model, a minimal representative in each equivalence class, is the lack of a good contraction theorem analogous to Castellano's theorem of surfaces. Okay? See, I can do exactly the same thing. Start with a variety X and take resolution singularity. It exists at least over complex over characteristic 0 by Hironaka. It's a very famous theorem of Hironaka. So it exists, and then if I had a Castellano type of theorem, then start contracting, remove all the bad curves, and you would have a minimal thing. But that contraction theorem does not exist in higher dimension. That is the problem, okay? Starting dimension 3. But see, if you look at the Castellano's theorem, so this obstacle, that not having a analog of contraction, Castellano's theorem in higher dimension, it was a huge problem. Okay? So there was absolutely no progress in the minimal order program or this kind of contraction theorem for 60 years after 1920. Okay. Then in 1980s, Mori made the following simple yet very remarkable observation in Castellano's theorem. Okay, that he observed that what Castellano is saying, that you can contract -1 curve. Okay, but a curve C on a smooth projective surface is -1 curve if and only if when I intersect the curve C with the canonical divisor of S, that one is -1. At least in particular, it's a negative number. Okay. So -1, that number was not important for him. The fact was important for him is that it's a negative, that intersection is a negative thing. Okay. So Mori's idea was simply replace the question that is there a -1 curve on S by the question, is the canonical divisor Kx nef or not? Okay. See, when there is a -1 curve, because then Ks dot C is -1 in particular is a negative number, so this is definitely not nef. Okay. So ask this question now instead. Is the canonical divisor nef? Okay, sorry, it should have been Ks. Okay, I have it Kx. Okay, so yeah, so that's the next question. Is the canonical divisor nef? So now when you see the first time this question, it is a, well, yeah, it's a good question, but what if the answer to this question is no, it's not a nef? What do you do next? If it is a nef, then yes, you will call it a minimal model. That's our definition. But if it is not nef, what do you do? It seems like there is absolutely nothing we can do about it. Okay, but that is what is what Mori did, like his main work. Okay, or that he gives a very decisive information in this case. Okay, that what happens if this is actually not nef. Okay, he shows that this is all done in 1980s, 85, 88, around that time. Okay, I think starting from 82, 83. Okay, that if Kx is not nef, then there exists a contraction of Kx negative curves. What do you mean by Kx negative curves? I mean that the curve that has intersection with Kx negative number, not necessarily -1, absolutely not. You cannot say that in higher dimension, okay? But a negative number at least, okay? If you have a curve intersecting negative numbers, you should be able to contract it. And yeah, he shows that there exists a contraction like this, okay? This is the very big moment of the conception of the higher dimensional minimal order program. Okay? But there are some problems, okay? This theorem is not enough, as you'll see. See, let's go back to the surface case again for comparison, okay? In case of surface, we're contracting curves, right? Because for surface, the only thing is surface, then curve, then point. There is nothing in between, okay? There is like a point and surface, and in between there is a sub-varieties are curves. So whenever you contract from a surface, you're contracting curves. And curves are codimension 1 sub-varieties on S, okay? So the natural generalization of curves in higher dimension would be divisors for higher dimensional varieties. Okay, when you're contracting curves in surface, we would contract divisors in higher dimensional varieties. Okay, because divisors are codimensional exactly 1, okay, in higher dimensional varieties. But unfortunately, just contracting divisors in higher dimensional varieties is not enough to get a minimal model. Okay? So more specifically, there are 2 types of contraction in higher dimensions. Okay? One is exactly, you, as I said, contract divisors. Okay, so contract, it is called divisorial contraction. You take a variety x and you take a you contract a divisor by morphism f from x to y. This is called a divisorial contraction. So this type of contractions are good. It means that if what do I mean by good? It means that if x has a good singularity, mild singularity, the y will also have mild singularity. Okay. And there is another type of contraction called small contraction or clipping contraction. Okay, that instead of contracting divisor, you contract divisor codimension 1. So you contract something of higher codimension, codimension greater than or equal to 2, or dimension less than or equal to n minus 2 from x. Okay. So for example, if you take a 3-fold, you will contract, instead of contracting a surface, let's say you're contracting some curves, finite element curves from x. This would be an example of a small contraction or clipping contraction sort of things. Okay. So you're contracting a subvariate z, which has codimension at least 2. See, this type of contraction is actually bad, very, very bad. Okay, it's extremely severe contraction. I mean, y is always singular when you do this kind of contraction, even when x is smooth. Y is like necessarily a singular variety even when x is smooth. Okay, in this contraction. But unfortunately, this type of contraction is unavoidable in the minimal model program. Okay, so we have to deal with it. So I have given lots of definitions. Okay, so now we are ready to actually describe what a minimal model program is. See, when you define something in terms, when you say something that's some program like minimal model program or Langland program, when you say the word program, it automatically means that there is an algorithm for it, for the process. Okay, so that's what next is the minimal algorithm of the minimal model program. Okay, so this is of the chart is basically the heart of the minimal model program. That is what we intend to do here. Okay, so start with a variety x with mild singularity. Again, for our purpose, let's assume that x is smooth. In fact, okay. Remember what we want to do. Our objective is that look at the equivalence class of x and find a minimal model in the equivalence class that is minimal in some sense and also have good singularity. Okay, possibly not smooth, but at least mild singularities. Okay, so that's what we are doing. Starting with the variety x, and whatever we do in this diagram, every step will be living. Every step, the output will live within the equivalence class. Okay, you will not go down to the equivalence class of x. Actually, the originally that we define the equivalence class using the birationality relation. Okay, so start with the x with the mild singularity. Let's expect it is smooth. Then you ask this question: is kx naive? If the answer to your question is yes, then that's it. That's the minimal model. It is smooth. Then we are done. You end the program right there. Okay, it's a minimal model. You go to the right hand side. Okay. If the answer to this question is no, okay, then by Mori's theorem there exists a contraction. Okay. But as I said, there could be two types of contraction. Okay, actually, there's a third type of contraction that I said it before, saying the divisorial and flipping contraction. Okay, let's just, since I did that, I have to say it differently. Okay, so there is a contraction. Okay, so after the contraction, you actually judge this. Okay, look at this thing. Whether the base of this contraction y has a dimension equal to x or strictly smaller than x. See, when you contract things, if it is a birational contraction, then the base will have, the y will have exactly same dimension as x because it's birational. If it is not a birational contraction, then dimension of y will be strictly smaller than x. Of course, it cannot be bigger. It can never be bigger than x because you're contracting things. Okay. So if the dimension is strictly smaller than x, then automatically this one becomes a Mori fiber space. Okay. Remember, we defined Mori fiber space before. Mori fiber space means that the fibers of these morphisms are all Fano varieties. That means the anti-canonical divisor of the fibers are ample divisor. Example is you take a projective bundle over a vector bundle over any variety. Okay, take a vector bundle E over a variety X and take a projective bundle. That's an example of Mori fiber space. Okay, so if the dimension and then so if the dimension of the base contraction Y is smaller than X, then it immediately becomes a Mori fiber space. And this is Mori fiber space is not a minimal model. Okay, but it is in this case it's simply the fact that the equivalence class of X does not have a minimal model. Instead, it has a Mori fiber space, but that is still a positive outcome because Mori fiber space can be classified. Okay, so it's not a bad thing. Okay, so and the other thing is that if there is a Mori fiber space, then there will be Mori fiber space and minimal model. They are like two exclusive cases. If there's a Mori fiber space, then there is no minimal model. Okay, but still, like it's having Mori fiber space is not a bad thing. Okay, so let's say we are in the situation no, the dimension of y is in fact equal to x. So the no. So then means it is a birational contraction. The base has same dimension as the domain. Now we ask, is it a divisible contraction? It means, are we contracting a divisor from X to get a Y? Okay. If it is a divisible contraction, then it's very nice. Okay, then it is yes, then you simply replace your X by Y and continue this program. Okay, go run through it again. But if it is not a divisible contraction, then it's a contraction that you're contracting something of codimension greater than equal to 2. Okay, it means that you're contracting curve from 3-fold or surface from a 4-fold, dimension less than equal to 2 subvarieties. Okay. Then there is a conjecture, this thing that, I mean, yeah, so then you have this f x to y, but this, as I said, that y will have a horrible singularity. Okay, it's a extremely bad singularity, so bad that you cannot replace x by y and run with this program. It will not make sense running with this program. It's not possible. Okay, so you need to replace this y by something x plus. Okay, and then you replace x by x plus. So this is conjectural whether this x plus, this morphism f plus to from x plus to y is exist or not. Okay, this is called flip conjecture. I'll come to that thing later. Okay, so if let's say I assume the conjecture, flip conjecture, it does exist. I can find a better variety x plus that is birational to both x and y and has good singularity. Then replace x by x plus and continue with this program. Okay, so that's it. So this is the minimal model program. You start with the variety, ask whether kx is NF. If it is NF, you have a minimal model. If it is not NF, then you have a contraction. If the base of the contraction is smaller dimension, that's the Mori basis. If it is same dimension of the domain, then it's either divisible contraction or flipping contraction. If it's a divisible contraction, you simply replace x by y and continue with the program. If it's a flipping contraction, you do not, then you are not sure if you can go to the next step. Conjecturally, you can, that you should be able to do it next step, replace y by some other variety, third variety, x plus, which is conjecturally exists and is which has good singularity, and then continue the program. Okay. So there are two obvious conjectures related to this minimal model program, this algorithm. Okay. First is the existence of flip. As I said, one of the steps in a minimal model program is conjectural. Okay, so like that's a problem. So the first conjecture is that the flip of a flipping contraction always exists. Means that if you have a flipping contraction x to y that contracts something codimension greater than equal to 2, then the singularity of y becomes very bad. That I want to replace y by something x plus. Okay, that x plus exists. That is the first conjecture. Next conjecture is termination of flips. Here's the thing. Anytime you define it using an algorithm, the natural question is, does this algorithm terminate after a finitely many steps? Okay, that's a natural question to ask. Okay, and the point is that we do not know for MAP. That is a big conjecture whether it terminates after finitely many steps. We know in many cases when it do terminate in finitely many steps, but a conjecture is that if the conjecture is called termination conjecture, it should terminate at finitely many steps. And see, here's the thing, that the only obstacle here is that the flipping part, when you're doing this the smaller flipping contraction. Okay. If you do divisible contraction, I know that we can say that very easily that you can only have finitely many divisible contractions. Why? Because each divisible contraction reduces the Picard number of a variety exactly by 1. And Picard number of a variety is always a positive integer. Picard number of a variety cannot be 0. It's not possible. Okay. Unless it's a point. Okay. So as you start with a variety, you start decreasing Picard number, it will has to stop at least when it arrives 1. It cannot go any below than lower than 1. Okay, and each contraction reduces Picard number by 1. Okay, exactly by 1. Okay, so that there's no like repetition that it does not change Picard number at all after a stage. It does not happen. Okay, with the divisible contraction. However, flipping contraction does not change Picard number. The flip does not change Picard number. Okay, that x plus that you're replacing. See, this x to y, it does change Picard number by 1, decrease the Picard number by y by 1 in y. But again, when you replace y by x plus, it puts it back again. Okay, so x plus and x has exactly same Picard number. Okay, so there is no natural invariant to control the number of flips that you can have. Okay, so this is why it's not known whether in general that the flips will terminate or not. And then there is the final called abundance conjecture. Okay. So see, once you do have a minimal model, that means you have kx equal to NF. This is a question that I got asked many times. I see I have only 5 minutes, so let me be quick. That whether the kx, so what does, if let's say I do have a minimal model kx equal to NF, why is that a good thing, having kx equal to NF? That's a very numerical property, right? So why is that a good thing? So the good thing is that this is the next conjecture, this abundance conjecture. Okay, that once you do have a minimal model, then kx is not that's not it. Okay? If kx is not, kx is actually semi-ample, means you will always have another sort of contraction from x to y, such that the kx is pullback of a divisor from the base. Okay? And each of the fibers of this morphism is a Calabi of varieties. Okay? So this is something very significant. Okay? So what is the current status of this program? Okay. So okay, yeah. So let me tell you. Okay, before I say anything about the conjecture, so this is the upside of the minimal program. What do you get from the minimal program? The prediction of the minimal program. So minimal program basically gives us this. Minimal program along with this conjecture that I told you, abundance conjecture, flip conjecture, dimension conjecture. If you believe all of this conjecture, then the minimal program says exactly the following thing: that every projective variety X with mild singularity is birational equivalent to one of the three classes of variety. Either it's birational to a Mori fiber space X, that means it's birational to X, either X has a fibration X to Y, where fibers are Fano varieties, or it's a birational to a variety X, which is a Calabi of fibration over some other variety Z, or it's birational to a variety of general type. So these are the three varieties. In particular, it basically says that if you want to classify all varieties, okay, in the modular sense or in birational sense, you have to only look at three classes of varieties. These are the fundamental classes of varieties: Fano varieties, Calabi varieties, and varieties of general types. This is it. This is the precise information that minimal program gives us, along with its conjecture, if you believe the conjectures, okay, to be true. Now, what about the conjecture? Are the conjectures true? The conjecture, the first one, the existence of flip, that one was proved in dimension 3 in 1988 by Mori, which led him to his field medal, okay, in the later year. And higher dimension, people tried to do this as very interesting actually history. People so in dimension in 1988 it was proved by Mori, and then people tried to do it for another 20 years, tried to prove it for dimension 4, okay, without much success. Then in 2006, Christopher Hagen and James McKernan, okay, this one here, they showed that there's a breakthrough result that year, okay. They proved that flip exists in every dimension, not just dimension 4, all dimensions, okay. They were able to do a induction on it. They said you do not need to focus on dimension 4. You can do induction on dimension and show that it exists in all dimensions. This is a huge result, okay. So they proved, so again, all of these things is in characteristic 0. So characteristic 0 flip exists, okay, in all dimensions. But dimension conjecture is still not proved, okay. There are special cases where we know, but not in general. These characteristics 0. So what about other characteristics? In positive characteristics, there was another breakthrough in 2013 again by Christopher Higgins and other authors, Qian Yang Su. They showed that minimal model program, they can prove existence of minimal model program flip and all these things, termination of flip in dimension 3 in characteristic p greater than 5 in positive characteristics. And this was done in a very interesting way using tight closure theory from the commutative algebra, okay, F singularities. This was something very remarkable, very new ideas. And then there are lots of progress. They did basically the fundamental cases in this positive characteristic, and there are lots of other other people contributed to complete the program in dimension 3. And then yeah, so the abundance conjecture in dimension 3 is also known in characteristic 0 and positive characteristic as well in many cases. People contributed. Birkar, Waldron, myself, Sue, and Zhang with Sek. So let's just 1 minute. I'll tell you this thing that so minimal program is there for characteristic 0, positive characteristic. Positive characteristic you only know up to dimension 3. In characteristic 0 we know a lot, okay, but still not the complete thing. And all of those things are projective varieties. But there is a new thing, minimal program for scalar manifolds which are not projective. Okay, so this thing was started in the late 90s by Kampana, Peter, Horing. They showed a lot of the cases in dimension 3, and this is the sort of the thing that I'm currently interested in. Okay, I will stop here. Thank you.
Thank you so much for your excellent talk. So I'd like to invite the questions from the participants.
Okay.
So are there questions for the speaker?
Yes, I have a question.
Sure.
How do we know that there are finitely many -1 curves on the, on the surface that you were talking about? I mean, you said after.
Yes, so there is not -1 finally many -1 curve in general. In fact, there could be infinitely many -1 curve. For example, if you take a P2 blown up at 8 points or more, okay. But the fact is that what is happening is that each time you contract a -1 curve, it reduces the Picard number by 1. And here is other thing, okay. When you contract something, you change the intersection property of the variety, okay. So for example, like I said, if you take a P2 blown up at 8 point, it has infinitely many -1 curve, right? But if you contract one of those -1 curve, you go to, then that becomes a blown up P2 at 7 point. That one has now finally many -1 curve. Why does that happen? Well, because when you contract things or blow up things, you change the intersection property of the variety, okay? So the number of -1 curves heavily depends on the contraction or extraction of curves, okay? So the reason I know that I can, so what I'm claiming there is that there are not finally many -1 curve. I'm claiming that I can contract finally many curves, and after a certain point there are going to be no -1 curve, because yes, this two are obviously related. Yes, this is the reason, okay, that contracting -1 curves actually changes the behavior of the intersection property of the variety. And so what I can tell you, that you might be wondering that at least how do I know that I will stop, right? Okay, you will stop for sure contracting -1 curve, because each contraction reduces the Picard number by 1, right? Okay, and a variety of positive dimension must be a positive Picard number, okay. So clearly, if you start contracting -1 curve, each time dropping the Picard number 1, 1, 1, 1, it has to stop at some number, right? You cannot continue, okay. So that one tells you that at some point there will be no -1 curve.
Okay. Yeah. So there's one more thing. So I think in slide 44 or something, I could see C and D being divisors, and their intersection number was greater than equal to 0. I think it's in.
Sorry. What is the question again? Say it again.
So there were two divisors, C and D, on a variety X of an arbitrary dimension. I mean, the dimension was not 2. So the C dot D was taken to be greater than equal to 0.
Yeah, so C is not a divisor. C is a curve and D is a divisor.
Oh, okay.
Yeah.
I see.
Okay. D dot C is a divisor, C is a curve.
Yeah, so there's one more thing. So at the end, so I have not really seen, well, the only thing, I mean, I've seen for a surfaces when we contract a -1 curve, there are no introduced singularities, right?
Correct.
But I could hear repeatedly that there are, I mean, when we do it in higher dimensions, it is not the case.
Correct.
So I was wondering if there are like
examples.
an example of
correct.
Yeah.
Yes. Of course, I couldn't give it here. Here's the example. Okay. Take a abelian threefold. Okay. And quotient it by Z2, the group. Okay. Group of order 2. Okay. Then you will have, let's say, 2 to the power. Let's say how many 6? 36. You will have 36 singular points. Okay. In that quotient of A3, the abelian threefold of dimension 3 over complex number, let's say. So there are 36. 36. Yes. 2. Okay. Just let me just check. Okay. 2 times. Okay. 2 to the power 6. No, not 36. 2 to the power 6 number of singular points. Okay. That one. If you blow up that thing. Okay. That one becomes smooth again. Okay. If you blow up this 2 to the power 6 number of singular points. Okay. And I'm not saying all this clearly. I said that there is a contraction, right? Those contractions are very specific type contraction called contraction of extremal ray of the Mori cone. Okay, you can see that if you once you blow up this 2 to the power 6 number of points of this quotient of abelian threefold by Z2 action. Okay, each of this blow up of this 2 to the power 6 point are extremal rays, and those are the only extremal rays. Okay, negative extremal rays of Kx. Now see. And those are all divisors, right? So if you contract any of those things, you are going to get a singular variety.
Okay.
Does it make sense?
Yeah, it was a little fast. So is there a reference?
Okay. Yeah, let me say it again. Sorry.
Okay.
First, I am aware of that. I've been told it many times. Okay. Let's take an abelian threefold, A3.
Okay.
Quotiented by the group Z2. Z mod 2Z. Okay.
Yeah, sure.
Then you can calculate that it has 2 to the power 6 number of singular points. This is a singular variety, right?
Okay. Yeah.
And then you blow up all those singular points. You can blow up them up simultaneously because they are disjoint point, okay? Disjoint close points. Okay. So then you get one single blow up will give you actually a smooth variety. No problem. Okay? And there in that smooth variety, let's call it x tilde. There, you look at the Mori cone. Okay? Mori cone will have exactly 2 to the power 6 number of extremal negative kx negative extremal rays. Okay. And what I did not say here in my discussion is that the Mori's theorem that tells you there is a contraction. You do not just contract arbitrary things. You contract the kx negative extremal rays of the Mori cone. That is the only type of contraction that you will do. That means you will contract one of these 2 to the power 6 number of extremal rays from x tilde, right?
Yeah.
See, let's say you contract one of them, okay? That means you get a new variety where you have 2 to the power 6 minus 1 number of singular points. So no matter which extremal ray you contract, you will always end up having a singular 3.
Okay.
Right? Because contraction in this case would be the reverse process of blowing up, blowing down this would be.
Yeah.
Right? Because you can think of this 2 to the power 6 number of point, this blow up process as just doing blow up one by one.
Yeah.
So yeah, so it's contracting one by one.
Yeah.
So that's the example.
Okay. Yeah, that's it.
Okay. Any other questions?
Are there further questions for the speaker?
I have a question.
Yes.
Sure.
So what happens if you have curves of, even in the case of a surface, if you have curves of higher intersection numbers, negative intersection. So for instance, a -2 curve or.
Correct. Yes. Okay. Yeah. Okay. So yeah, of course, I have to leave a lot of things here. Okay. So see, if you have, let's say kx dot c equal to -2, right? Okay. So you are saying that whether you can contract that curve or not. Is that the question?
Right. So I know that you can contract it, but you get a singular.
Correct. You get a single
singularity,
surface.
right?
You get a single surface. That is very true. Okay. Yes. That is exactly what happens. Okay. But for the contraction does not come from Custom-Lobos theorem. Okay. So you will get a canonical singularity in this case.
I see, but that's allowed in the minimal model program.
In the minimal model program after Mori, okay, that when you ask this question whether kx is nef or not, okay, in this new series of minimal model program, not the Custom-Lobos way of doing.
I see. So also in the Mori contraction, I mean, what kind of object do you contract? Do you contract a divisor or?
Mori, yeah. So you contract either a divisor or a codimension greater than or equal to 2 subvarieties, or there's a third contraction that I don't know how, when I organized, I wasn't being very careful. These are old slides which I edited. For example, you can have a contraction sort of like for example, this thing, like I said, take a projective bundle, right? Okay. Those contractions can appear, which will give you the modifier space. Okay. So you can have a contraction where you completely drop the dimension from x to y.
Right, but what kind of object are you contracting on X? So, for instance, I mean, for divisorial contraction, you are contracting an actual divisor, right?
Yes. So in a flipping contraction, you are contracting codimension greater than or equal to sub.
Right, but in the first step of contraction that you mentioned, what kind of?
So modifier space contraction is not like you are contracting a divisor. You're like contracting a family of, let's say, a family of curves which covers the open subset of X.
I see.
Or a family of subvarieties which covers open subset of that has to be.
Oh, that gives the fibration.
That gives the fibration, yes. Otherwise, you will not reduce the dimension.
I see. Okay. Yeah, thanks.
Okay. Are there further questions for the speaker? If not, let's thank the speaker once again. It's a pleasure to have you. Thank you so much.
Likewise. Okay. Oh, Krishna has a question, something?
No, that was just a mistake.
Okay.
Nice talk.
Thank you.
So, okay. I was wondering, what is the? I mean, all of this was in characteristic 0, right?
No, the algorithm and everything, all of it will work in every characteristic, at least conjecturally. But most talk is done in characteristic 0. Yeah, go ahead. Oh, sorry, I stopped you. What is your question?
No, I thought. Can you repeat what is possible in characteristic P? I mean,
okay, so more specifically in characteristic P, we do know the existence of flip in dimension 3. Okay. And we know that we do not know termination of flips exactly in characteristic P, but we also know lot of the part of the abundance condition in characteristic 3. But in characteristic 0, we do know the existence in dimension 3 particularly. We know existence of flip, termination flip, abundance condition, all of it. Dimension 3. In high dimension character 0, we only know existence of fleet, all dimension. We do not know termination of free. We do not know abundance conjecture. Abundance conjecture in character 0 is one of the most important outstanding conjecture there is, okay, in biaxial geometry. Okay. It has over literally hundreds of applications of that conjecture.
Okay. Okay.
Okay, so if you have any further question, let's thank the speaker. Thank you.
Thank you.
Thank you so much.
Yeah. Let me stop this screen sharing. Pause. When does the next talk start?
At 11. It's at 11, and
okay.
it will be given by Dr. Snehojit Mishra.
Okay.
Yes, Snehojit, you can share your screen.
Shayan, are you here by the way, or maybe sort of?
Yes, I'm here.
Yeah, okay. So just the next one will be kind of a contributory talk, right?
Right.
Yes,
right.
yes.
Okay. So we'll have kind of 3 speakers, one after another.
Right. 15 minutes for the talk and 5 minutes for the question answer session. And this is for each speaker.
And in the order it is mentioned, right?
Right.
Okay.
First Snehojit, then Bibhash Khan, and then Anup Singh.
Okay. Can I share now?
Yeah, please.
Yes.
Is this visible?
Yes.
Yes, I can see it.
Working, right?
Yes.
Can you see the slide?
Yes, we can. Yeah.
Snehojit, you can turn on your camera if you wish to.
Okay. Yeah, is this okay now?
Yes.
Move a bit.
Can start?
Yes, it's time.
Yes. Yeah.
Okay, let's welcome Snehajit Mishra from TR from Mumbai. He will speak on ampleness criterion for vector bundles. Please welcome.
So first of all, thank you very much to the organizers for letting me speak in this Math Fest. So today I will speak on ampleness criteria for vector bundles. So it's part of our joint work with Nobonita Ray. So let me start with the definitions. So throughout this talk, we'll consider projective varieties over complex numbers, although things can be said for any complete scheme, but that is not needed for this talk. So given line bundle on such projective variety, and if we fix a basis for the space of global sections, we can define a rational map, which is just evaluating those sections at a particular point. But the problem is that this map may not be well defined. In fact, it is not defined precisely on the base locus, which is nothing but the intersections of the zero sets of all the sections. So a line bundle will be called base point free or globally generated. If the base locus is empty, that means it keeps a full morphism from X to the projective space. And in addition, if the map defines a closed embedding, then it's called very ample. So in general, given a line bundle on X, it's very difficult to check whether that is globally generated or very ample or not. So one can check in the internet about a famous conjecture due to Fujita regarding global generations and very ampleness in this. So in this particular talk, we are interested in ample, and ample bundle is nothing but a bundle for which some positive integral multiple is very ample. But checking ampleness is, again, it's not that easy. So we'll see later why it's not. Before going to that, we'll like to see some examples. So for any positive integer, we have this Veronese embedding on the projective n space, and this map is given by this OPND. So in particular, the OPND is very ample, and it's ample for every positive integer. Another example I want to mention is a line bundle on smooth curves. So for a line bundle on a smooth curve, if it corresponds to the divisor of the form, the summation ni pi, then the degree of the line bundle is simply taking summation ni, where ni are integers and pi are some close points in the curve C. So checking ampleness of such line bundles is enough to check its degree. But in general, for a line bundle on any arbitrary smooth projective variety, checking ampleness is again very difficult, and there are some characterization of ampleness. There is homological characterization due to SED, and then there is Grothendieck's characterization of ampleness. But in this talk, we are interested mostly in numerical criteria for ampleness. So one such numerical criteria is due to Nakai, Mosian, and Kleiman. So it's basically saying that a line bundle on a projective variety is ample if and only if certain intersection product is ample, specifically L to the power dimension of V intersected with V is positive for every positive dimensional irreducible closed subvariety of X. So one particular thing to notice is that this criteria is saying that if X is ample, then its intersection with every integral curve is positive. And another criteria due to Seshadri, it's basically saying that a line bundle on a projective variety is ample if and only if you can find a positive epsilon, thus that at every point X and every irreducible curve passing through that point, this intersection product divided by the multiplicity of the curve, it should be bigger than equals to epsilon, and this should happen for every point. But most of the time, this finding epsilon is very difficult. And one unique part about this criterion due to Seshadri is that ampleness is a global property, but this criteria is somehow saying that you can actually check it locally by picking some positive number at every point of the base space. Okay. So we need a couple of definitions. Firstly, what is an F-line? It has already been defined in the previous lecture. So let me recall. So a line bundle is naive if its intersection with every curve is non-negative for every reducible curve. And so Harshan extended this definition of ampleness for higher rank vector bundles on projective variety. He considered the Grothendieck projectivization and call a vector bundle E is ample if the associated tautological line bundle is ample or a naive on P of E. So E will be called naive if this tautological line bundle is naive on P of E. So now the question is that given a vector bundle on a smooth projective variety, how one determine whether E is ample or not, or more generally E is naive or not. So I mean, there are some criteria due to Giesecke, also due to Harshon. I'll come to those things later, but first let me recall two different notions of stability that exist on smooth projective varieties. So one is slope stability, which is basically saying that torsion-free sheave is slope stable if the slope of its proper sharp sheaves are less than equal to the slope of the torsion-free sheave. And there is another due to Giesecke, which saying that a torsion-free sheaf on X is Giesecke semi-stable if for every proper sharp sheaf, if you consider the reduced Hilbert polynomial, that should be less than equal to the corresponding reduced Hilbert polynomial of the torsion-free sheaf. So in general, we have this relation that slope stability implies Giesecke stability, and then it implies Giesecke semi-stability, and then Giesecke semi-stability implies slope semi-stability. But in the case of curves, both the notions coincide. It just one can see it from Riemann-Roch theorem. And one more thing, for every vector bundle on X, there exists a unique filtration called the Harder-Narasimhan filtration, such that the successive quotients are semi-stable torsion-free sheaves, and the slopes are decreasing. So the minimal slope will have, I mean, this quotient, Ek quotiented by Ek minus 1, will have the minimal quotient. We'll call the mu min of E to be the slope of that quotient. So the Giesecke's ampleness criteria is basically saying that if I start with a semi-stable bundle on a smooth projective curve, then that is ample or naive, if and only if the corresponding determinant bundle is ample or naive. And Harshan also proved much earlier, because he is proving something for ampleness only, not for naive. A vector bundle E on a smooth projective curve is ample if and only if the mu min of the bundle is ample. So the ampleness can be read off just by looking at the Harder-Narasimhan filtration of the bundle E. So, this criteria, this ampleness criteria of Giesecke can be deduced from this Harshan's criteria. It's a special case, but there is something about naiveness also in Giesecke's ampleness criteria. So our first result in this direction is that if you start with a semi-stable bundle on a smooth complex projective variety with vanishing discriminant, that means the C2 of endomorphism of E is 0, then E is ample or naive if and only if the determinant bundle is ample or naive. Since on a smooth curve C2 vanishes, so this can be thought of as a generalization. I must mention that the condition that we put is only sufficient. It's not necessary. I mean, if you consider the tangent bundle of P2, that is stable with respect to every polarization, C2, I mean, the discriminant is not equals to 0, but still it's ample, because, and also the determinant bundle of the tangent bundle is also ample. So now the next question is how do you produce such kinds of semi-stable bundles on an arbitrary projective variety? Well, one way to pull back semi-stable bundle on a curve under a surjective map. So this will have semi-stable. This will be semi-stable bundle with this vanishing discriminant. And so as corollary to this result, we prove that on a projective bundle over a smooth curve, the pullback of the vector bundle it will be semi-stable. So note that if you pull back a vector bundle on P of W, that will not be ample. So you have to twist it by some other line bundles to make it ample. So I'm saying that a semi-stable bundle on PW is with vanishing discriminant is 0 if and only if this CO1 of B satisfies this property. So this property is saying basically the determinant bundle of B is ample. So I just want to mention one thing that we have, while proving this one, what we actually proved that the added symmetric power, the added symmetric power of E tensored by the dual of the determinant bundle is actually flat, and hence it's NF. And from there we conclude that E is ample on NF if and only if the corresponding determinant bundle is this. We basically use Nakama, there's Noburu Nakama's result, or there's similar kind of results due to Biswas and Buzo. Now we come to the second part of the talk, saying that a line bundle on a projective variety is called strictly NF if its intersection with every integral curve is positive. So by, again, Naka's criteria, every ample line bundle is strictly NF. And the converse is true for abelian varieties, toric varieties, flag manifolds. However, the converse is not true in general. There is an example due to Mumford. So using Narasimhan Sheshadi theorem for any smooth projective curve of genus bigger than equals to 2, Mumford produces examples of stable degree 0 bundle of rank 2 on such curve, which has this property. This H naught of M symmetric power of E twisted by the line bundle is 0 for non-positive degree L line bundle. And for such vector bundle E, if you consider the projective bundle, the tautological bundle, we have the property that its restriction to every curve is ample, but the line bundle, the tautological bundle, is not ample. So obviously the converse is not true in general. So a similar question has been asked in a preprint due to Biswas, Krishna Hanumanto, and Nagaraj, and first version of this came in 2019. After looking at that, we started doing something on rule surfaces. So basically the question asks that a vector bundle on a projective variety X such that its restriction to every curve is ample. So under what condition E is ample? So Mumford example is saying that you have to put condition on the vector bundle E. And they answered this question affirmatively for certain homogeneous variety. They have showed that every T equivariant vector bundle on certain homogeneous variety is ample if their restrictions to every T equivariant closed curve is also ample. And they also give some examples of semi-homogeneous vector bundles in the sense of Mukai on some abelian varieties, and so that such bundles are ample if and only if the determinant bundle is ample. And a similar kind of results are known on toric varieties also due to Herring, Mustata, and Pine. So they basically prove that a equivariant vector bundle on a toric variety is ample if and only if its restriction to every T rational curves is ample. So we look at this problem on rule surfaces. Before going into that, we need some definitions. So a vector bundle of rank 2 on a smooth curve will be said normalized in the sense of Harshon if it has non-zero sections and the sections vanish. I mean, there is no non-zero section if you twist it by some negative degree line bundle. So one observation is that the normalized bundle is semi-stable if and only if degree is non-negative. And for a rank 2 bundle, you can always twist it by some line bundle to make it normalized. So typically examples of normalized bundle will be OC direct sum of L, where degree of L is non-positive, and some non-split extension of W by OC for genus bigger than equals to 1 curve. And there's a one common factor for in these examples is that mu mean of W is equals to degree of W in both of the cases. So our result in the direction is that if I fix a rule surface which is defined by a normalized rank 2 bundle such that it satisfies these properties, mu mean of W equals to degree of W, then for any semi-stable vector bundle of rank R with discriminant 0, it's ample if and only if its restriction to a smooth section and just the fiber of the map row is ample. So in particular, we do produced strictly NF line bundles on rule surfaces, but you have to choose your rule surface very carefully. And then similar things one can do, that pullback of semi-stable bundle on the curve on X is semi-stable with discriminant 0. You have to twist it by some positive power of the tautological bundle to make it ample. Okay, so all these results are on semi-stable bundles. We try to find if we can find any non-semi-stable bundle on certain rule surfaces which has the same property. So we look at Hirsebus surfaces, which are defined by this rank 2 bundles on P1, projectivization of rank 2 bundles on P1 for E bigger than equals to 0. And for any rank 2 bundle on such Hirsebus surfaces, we can associate two invariants. The first invariant is coming from the general splitting type of the bundle restricted to a generic fiber. And the other one is basically R of E. So this is degree of rho star of E twisted by minus D of C naught, or C naught is the section corresponding to the tautological line bundle on F of E. So note that by semi-continuity theorem, its push forward will be a torsion free sheaf, and it's locally free on P1, so degree completely makes sense. So our result in this direction is that if I start with a globally generated rank 2 bundle on rules and not Hirsebus surfaces with having this invariance D and R, which sits in this kind of exact sequence, then E is ample even on leaf. Again, restriction to a generic fiber and section C naught and sections of the form C naught plus NF are ample, or N has to satisfy this property, and there is a finitely many choices for N in this case. And here are some references. So the question posed by Vishwas, Hanumantu, and Nagraj is this in paper, and so this is our preprint. Most of the work based on this. So section 4 in this paper is what I presented to. Thank you for your attention. I'll stop now.
Thank you so much, Neeraj, for your talk. So are there questions for the speaker? Okay, so so if there are no questions for the speaker, let's thank you. Thank you so much.
Thank you.
So in the meanwhile, Dr. Bhivash Khan, you can share your screen.
Okay. Hello. Is it visible?
It's visible.
Yes.
Okay, welcome everyone. It's pleasure to have Bibhash Khan with us from ISO Pune. He will speak about Seshadri constants on bot towers. Welcome.
Thanks. Also, I'd like to thank the organizer for giving me this opportunity to speak here. I will talk on Seshadri constants on bot tower. This is a recent work joined with Indrani the line algebraic varieties. For Ampleness, as this is how story begins. So let's take non-singular projective variety. A line bundle L is ample if and only if there exists a positive number epsilon such that for all point x and curve C passing the intersection of Taylor C is greater than equal to epsilon times multiplicity of x. So here multiplicity is a non-negative integer which detects the singularity of the curve at the point. It is normal to ask for the optimal value of epsilon in this theorem. This leads namely to the following definition of Seshadri constant. So let L be a naive line bundle, a complex projective variety. So for a point x in x, the Seshadri constant of the line bundle L at x is denoted as epsilon x Lx, and it is defined to be the infimum of E or the ratio L dot by minus X. That is for all curves C, all reduced curves C passing through the point X. So this ratio is called the ratio. So one of the original to use the constant towards a proof of the conjecture says X is non-singular projective variety dimension n and L is amplified. Then K plus n plus 1 is global and X plus n plus 2 is billion. So that
I think there are some severe internet problems. Yeah.
We have lost the connection.
Right. It was, I think, due to unstable internet connection. So we can wait for some time for him, I guess. Yeah.
Do you have his phone number?
You are back.
So Bibhash, can you share your screen again, please? You are muted. You're muted. First, unmute yourself in order to talk. Yeah. So
now is it visible?
Wait.
Yeah, your sound was not very clear.
Now, yeah.
Now is it clear?
I think it's slightly better.
Okay.
Yeah.
You can also switch
can-
off your
you can
video
turn off
if you
your
want.
video maybe.
Yeah. If it is
Okay.
taking too much internet.
Okay. Is my slide visible and it is clear now?
Yes. Go on. Yeah. Proceed. Yeah.
Okay. So if Seshadri constant is bigger than or one, then this will be very simple. But soon Miranda shows that this approach will not be helpful to to conclude Fujita conjecture, as Seshadri constant can be arbitrarily small. So this means that in the first place, this condition may not be satisfied. Nevertheless, it soon become clear that Seshadri constants are interesting invariant to study in their own rights. Now the research regarding Seshadri constant involve, of course, first of all, computing Seshadri constant for a given variety at any point, but it turns out to be a very difficult problem, not always possible. So the next best thing is to give as good bound as possible for them. And another interesting thing is to check if they are irrational. So till now, there is no example where Seshadri constant is irrational. However, it is rather unlikely if all Seshadri constant will be rational. Constant will study extended for the case of surfaces. For example, varieties that study by authors like Nakamae, Lazarsfeld, Bauer, Tivade, and so on. Right. We are interested in this class. So, Tiro and Harry most of the time has computed only the finitely many cross in a equilibrium vector found or for subsequent arbitrary Tory variety.
So you lost the connection once again, probably.
Yeah, I think we can try a little bit for him to
Sure.
reconnect you.
So Shan is writing in the chat.
No, Shanda, we actually cannot hear also.
Hello.
Okay, okay,
Yeah.
all right.
So maybe we can have the next talk and then we get back to Bhivash afterwards. Because
that might be a possibility. In the meanwhile, his internet connection might get stable. Yeah.
We maybe improve. Yeah.
Yeah.
We can't hear you, Bhivash.
Yeah. Can you hear me now?
Yeah. So Bhivash, what we are telling is you can take your time, so that internet connection becomes stable. In the meanwhile, we can have talk by Dr. Anup Singh. Okay.
Okay.
Okay. So you take your time. Okay.
Okay.
Yeah. So Anup, are you here?
Hello.
Hello,
Yeah.
Anup.
Hello.
So
Can you hear me?
Yeah, we can hear you very clearly. Yeah. So
Oh.
are you ready to present?
Yeah, sure, no
Yeah,
problem.
please share your screen.
I was
please.
in the queue, so yeah, it's
Yeah.
okay.
Okay. Yeah.
So can I share my screen now?
Please. Yeah. Please.
Okay. So wait a moment. Yeah. Okay. So can you see this? Hello.
Yeah. Now it's visible. Go to the full screen mode.
Yeah. Of course, I'll go. Is it fine now?
It's fine. Absolutely fine.
Hello.
Yeah.
Yeah.
Fine. Absolutely fine.
Okay. So I think it's going fine. Okay.
Great. So maybe we can get started. So it's a pleasure to have Dr. Anup Singh with us from HRI. He will speak on the moduli space of logarithmic connections over a compact Riemann surface. Well, please go.
Thank you so much. First of all, I would like to thank organizers, such a wonderful this virtual math fest, and giving me this opportunity to speak here. So, title of my talk is. Wait a minute. This is someone is okay. Sorry. So, title of my this talk is on the moduli space of logarithmic connections over a compact Riemann surface. So. Working. So as far as history and motivation is concerned, so the notion of moduli spaces are very fundamental in classification problems in algebraic geometry. That is, if we are given a collection of objects and equivalence relation, then the problem is to describe the set of equivalence classes. And here comes the notion of moduli spaces. In 1993, Nitsure constructed the moduli space of semi-stable logarithmic connections. And again in the same year, kind of, but later year in 1994, Simpson gave a very general recipe to construct the moduli space of lambda modules, where lambda is a sheaf of differential operators. So once we have a moduli space, we study its a lot of algebrogeometric invariants. So Picard group is one of them. And it has been studied extensively by many algebraic geometers. So in 2005, Biswas and Raghavendra studied the moduli space of logarithmic connections, singular exactly over one point with fixed residue, and described the algebrogeometric invariants of this moduli space, like algebraic functions and Picard group, and also compactification. So here we study the same for the moduli space logarithmic connection, singular over a finite subset of a compact Riemann surface with fixed residues and of course without fixed residues. So here we are replacing our moduli space rather than singular exactly at one point to finitely many points. So next thing, definition and all. So throughout this talk, X will denote a compact Riemann surface of genus greater than or equal to 2. And S is a finite subset of X such that these points are disjoint. They are not same. So let Z is equal to X1 plus dot 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 plus Xm denote the reduced effective divisor associated with this subset S. The notion of logarithmic connection was introduced by Pierre Dulin in 1970 in this lecture note, which is very useful note, and it studies the regular singular points of differential equations. So as far as definition is concerned, let E be a holomorphic vector bundle on X. A logarithmic connection on E singular over S is a C-linear map D from E to E tensor omega 1x tensor OXZ. This is a line bundle corresponding to divisor Z, which satisfies this Leibniz identity, which is D of Fs is equal to FDS plus DF tensor S, where F is a local section of OX and S is a local section of E. So can you hear me properly? Hello? Hello?
Yes.
Hello? Okay. That's great. So when logarithmic connection is given, we can talk about residue of a logarithmic connection. So by a pair in this talk, we mean that D is a logarithmic connection in E singular over X. So the subset S, we take any point X beta in S. The fiber is canonically identified with this complex number by sending a meromorphic form to its residue. Actually, because of this, given a pair, we get an endomorphism in this fiber of a vector bundle, and this endomorphism is called the residue of a logarithmic connection at this point Ex beta, where Ex beta denotes the fiber of E at X beta. Now given such a pair ED, due to Otsuki in 1982, we have a this formula which relays the degree and the trace of the residue, and this gives the constraint on the degree. Means you can fixing this residues, you can immediately get what is degree is. So degree of E plus summation j is equal to n to m trace residue d comma xj is equal to 0, where the this notation res d comma xj, this is the residue of this logarithmic connection. Now this formula is very important, we will see. Coming back to the moduli spaces of logarithmic connection, the slope of a vector bundle is defined by degree upon rank, and a pair ED is said to be semi-stable. So this is, I'm talking about the semi-stability of logarithmic connection. So a pair ED is said to be semi-stable, respectively stable, if for every non-zero proper subbundle f of E, which is invariant under D, that is df, the sections of f goes inside f tensor omega 1x tensor ox. Oh, I forgot to write here z. Okay, that's fine. We have mu f less than or equal to mu e. The slope is less than or equal to mu e for these bundles which are invariant under D. Respectively, mu f is strictly less than mu f, where mu e is a slope of E for the stable one. As we know, for stable vector bundles, it is true for every non-zero proper subbundle, but for logarithmic connection, it has to satisfy only those proper subbundles which are invariant under D. Now, we consider holomorphic vector bundles of rank n and degree D such that D and n are co-prime. For I is equal to n to m, we fix rational numbers such that multiplication with n lambda I belongs to Z. Now we consider the pairs ED satisfying the following conditions. ED is a logarithmic connection of rank n and degree D singular over S with fixed residues. So here I'm fixing residue of this special kind. I have chosen the numbers in Q and such that n into lambda I in Z. So residue I'm choosing lambda I into identity of these identity morphism on the fibers of a vector bundle E. So this is for all I is equal to 1 to m. So from the above assumptions and from this this Otsuki's formula, we have this. We immediately conclude that d plus n summation I is equal to m, lambda is equal to 0. And if we assume further, because d and n are co-prime, we will see that this logarithmic connection, because of this relation, this is automatically stable. So I'm saying this logarithmic connection is stable. It doesn't mean that vector bundle is stable. Vector bundle may be unstable or semi-stable, whatever, but this is automatically stable. Now let MLCND denote the moduli space which parameterizes the isomorphic class of pair CD. Then MLCND is known to be irreducible smooth quasi-projective variety over C. This is due to Nitsure and Simpson, and this irreducibility follows because we have considered there is a theorem by Simpson. We have considered. I'm sorry. I'm sorry. It's going. It's jumping here. Because we have considered the genus of curve is greater than or equal to 2. Okay. So here is the first result. So first of all, let MLC prime ND subset of MLC ND denote the moduli space of logarithmic connections whose underlying vector bundle is stable. Is stable. But the vector bundle need not be stable, underlying vector bundle. So I'm taking further small subset of this where underlying vector bundle is stable. Now let UND denote the moduli space of stable vector bundles of rank n and degree d over x with n and d co-prime. It is known that UND is irreducible smooth is smooth projective variety. It's not quasi-projective variety, it's projective variety. But MLC-ND is a quasi-projective variety and it is open subset of this. So MLCM prime ND is also quasi-projective variety. So we have a compactification of MLC prime ND. See, still I'm able to compactify only this MLC prime ND due to this UND, but not MLCND. This is again an open problem to compactify because this is a quasi-projective variety. So what is the natural compactification is MLCND? It is not done. So it is an open problem. So MLC prime ND, I'm going to compactify this thing. So theorem is there exists an algebraic vector bundle E over UND. This is Xi, capital Xi, such that MLC prime is embedded in this projectivization of this vector bundle with complement as the hyperplane at infinity. So because of this is a smooth compactification of this MLC prime ND, and this theorem is used in proving this Picard group isomorphism. So before going to this, so we have a natural morphism P from MLC prime ND to UND because we have considered MLC prime ND is all those pairs E comma D where underlying vector bundle E becomes stable. So if E is stable, then we can send just forgetful functor sending this pair ED to E. Then it will give you a UND. It goes into this moduli space. Now there is a criterion for the existence of a logarithmic connection in a vector bundle over a compact Riemann surface with prescribed residue. It has been proved due to Biswas, Dan and Paul in 2018. And because of this, and because our residue satisfies this formula that d plus n summation lambda is equal to 0. Because of this, it is surjective. So there exists a vector bundle, and if residue satisfies that relation d plus n lambda I is equal to 0, summation n summation lambda is equal to 0, then there exists a vector bundle, holomorphic vector bundle over X with logarithmic connection in this vector bundle having those residues lambda into identity of these. So because of this result, this criterion P is surjective. Now this morphism will induce a homomorphism on the Picard group which sends a line bundle here taking pullback here of Picard groups where this Xi sends P pullback of Xi where Xi is algebraic line bundle over this. This homomorphism of Picard group is an isomorphism. So we have that Picard group of these two moduli spaces are actually isomorphic. And proving this theorem, this is a core result. This has been used. The compactification has been used. Okay, going one slide down. So again, similar result can be proved. Fix a holomorphic line bundle L over X of degree D and fix a logarithmic connection. Now, DL, actually, now what we are doing is we are considering moduli spaces kind of with fixed determinant. But here we cannot fix just line bundle. We have to fix some connection on it because we are parameterizing the pairs E comma D. So that's why fix a holomorphic line bundle L over X of degree D and fix a logarithmic connection DL singular over X with residue this. Now this is being a complex number because endomorphic, because fiber of this L is isomorphic to a complex number. So lambda J is already chosen to be a rational number. So n into lambda J. So let MLC NL contained in MLC ND be the moduli space of parameterizing isomorphic classes of pairs such that the top form of E comma D tilde is isomorphic to this pair L comma DL. This isomorphism is means there exists an isomorphism from top pair to L which satisfies the commutative diagram where D tilde and DL are connections going from top exterior form to top interior E tensor with omega 1x tensor OXZ, and similarly here. And D tilde is the logarithmic connection on this induced by D. We go further down. We consider this moduli space. Now we consider again the moduli space whose underlying vector bundle is stable. Why? So that we can get a morphism from this MLC prime NL to ULND. What is ULND? ULND is the moduli space of a stable bundle, stable vector bundles with fixed determinant. Now, because of this variety, we have a natural morphism of variety that induces a homomorphism of Picard groups, and here also these this Picard groups are isomorphic. This homomorphism of Picard group is an isomorphism. Now, actually, now this is the main theorem of this talk. So assume that genus of X is greater than or equal to 3, then this MLC prime NL, this is the moduli space of logarithmic connection kind of with fixed determinant L whose underlying vector bundle is stable. Then the global sections are actually constant, means algebraic functions are constant maps on this moduli space. Algebraic functions, I mean regular functions. Yeah. So to prove the above theorem, we proceed as follows. Actually, theta, we take the ample generator of this group and C theta sheaf of sections of open subset are holomorphic connections in this. And for every open subset, the space of holomorphic connection in affine space modeled over this. Therefore, C theta is omega 1 ULND torsor. So we take a torsor and the two torsors C theta MLC prime ND, these two torsors are actually isomorphic as an algebraic variety. So to prove that this constant algebraic functions over MLC prime ND, it is enough to prove from C theta, this space. So it has been proved using Atiyah bundle and means computing the global sections of symmetric powers of Atiyah bundle and Hitchin fibration on this T star of ULND. Using these two techniques, we are able to prove, and in this way, this will complete this theorem. Now, with arbitrary residues also, we can characterize algebraic functions. So we fix a pair L comma DL as above, but without fixing residues. I'm not fixing here residues at all. NLC NL denote the moduli space parameterizing all pair CD satisfying this condition. N and D are mutually co-prime, as you know. The residues lies in the center of this Lie algebra associated to GLNC. This is so residue can be anything. I'm not fixing residue, but I'm fixing this condition that trace should go in integer due to certain reasons. And it is a logarithmic connection singular over S of rank n and degree D, which satisfies this condition as we saw previously. Then this moduli space irreducible normal quasi-projective variety. It need not be smooth. This moduli space need not be smooth. So this is a irreducible normal quasi-projective variety over C. So here we have a result. We characterize somehow this algebraic function. So V is equal to, we take this tuple such that n into alpha j belongs to Z, and this will satisfy this condition. So this is the subset of CM. So we can define a map from NLCNL to V, which sends this pair to trace divided by the ranks. So from the Otsuki's condition, actually these numbers will go inside V because they satisfy this condition. Then size and surjective homomorphism. Size actually surjective homomorphism, and and we have this theorem. So let X be a compact Riemann surface of genus greater than or equal to 3. Then every algebraic function on NLC and L factors through this map. This map. So if I take any algebraic function on this, then there exists a unique function from V to C such that this diagram commutes. So this result means this. And here are the references for this. This is the thing where I studied. This is the paper. This is in our on archive also. Moduli space of logarithmic connections singular over a finite subset of a compact Riemann surface. This to appear in math research letters. And this is the paper from where I got motivation, Biswas and Raghavendra. And this is the paper where criteria for logarithmic connections. And this is a Nitsure's paper, of course. And these are the two papers of Simpson's where he talk about moduli spaces of lambda modules. And this is the Otsuki's paper, residue formula for Chern classes logarithmic connection. Now, thank you so much for this. Hello.
Thank you so much.
Thank you.
Are there questions for the speaker?
I cannot exit.
Hello, your voice a bit low.
Hello. Hello.
Yeah. Hello. Yeah. So we could hear you. So
yes. So hello. Is there any question? Hello.
Hello.
Hello. Can you hear me?
Yeah, we do hear you.
So is there any question or something? I cannot see actually.
No, there are no questions in the chat box posted yet. So
okay.
the participants can directly ask you if they have any questions.
Okay.
Let's see.
Okay.
Okay, so
can I stop right now?
Yeah, maybe there doesn't seem to be any question. So
yeah, okay.
So let's thank the speaker once again.
Thank you so much. Okay.
So
shall I stop now?
Yeah, please stop. Yeah.
Okay.
Yeah.
I'll stop now.
Thank you for the wonderful talk. And Vibhash, are you there?
Yeah, I'm here. Can you hear me now?
Yeah, I can hear you very properly. Can you share your screen now, please?
Yeah, I'll try. Well, is it visible?
Yeah, it's visible. Yeah. Go on.
Okay. Shall I?
Okay, please, Vibhash.
Okay. Sorry for the interruption. So let me just quickly go through the first few slides. So we have started with Sesardi's criteria for Ampleness, which sort of motivates de Mailly to define Sesardi constants. And so there is a connection with Fujita conjecture. But Miranda pointed out this approach will not be helpful to solve Fujita conjecture. Nevertheless, Sesardi constants have become an interesting invariant to study quite in its own right. So there are lots of work on surfaces, but there are few work on higher dimension. So we are interested in this class by toric varieties. Am I audible now? Hello?
Yes, you are. Okay. Don't worry. Yeah, carry on.
Okay. So Dirocco and Herring most of the point have computed Sesardi constant for torus fixed points, and for a toric variety there are finitely many torus fixed points. But later Ito has given bound for Sesardi constant on any toric variety at all points. However, it's not always possible. In some cases only it is possible to compute Sesardi constant explicitly. So now for Fano varieties, there is a work by various authors like Bauer, Zemberg, Liu Zhang, and so on. And very recently, Sesardi constant have been computed for Grassband bundle over curve by Bisa, Sonomoto, Nakaraj, and Neostate. So we are interested in Bot tower, which is a particular class of non-singular projective toric varieties. They are actually constructed by Grossberg and Carlson. So a Bot tower is a tower starting from a point x0, which is just a point, then x1 and so on. it is defined inductively as an iterated P1 bundle, so that at the kth stage, it is projectivization of the trivial line bundle and the line bundle Lk minus 1 in the previous step, on the previous step, xk minus 1. So x1 is just P1 and x2 is the Hirzebruch surface, so which is geometrically ruled surface over P1. So it is a fact that any such Bott tower arises from a collection of n into n minus 1 by two integers Cij, and these integers called Bott numbers. So the first stage of the Bott tower is P1, and on P1 Sesothy constant is known. So for any point Sesothy constant of O P1 A is just A. Now if we consider the next stage, which is Hirzebruch surface, projectivization of OP1 direction OP1R. If we take a line bundle L as a tuple A1, A2 with respect to a suitable basis of Picard group X, then there is a section gamma with self intersection minus R, so that the Sesothy constant is given as follows. So for the points on gamma, it is just minimum of A1 and A2, and otherwise it is A2. So Sesothy constant for Hirzebruch surface have been computed by various authors like Sistek, Garcia, Honumunt, and Mukhopadhyay. So we would like to extend this computation to higher stage of Bott tower. So we will use the extra structure of Bott tower to do so. So first we compute the nave cone, the cone of effective divisors. To do so, we will restrict to Bott numbers which are positive. So it follows that the Picard group is generated by n dividers d1 up to dn. In fact, they are cross invariant prime dividers. So if L is a line bundle numerically equivalent to A1 D1 up to AN DN, so we denote it as a tuple A1 up to N. So we have found an ampleness criteria which says that L is A1 up to N is ample or respectively net if only all of these integers are positive or non-negative. Now, having found the nave cone, next we compute the Mori cone, which is a cone of curves in Bott tower, and we use the fact that Mori cone is dual to the nave cone. So to do so, first we construct some subvarieties. Let us fix a point xn and describe with special class of subvarieties xnj containing some rational curves gamma nj. Note that these subvarieties xn and curves gamma nj will depend on x. So let this is our given Bott tower. So we set xi1 to be xi, and we denote the composition of the projection from xi to x1 by pi I. So x sits inside here. So we take the inverse image of pi and x via pi I, so which is a subvariety of xi, and we call this xi2. So note that x will be in xn2. So we will get a tower starting from x22 up to x32 and so on. It is a fact that it is again a Bott tower. So we can repeat the similar process here to get subvarieties like xij, and it follows that it starts at P1. So these xii terms will be all P1. So what we got is the following. So we are given this Bott tower. We have constructed n minus 1 more Bott towers, and this is the Hirzebruch surface, and each of the Bott towers starts at P1. So it follows that if we start with the Bott numbers for this tower is positive, then all Bott numbers for the vertical tower will also be positive. So now consider one of the vertical tower like this. So by construction, each of them has a section, and we denote the composite of this section by sigma I and call gamma ni the image of xii inside xni. So this will give n curves such that gamma nn is just xna. So x is inside gamma nn. We denote by gamma n1 by gamma n. So we have constructed some subvarieties of xn like xn2 up to xnn, and each of them contains a curve gamma n2, and so on. It follows that these are the curves which generate the Mori cone of the Bott tower xn. In fact, they are dual to the generators of the Picard group d1 up to dn. let's move to our main result. So given a bot tower with positive bot numbers, if L is a naive line bundle, then for any point x, the Sesati constant is given as follows. Like the points on the section gamma n, on the curve gamma n, is given by minimum of this first one, A1, and Sesati constant of L restricted to x and 2x. So note that x is always in x and 2. And otherwise, it is just Sesati constant of L restricted to x and 2x. So let's move to some corollaries. Yeah, so as a application of the main theory, repeated application, we can see that the Sesati constant is given by minimum of the intersection product in L dot all such curves gamma and I which contain the point x. So this product is nothing but AI. So in particular, Sesati constant will be one of the coefficient AI. So we call a curve Sesati curve if the Sesati ratio corresponding to the curve gives the Sesati constant at that point. So from the corollary, it follows that this curve, one of the curves gamma and gamma and 2 will be Sesati curve of L at a point x. Now let me recall the result of HMP, which says that for a non-singular complete toric variety, the Sesati constant at a torus fixed point is given by a minimum of intersection of L dot C, where C is invariant curve containing x. So in some sense, we have generalized this result for arbitrary point in bot tower. However, no longer these curves are invariant here. Let's move to the next corollary, which says we can compute the Sesati constant of the line bundle, which is denoted as epsilon xnl, which is taken as infimum of all these epsilon xlx. It is just minimum of these coefficients a1 of 10. Similarly, we can compute the supremum, which is just an. One final remark is that note that so far all Sesati constant on bot tower is integer. This more generally this was true for torus fixed points on arbitrary toric varieties. However, there can be toric varieties with Sesati constant rational. One of the example was given by Ito. So let me come to the final example, which illustrates our result. So by repeated application of our results, we can explicitly compute Sesati constant like this. So if L corresponds to the divisor 1, 3, 8, 4, then depending on x belongs to which card, we can get the Sesati constant as 1, 3, and 4. I'll stop here. Thank you. Hello?
Yeah, okay. Any questions?
Is Jyotida here?
I was actually going to ask the same question.
Hello?
Yeah, if you guys have any question, then you can ask directly to Bibhash by unmuting yourself.
Okay. Thank you so much for your talk.
Thanks.
So, are there questions for the speaker? Okay, so if there are no questions for the speaker, then let's thank him once again.
Thank you.
Thank you so much. So,
yeah, we can start the next talk at 12:10. The scheduled time is 12:10.
Yes. Okay. So
we can have a short break.
Yeah.
Okay. Good.
Vidisha, you can share your screen maybe.
Okay. Which one I should select? This one, I guess.
Just share screen, green button. You can see the green button on your screen, right? It's visible. Yeah.
Okay, then the presentation thing is.
Yeah, so is the time to start?
Okay,
Yeah.
the presentation is not coming, so how should? Okay, it's coming.
But
Is it
the left hand side of your screen? Can you just erase that or that menu kind of thing? All the pages are visible.
okay? Okay, just wait. Just give me a second.
Yeah, sure.
You can open the file in Adobe maybe.
Yes, I have opened that.
Then maybe if you press Control L, you automatically
okay. Okay, is it fine?
Yeah.
Okay.
Yeah.
Absolutely fine. Yeah. Go on.
Okay. So let's welcome Vidisha Roy from Harita Research Institute. She will speak about torsion groups of model curves over cubic and textic fields. Please.
Thank you. At first, I would like to thank the organizer for taking this nice initiative and for giving me the opportunity. So the title of this talk suggests that today we will discuss about elliptic curve over number fields. So let us start with that. Let K be a given number field and E be an elliptic curve defined over that number field K. It means that the coefficient of the elliptic curves are coming for the given number field K. So now, since we know that if the characteristics of the number field is not equal to 2 and 3, then we can modify that elliptical E in terms of Weiss transforms. We are doing that because of easier of the calculation. And then we are taking this set. What is this set? This set is called the set of K rational points of E by taking all points satisfying the given elliptic curve E along with the point of infinity. So why this set is important? Because this set actually forms a group under addition with the identity element O, that O is the point of infinity in the projected plane. So now we know that the set EK actually an additive group, and by a celebrated theorem of Goel, we can say that EK is not only additive group, it is a finitely generated abelian group. So now we have in our hand a finitely generated abelian group. Then we can apply the structure theorem of group theory, and we can write EK, which is isomorphic to torsion part along with the R copies of Z. So this R is called the rank of the elliptic curve defined over K, and this torsion part is called the torsion group of the given elliptic curve E over K. So now we have torsion torsion element, torsion group. So the next question comes that how this torsion group looks like. The torsion groups actually looks like of the from Z mod nz or Z mod nz direction Z mod nz where m divides n. So it means that these are only two possibilities of like torsion groups. So there are only two possibilities, either this form or this form. So though it is at only two possibilities, but if we collect all possible torsion groups, then we define a following set. So what is this set? So only we are fixing a positive integer d, and then we are taking all number field of degree d and all elliptic curve defined over those number field. And then we are collecting all torsion subgroups of those elliptic curve up to isomorphism and putting them in a set. So that set is denoted by phi d. So since we fixed only a positive integer d, then we are getting the phi d in terms of d. Though this is nothing but a set. So what information we know about the set? So when d equal to 1, then it means that k equal to q, then measure proves that there are only 15 possibilities up to isomorphism. It means that if we fix k equal to q and we take all elliptic curve over the number field q and take all torsion subgroups up to isomorphism, then we will get only 15 torsion groups up to isomorphism. So next case is for the quadratic case. Quadratic case, Kamni, Kamsu and Momo said they proved that there are 16 possibilities. And for the cubic cases, we know the sum answer, but not in general, full answer. So next question is that does it, is this, the set is going, we see that, but is it finite? For answering this question, Medal defined this set. What is this set? This set is a set subset of prime numbers. It captures set of all primes such that there exists an elliptic curve of defined over a number field of degree d, and there exists a torsion element in the torsion group such that the order of that element is p. So why this set is important? Because he proved that this set is finite and he could calculate the what could be the largest element of this set. So the largest element is bounded by this and in terms of the given integer d, and later austerely improve this bound. And once we know this bound, uh, then we can say that phi d is finite and it depends only on the given d, that is the degree of the number field, because this bound is depending only on d. So as we have started that by the result of measure and Kamnikans and Momose, that these are growing, but this is actually finite. So once we know, get a finite set, we would like to know the elements of that finite set. So previously only for phi d we could get the few information up to degree d. So then we are restricting the family. So how we are restricting the family? So we are taking all elliptic curve defined over rational number. It means that the coefficients are coming from only over q. So coefficients are coming from q, but we are allowing the torsion groups over degree d number field. So we are taking the satisfying element over the higher degree number field, but we are allowing the coefficient only over q. So in this way, we are restricting the family, and we are trying to get more information. But there are some result in this restricted family also by Najman, Enrique, and their collaborators. But in general, when the degree is bigger than equal to 7, then we don't know the answer yet. So then we can further restrict our family. So how we can restrict our family? We can impose one more condition on that elliptic curve. Then we can impose the condition, the well-known complex multiplicity condition. And then we can define the same constant over CM elliptic curve. So for the CM elliptic curve, if we want to ask the same question, then also there are some progress. But recently, Clark et al., they could compute from 1 to 12. It means that when the degree of the number field in between 1 to 12. But previously, it was known for 1 to 3. But they recomputed also for 1 to 3 and along with 4 to 12. So their paper actually give information so about the set. So what can be the set when you take the subfamily up to 12. But after 12 also, we don't know the we know the set, we don't know the set actually, then we can take the another subfamily. So how we can take the another subfamily? We can take the model curve. So model curve is of the form y square equal to x cube plus c. It means that the y stress form, so there was some ax type of thing. So here that coefficient along with the x also 0. So in this curve is a CM elliptic curve. So in that sense, this family of the model curve is a subfamily of CM elliptic curve. So let's see what we know about this subfamily. So we are taking the same notation over here. So it means that when we are taking the model curve, then we are denoting it by M, and here the two notation along with the same what we have defined in general, that over K or over Q. So in this talk, we, as I told that, we will discuss about the cubic field and the sextic field. So what is the goal of this talk? So here we are considering elliptic curve and we are taking two subfamilies. So the rational model curves and the model curve. So it means that we are taking a subfamily and Q, whatever I mentioned. And among these two subfamily, this family, we are taking two cases over cubic field and over sextic field. And we are studying this, we will study this set and that this set, and over the general number field also we are taking this, we will study this set where the over cubic field and over sextic field. So here with classification you have seen. So what is the with classification? So with classification means if one element of the torsion set, so from the dash set has been given, so when exactly that group will appear, that depends only on the elliptic curve and the number field. So the reverse question that given an element of this set, so we should give back the possible model curve. So that is called the complete classification. So first observe this case over cubic fields, rational model curve. But before that, since we have seen that over cubic field and over sextic field, but what about the k equal to q and the quadratic case? K equal to q has been studied by Knapp long back, and he proved that there are only 4 possibilities, and all possibilities are cyclic. So these are the possibility. It means that only z mod 2z, z mod 3z, and z mod 6z. So what about the quadratic cases? Quadratic case, Pallab Kantide, he proved that when the quadratic is, then there are these many possibilities, and you can see that some of them are non-cyclic. So the complete classification means, as I mentioned, that when in particular these non-cyclic cases are occurring, for which model curve and for which quadratic number field. So for that, if we fix a quadratic number field and a model curve, then we have to give the information about this constant and about this d. So this information has been provided here. So z mod 6z is occurring only when c equal to these two choices and d has to be lie in this set. And similarly, the cyclic cases are occurring in these cases and non-cyclic cases are occurring in these cases. So what about the higher degree number field? So higher degree number field means, so when d is bigger than equal to 3. So in the same paper, he computed when d is co-prime with 1. So what about when d is not co-prime with 1? So that's why in this talk we have considered d not co-prime with 1. So the first two cases, when d equal to 3 and d equal to 6, we have taken here. So first see d equal to 3. And we are taking the rational model curve and we are allowing all cubic fields and we are taking this set. So here we can see that z mod 9z is occurring, which we didn't see neither in the k equal to q or not in the quadratic case. So first time z mod 9z is occurring. So when precisely this group is coming? So this group is coming when c equal to precisely 16 and k has to be of this form. And the other cases, there are several options, but these are finite options up to isomorphism. And later we will see the proof of this theorem. So, but now we see that when we are giving more relaxation, it means that when we are allowing the coefficients of the model curve C over the cubic field, then also there are same possibilities, but these possibilities are occurring with more choices. With more choices means, so previously we have seen that z mod 9j was occurring when c equal to 16, but here z mod 9z is occurring when c equal to square and 4c is a cube. So that is the difference. So we have more choices here for getting this torsion group. So here also there are some differences when we are giving more relaxation. So let us see the proof of the first one, that is for the rational model curve. So as I mentioned in the Merrill result, that we are considering the prime elements, because the order of the elements has to divide it by some prime element. So here if we can eliminate all the primes up to 5, then we could eliminate many choices. So let us first consider the prime order element where the prime is bigger than or equal to 5. So suppose that there exists an element of order q, where q is bigger than or equal to 5. Then q has to divide the cardinality of the torsion group, which I have denoted by t. So now we are taking p congruent to 2 mod 3q, and along with another condition that he has good reduction at p. It is possible because he has bad reduction only at finitely many places, and times in arithmetic progression says that there are infinitely many choices for this case. So along with these two conditions, we have enough choices of prime. And then we are splitting it where E is at the ramification and this is the residue degree. And this is the well-known fact in number theory. And then we are using this lemma. So this lemma says that if we quotient it by a prime ideal, which the prime ideal are coming from this splitting, then after reducing it, we will get an injective map. So that injective homomorphism will allow that if Q divides the cardinality of this torsion group, then Q has to divide the cardinality of right hand side. So why we are taking this? Because we can easily calculate. So how we can calculate is that will come from this lemma. So when P congruent to 2 mod 3, which we took the earlier, that P congruent to 2 mod 3Q. So then we can actually calculate it. So after calculating, we get that this is nothing but P to the power Fj plus 1. And then we are allowing that P congruent to 2 mod 3, and we are getting that this is nothing but this one. And then we have two choices, that Fj either 1 or 3 because of the property of residual degree, and we are getting 3 congruent to 0 and 9 congruent to 0 mod q, and that is not possible. And this is the contradiction, and we can conclude that there exists no point of bigger than or equal to 5. So then we have to deal with all those primes which are smaller than 5, that means 2 and 3. So now we have calculated what can be the possible torsion subgroups. That is the two torsion we are calculating. So I didn't put the calculation here. So similarly for the 3 torsion also we have calculated, and we get back that these are the choices for C, and these are the choices for the K. Choices means these are the property of the K and property of the C for which we are getting 3 torsion. So now what is the power of 2? So if we can eliminate power of square of 2, it means 4, then we can eliminate the above power also. So first we have eliminated the power of 2. So after eliminating square of 2, but we have seen that z mod 9 was occurring. So it means that we have to consider square of 3. So square of 3, that is 9. So that is occurring only when c equal to 16 and k has to be of this form. And I didn't include the proof here. And then the higher power of 3, that is 3 cube, and since 9 is occurring, then there is a possibility of 9 into 2, 18. So those two cases also we have to eliminate. So now the remaining cases is 2 into 3, that is 6. So now we have to calculate the all possible element of order 6. So that we have calculated, and this finishes the proof of the theorem. Because first we have eliminated all primes bigger than or equal to 5. Then we calculated 2 and 3. Then power of 2 we have addressed. Then power of 3 we have addressed. Then the product of 2 and 3 and product of 2 and 9. And the higher power of 3 we have eliminated, and product of 2 and 3 we have calculated. So in this way we are getting back all the possibilities of the rational model graph over cubic field. So as I mentioned that over sextic field also we will consider. So let us see the sextic field. So sextic field means the degree of the number field is 6. And the first we are taking the rational model curve. Then as we have mentioned in the quadratic case also. So we have witnessed in the quadratic case non-cyclic cases. So here also we can witness non-cyclic cases, but involving Z mod 9Z, which we didn't see earlier. So when precisely these groups are coming, so the cyclic cases are coming for these cases. So it is depending on the omega cube root of unity, and some cases it is depending. And this is the Z mod 2Z, the last cyclic cases. The rest are non-cyclic cases, and non-cyclic cases are coming for this property has to be involved in C and the L, that is the sextic number field we have taken. And if we give the more more relaxation, that we are allowing the coefficient of, from the sextic field, then we can get the higher degree torsion group, that is Z mod 19Z, Z mod 7Z, and this Z mod 7Z we didn't see earlier, and this also we didn't see earlier. So here we are getting some higher order element. So if we give the more relaxation, then over higher degree, then we may get some more groups, but we may not get. And these two results in sextic field, and these are the references. So this is the Clark et al. Paper, which I mentioned that, where they have computed all CM cases from 1 to 12. And this is the NAP result. And well, on the first model curve over Q, they have computed. And this is the result of Pallab and Dide, who calculated over quadratic number field. Thank you for your attention.
Let's thank the speaker for excellent talk. So, are there questions for the speaker? So, if not, then I have just a very short question. Is there something known about the torsion subgroup of the elliptic curves over quintic fields, maybe? And hello, sorry, maybe you have muted yourself. You're not.
No.
Okay.
Okay.
Now it's working. Yeah.
So is there any, I didn't able to see the chat. Okay.
Okay, and there is also one question which says that, is there any result for D greater than 6?
Yes, so as I mentioned that when D is co-prime with 6, then that is coming similarly. But when D is not co-prime with 6, then still there is no result. But we are trying to prove some cases, for some specific cases, when D is not co-prime with 6, but till now, as per my knowledge, only these two has been addressed.
Okay.
So I assume that this question is for the model curve, but for the CM curve, up to 12 is known, and the other cases, that up to cubic and the some kind of curves for the quartic cases, also some cases are known.
Okay. So, are there further questions for the speaker? Okay, if not, let's thank her once again. Thank you so much.
Okay. Can I stop the sharing?
Sorry, maybe there are a few questions.
Okay, yes, please. Hello, am I audible?
Yeah, I think you're audible. Yeah.
I have a suggestion for speakers. They should not keep the thank you screen on the screen, but some slide so that people can see rather than just get thanked.
Okay, sure. Thank you, ma'am.
Great. Thank you so much.
Okay.
So, Shoma, we get started.
Yeah. So the next speaker is Jyotirmoy Ganguly.
Okay. So,
Jyotirmay, are you here?
Yeah, I'll share my screen.
Sure.
Okay. Wait, I can't bring to the presentation mode. Yeah, is this my screen visible?
Yeah, perfect.
Okay. Okay, good afternoon, everyone.
Here to have Dr. Jyotirmoy Ganguly with us. He will
Okay.
speak about spinorial representations of orthogonal groups. Yeah, please.
Yeah, thank you. And I thank all the organizers for giving me this opportunity to present my work in the symposium. So I'll be talking about spinorial representations of orthogonal groups. This is a recent work with Rohit Joshi. Okay, so to set the stage, I will just define the terms that I would use. So let G be a Lie group, real Lie group, and pi be a real representation of G. So throughout this talk, I will restrict myself my talk with real representations only. And such a representation is called orthogonal if the image lies inside the orthogonal group. And the pin group is a non-trivial topological double cover of the orthogonal group uh, with a covering map rho, which is a map from pin V to OV with kernel plus minus 1. Okay, and here is the definition of the spinorial representations. So you start with a orthogonal representation of the Lie group G, so that the representation lands inside the orthogonal group OV, and you have this pin group, which is a double cover. And so the representation pi is called spinorial if there exists a homomorphism pi hat such that this diagram commutes. Okay. So in fact, all the representations of the orthogonal group are orthogonal, and we determine the spinorial representations of the orthogonal group. Rather, we give some criteria to determine the spinorial representation. So here I will briefly discuss about the pin group. So you take the real vector space V with the standard basis E1, E2 up to En, and associate the negative definite quadratic form with V. So one can define the Clifford algebra CV, which is the quotient of the tensor algebra by this ideal generated by the elements of the form V tensor V plus mod V square for elements in V. So without going into much details, uh, one can define pin group in this simple way. Uh, so the pin group is a subgroup of the group of units of the Clifford algebra, which is generated by the unit vectors in the vector space V, which also lies inside the Clifford algebra CV. Okay. So I will just mention the properties that the pin group has and we need for the calculations. So the basis elements EI, they also lie inside the pin group, and the image of these elements EI under the map rho are the reflection matrices. So the matrix REI is the diagonal matrix with -1 at the ith position, and everything else is 1. All the other positions are occupied by 1. Okay. And because of this negative definite quadratic form, we have the relations EI square is -1 and EI EJ is equal to minus EJ EI whenever I is not equal to J. Okay. So to get a flavor of the spinoriality business, let us do this simple example. So take the cyclic group of order 2, which is generated by this element G. And this we know that the irreps of C2 are just trivial and sign. So any representation pi of C2 will look like this. I have trivial representation appearing m naught times and sign representation appearing m1 times. And note that this is for the representations of C2 are all orthogonal. So pi in general is orthogonal. And the image of this element G under the representation will be this diagonal matrix uh, where -1 appears m1 times and the rest of the diagonal positions are occupied by 1. So let me denote this matrix by dm1. So we claim that the representation pi is spinorial if and only if m1 is 0 or 3 mod 4. So the proof is quite easy. Just note that this matrix dm1 can be written as product of reflections re1 re2 dot dot em1, and from the using the relations in the previous slide, we get that rei is basically the image of ei under rho. So ei, these elements are elements lie in the pin group, and you take the image of these elements under this covering map, you get the reflections. So in fact, dm1, this matrix is the image of this element e1, e2 dot dot em1 under the covering map. So one can take this element as a lift of G, the generator of C2, uh, in the pin group. So now the representation pi is spinorial if and only if there exists a homomorphism from C2 to the pin group, and that demands that the order of this element should be 2. And using the relations ei square is -1 and eij is minus ejei, one gets like this square is equal to -1 to the power this triangular number, and this triangular number m1 into m1 plus 1 by 2 is even if and only if m1 is 0 or 3 mod 4. So we have the result. Okay. Okay, now let's take up the case of orthogonal groups. So we have the orthogonal group OM is equal to SOM direct product C2 when M is odd, and it is SOM, the special orthogonal group, semi-direct C2 when M is even. So we just call them the odd and even orthogonal groups for convenience. And for the sake of computation, I take the generator of the cyclic group C2 to be G0, and the G0 is different for depending on the parity of M. So when M is odd, we take this minus I to n plus 1, which is where I to n plus 1 is the identity matrix of order 2n plus 1. And when M is even, we just take this particular matrix. This is like you take the identity matrix of order 2n minus 2 and just add a reflection block at the end. Okay. So I will just talk about the spinoriality of the even orthogonal groups, because similar results follow for odd orthogonal groups. So a representation phi of O to n is spinorial if and only if its restriction to the subgroups SO2n and C2 are spinorial. So we have in general proved a result like if G is a group which is a semi-direct product of G1 and G2 where G1 is connected, then the representation of G, a representation pi of G is spinorial if there are restrictions to the subgroups are spinorial. Anyway, so this is the case for the orthogonal group. Okay, now let us survey briefly the how the irreps of O to n comes. So you just start with you just start with an irreducible representation pi lambda of SO2n. So the representations are basically parameterized by the highest weights lambda, and take the induced representation to the orthogonal group, call it rho lambda, and there are two possibilities. So in the first case, rho lambda is irreducible. Uh, so in that case, we take the if we take the restriction of rho lambda to SO2n, it decomposes as pi lambda direct sum pi g naught dot lambda, where pi g naught dot lambda evaluated at an element x is equal to pi lambda evaluated at g naught x g naught inverse. Note that we just need to determine the spinoriality of the representation rho lambda restricted to SO2n and C2. So therefore, this is important. So when rho lambda is irreducible, we call these type 1 representations. And the other case is when rho lambda is reducible. In this case, it decomposes as the irreps pi lambda plus and pi lambda minus, where the dimensions of both the representations are same as dimension of pi lambda. And these restrict to pi lambda plus minus restricted to SO2n is basically pi lambda, that is representation we started with. Okay, so in this case, we call these representations pi lambda plus minus as type 2 representations. And this is a fact that any irreducible representation of O2n is either of type 1 or type 2. Okay, so I will just mention the lifting criterion for representations of type 1 because a similar result is true for representation of type 2. Okay, so let this bracket denote the killing form for the Lie algebra of SO2n, and delta denote the half sum of positive roots for the Lie algebra of SO2n. Then we have this result. So the irreducible representation rho lambda of O2n for n greater than equals to 3 is spinorial if and only if both the following conditions hold. Okay, so we stated the result that rho lambda is spinorial if and only if its restriction to the subgroups SO2n and C2 are both spinorial. So these two conditions come from that result. So when you restrict rho lambda to SO2n, that representation is spinorial if and only if this condition holds. So this is like 2n n minus 1 by n into 2n minus 1 dimension of the representation of SO2n, and this quantity alpha lambda plus alpha g naught lambda, where alpha lambda is the inner product of these two elements. So this is even. So this is basically a result in the paper by Steven Spallon and Rohit Joshi, where they have like deduced all they have talked about spinorial representations of connected reductive groups in general. And in our paper, this is just an addition. So this is disconnected. So for that, we just need to think about what is the criterion for the representation pi lambda restricted to C2 is spinorial, and that happens to be this. The dimension of the representation of SO2n should be 0 or 3 mod 4. Okay. Okay. Now I will quickly talk about the Stiefel-Whitney classes of the representations of the Lie groups. So you just take a real representation pi of the orthogonal group, and one can associate something called Stiefel-Whitney class Wi pi, which belongs to the ith cohomology group of the orthogonal group with z mod 2z coefficients. Okay. And if I is strictly greater than the degree of the representation, this quantity is 0, Wi pi. Okay. So the 0th Stiefel-Whitney class is 1, which is basically the unit element in the cohomology ring, direct sum of Hij, and we have this quantity called total Stiefel-Whitney class, which is the sum of the Stiefel-Whitney classes Wi pi, I varying from 0 to d. Okay. And one gets that the first Stiefel-Whitney class gives the determinant of the representation. Now, the reason I am bringing this concept is there is a beautiful relation between spinoriality of a representation of a real Lie group, of course, orthogonal representations, and the first and second Stiefel-Whitney classes of the representation. So it is given by this result. So I have just mentioned it for ON. It is generally true for any orthogonal representation of a Lie group. So a representation pi of ON is spinorial if and only if W2 of pi plus W1 of pi cup W1 of pi is 0. And using the concept of Stiefel-Whitney classes, we give a criterion for the spinoriality of the representations of the orthogonal group in terms of character values. So we denote by GI the diagonal matrix consisting of -1 and 1, where -1 is appearing I times. And without going into the proof, I will just state the result. So a representation pi of ON is spinorial if and only if both the following conditions hold. So it is like the dimension of the representation minus the character value at the element D1, that should be equal to 0 or 6 mod 8, and the dimension of the representation minus the character value at D2, that should be equal to 0 or 6 mod 8. Okay, so here is one more result. So let G be a reductive real Lie group and G0 has finite index in G, where G0 denotes the connected component containing identity, and let K denote the maximal compact subgroup of G. Then an orthogonal representation phi of G is spinorial if and only if its restriction to the maximal compact subgroup is spinorial. Okay, so we can use this result to talk about the spinorial representations of GL and R, because the orthogonal group is the maximal compact subgroup in GL and R, and we have the criterion for spinorial representations of, to detect the spinorial representations of ONR in terms of character values. So actually this result follows. You take an orthogonal representation pi of GL and R. This is spinorial if and only both the following conditions hold. The conditions just depend on the dimension and the character value at this diagonal matrices T1 and T2. Okay, so here are some references. So this is the paper which goes with the same name, spinorial representation of orthogonal groups. We have done the cases for, like, we have considered little general cases here in the paper. It is, the preprint is available in the archive, and this is the paper by Steven Spallon and Rohit Joshi. They talked about, where they talk about the spinoriality of reductive groups connected. And okay, sorry. This paper is important because this gives some wild character formula for disconnected Lie groups. Of course, when the connected component is simple, he just considers that. But we have used this the results from this paper extensively, and this is the paper where this is the paper where this concept of Stiefel-Whitney classes of real representations of finite groups there we can generalize them to compact Lie groups also. And this is a paper by Dipendra Prasad and Dinakar Ramakrishnan, who first considered the lifting of orthogonal representations on a very different context. So, okay, thank you.
Thank you so much. To thank the speaker for the excellent talk. There are a few questions for the speaker.
Oh, maybe I will just...
The chat section.
Okay, sorry, I have to.
First question is that I can see from Ajitipal Singh, says that, do you use Hadamard matrices? Do you consider projective representations? Shayan made some comments.
Okay, maybe I will. You just tell me the questions because I will
The
share this.
question is, do you use Hadamard matrices? And the second is, do you consider projective representations?
No, we haven't used the Hadamard matrices, and we really haven't used projective representations. This, um, so one can so you can read the paper by Steven Spallon and Rohit Joshi. There they have like detection methods. So you take a connected reductive Lie group and you just restrict the representation to the diagonal torus, and the spinoriality is detected from the restriction to the torus, and from there they have deduced things. Now in our paper we have just used the fact that I mentioned here, the spinoriality of C2, which is, I will just go back to the slide. Yeah. So it just depends on the, so you take this matrix and it just depends on the multiplicity of the eigenvalue of -1. So somehow playing with it. We haven't really used projective representations.
Okay. There is another question from Sagar. Maybe you can see. It says that are there any literature available of spinoriality in case of UN or SPN?
Yeah. So as I said, the case UN is there in the paper by Rohit Joshi and Steven Spallon. They have like studied it for connected reductive groups. So also I think there is a paper, there is a thesis in the thesis of PhD thesis of Rohit Joshi. He has done extensive calculations for various classical groups, and the thesis is available in Steven Spallon's homepage. You can go and have a look at it. And I can see one more question. I believe spinorial lifting can be studied.
So this was more or less answered, I guess, but you can continue.
Using the second cohomology of the group with, yeah, that I have just mentioned, right?
Yeah. I mean, I asked this before you mentioned this Stephen
okay.
class.
Yeah.
Okay.
Actually, for this paper and in my PhD thesis, I have just studied the spinorial representations of the symmetry groups, the finite group, symmetry group. So there I have extensively used this second cohomology of the groups and the criteria that W2 of pi plus W1 pi cup W1 of pi 0 if and only pi spin.
All right. Thanks.
Okay. Are there further questions for the speaker? If not, let's thank the speaker once again. Thank you so much.
Thank you.
And this marks the end of this symposium on algebra and number theory. Thank you, Professor Jyoti Prakash Shah, for chairing the whole session, and thank you all the speakers. Now we'll take our lunch break and we'll be back at 2 with the symposium on analysis and PD.
So I guess you know the format, like the first invited talk will be 45 minutes, followed by a 15 minutes break.
Yes.
And then the next talks, I guess today, so we will be having three 20 minutes talks.
And 1 10 minutes.
1 10 minutes, that's it.
Okay, right.
That's it, yeah.
Okay, so it's the order is Shayan and then
Prashant.
And then Prashant Goel, and then Vishwesh Kumar, and then Animesh Bhandari, and finally it's Asimani Tamil.
Exactly. Yeah.
Okay, great.
Just stick to the scheduled time so that, yeah.
Yeah, sure.
Yeah, okay. There is some background noise.
Is it from mine?
I don't know. Yeah, now it's
okay now?
Yeah.
Maybe because of my fan.
Yeah, the fan, I guess, but still fine.
No, there's something else. Some cycle.
Okay.
Oh, okay. Then it is not from mine because I'm also
Yeah. Okay, I guess we can start.
So let us start. Yeah, let us start the post-lunch session of Symposium on Analysis and PD, and we have Professor Senthil Rani from IISER Berhampur as the chair. So over to you.
So good afternoon. It's my pleasure to be a part of this virtual Math Fest. And although I was not following it online, I'm still, following it over YouTube. So thank you organizers to create, a very good platform for every one of us to have some informative session. So today's session on analysis and PD, we will start with Dr. Sayan Bakshi from IISER Kolkata. He is a good friend of mine who finished his PhD at IISc. And he's going to talk about sparse domination technique and spherical maximal function. So Shayan, here we go.
Thank you, Rani, for introducing, and thanks to the organizer for introducing this conference. So is my screen visible?
Yes.
Yes.
Yeah. Okay, so I talk about sparse domination and the spherical maximal function. So maybe the second part of this lecture will be based on my joint work with Saurabh Hait, Luz Ronkel, and Sundaram Thangavelu. So in the first part, I just briefly give a survey of the sparse domination technique, and then you go to spherical maximal function. So let's start with this Hardy-Littlewood maximal function. It's a very well-known operator. It is defined like this. So given a function f locally integrable, we can define this maximal function by taking the average over mod f over cube and then taking supremum over all cube which contains x. And it is well known that this maximal function is bounded on LP Rn for 1 less than p less than equal to infinity. And that's what I'm going to prove this by Morse-Equage interpolation theorem. The question is that what happens if we, instead of taking this unweighted space, we put some weight Wx here. Can we characterize all such W such that this weighted inequality is satisfied? And actually the answer is yes, it is possible to characterize all these W such that this weighted estimate holds. And those weights are called AP weights. So a locally integrable function W greater than 0 almost everywhere is called AP weights for 1 less than p less than infinity if WAP is defined like this. So we are taking supremum over all cube Q, and then we are taking average over W, average of W over Q, and average of W to the power 1 minus P prime. P prime is the conjugate of P, and then to the power P minus 1. So if this thing, supremum over this supremum is finite, then we call this W is a AP weight, and this quantity is called the AP norm of W. And Then there is a famous theorem of Markov, which says that if W is in AP for 1 less than P less than infinity, if and only if the Hardy-Littlejohn maximum function satisfies this weighted estimate. So here you can notice that we have put this Wx here and this W is coming from weight. Okay. So in 1993, Berkeley proved that this constant actually is given by this, and this is the best possible constant. So this power you cannot, this power 1 by P minus 1, this one cannot improve. This is the best possible constant. And for example, if you take P is equal to 2, then this becomes 1. So for example, for L2 case, this becomes WA2. Okay, so now the next slide. Now let's come to this very famous Calderon-Zibond operator. So how it is defined? So suppose this delta is the diagonal set in Rn cross Rn, that is x comma x, and T is a bounded linear operator on L2 Rn, and K be a function defined on Rn cross Rn minus this diagonal, such that if you take any function in L2 Rn which is compactly supported, then Tfx is given by this integral for all x which doesn't belong to the support of A. And further, if this K, this kernel, satisfies these three properties, this first condition is called size condition. It says on the modulus of xy is dominated by this thing, 1 by x minus mod x minus y to the power n. And the other two properties are called Hormandus condition. So here we are taking, fixing the first variable x and changing the second variable. Here we take y and then z and take the minus modulus of that. Is satisfying this estimate for if mod x minus y greater than mod 2 y minus 2 mod y minus z, and the similar estimate if we fix this y, the second variable, then this operator is called a Calderon-Zibond operator. This is a very well studied operator, very well known operator in harmonic analysis. And I mean, it is well known that these operators is LP bounded, and then from here this whole Calderon-Zibond theory, so-called Calderon-Zibond theory in harmonic analysis starts. It is also, one can prove, I mean, this is well known for a long time, that this CJ operator satisfies these weighted estimates with this constant depending on W. And this generally proves, one can prove by using soft maximal function, and very well known, maybe part of many graduate textbook. What was not known is that what is the best constant for this inequality, and that was a long-standing open problem for a long time. So it was conjectured that the best possible constant, this is given by this maximum of 1 and 1 by P minus 1. And this was actually one of the famous open problem that was existed earlier in harmonic analysis. So this inequality, it is enough to prove this inequality actually for P is equal to 2, because then there is an extrapolation theorem in harmonic analysis which gives this result for all P. So if you prove this for P is equal to 2, it is sufficient. And that's why this conjecture is also known, was also known as A2 conjecture. Okay, so some important development thing. So Alford-Berling operators, which is a example of Calderon-Zibond operator. It was solved first by Peter Mitchell and Vollberg in 2002. Then for Hilbert transform, it was solved by Peter Mitchell in 2008. Rich transform, again by Peter Mitchell in 2008. And there are other results, I am not going to that. And then finally, for Calderon-Zygmunt operator, it was proved by Thomas Houghton in 2012. So in 2016, Andre Lerner gave a very simple proof of A2 conjecture using this sparse domination technique. And that we will discuss now. So what is the sparse domination technique? So first we define this sparse collection of cubes. So sparse collection of cubes is defined this way: a collection of cubes, this S, so this is the family of cubes in Rn, is said to be eta sparse if for each member of this family there is a set Es which are pairwise disjoint and satisfy this estimate. Now so we have to understand this. So let's take an example. So you take a cube and then you subdivide that cube into 4 parts by just joining the middle point of opposite side. Then you can divide this cube into the 4 parts. And suppose your initial cube is S1 and is a member of the family. So you break S1 in 4 parts and choose one children, one child as your and rename it as S2. The other 3 cube, the union of other 3 cube, you declare this as ES1. Now you come to S2, you again subdivide this in 4 parts, choose one part and take it as a member of the family, and the other 3 part you describe it as ES2. And then you can go in this way, and then what you get a half sparse family, or I think 3 by 4 sparse family. So this is a typical example of sparse collection of cube. And again, so I use this notation. So given in a cube Q and 1 less than P less than infinity, this QP average of F is defined in this way. So we take mod of F and then take the average of over Q and then take the exponent of 1 by P. And if P is equal to 1, I just simply write this as this F of Q. Okay, so there are 2 operators generally used in this context. One is PQ sparse form, which is defined in this way. So here, this is a sparse collection, and this PQ sparse form is this. So we are taking F and G to function, and then this sum here we are taking the SP average of F and SQ over Q average of G, and then measure of S, and then sum over S. So this is one. This is called PQ sparse form, and also there is a sparse operator, which is defined in this way. So here we take the QP norm of F and then characteristic function of Q X, and then sum it over all collection of sparse Q. So these are 2 operators we use. And so what is this, the Lerner's result? So the Lerner's proof that the first that ARS, that is the sparse operator we defined, it satisfies this. So there is a typo, it should be LPW. So this, the LPW norm, the weighted LP norm of ARS of F is dominated by this. So here you can see that this exponent is maximum of 1 by P minus R, which is the best possible constant for Calderon-Zygmunt operator. And this is true for any eta sparse family A. So this constant doesn't depend on the family, this constant C. Okay, so then the Lerner proved that if T is a CZ operator, then for every compactly supported function F, there exists a sparse family A such that TFX is pointwise bounded by this quantity, this sparse operator. And the sparse family S is may depend on this function f, but that doesn't matter because ultimately we have to calculate the LP weighted LP norm, and this constant is independent of the sparse collection. So once we can establish this inequality from this theorem, one can easily prove the A2 conjecture. Okay, so once this sparse domination technique is discovered, people started to trying to apply this technique for various other operators in order to get these sharp weighted estimates. So, and there is a huge number of papers written in this direction. I'm not giving the survey of that because that is impossible to impossible to give. I just give one important operator. This is called a rough singular integral. So suppose suppose omega is a L infinity function on sphere, and suppose this average of omega over sphere is 0. Then you have then the rough singular integral is defined in this way. Here, PV stands for this principal value, which is coming from the distribution theory, and then we have this. So this is the kernel omega y by mod y to the power n. So this is the kernel, and this is the operator. In 2017. Newton, Roncal, and Tapiola proved this estimate. And this estimate so that the weighted L2 norm of this is bounded by this thing. So here you can see the dependence on the weight. Here we are getting the A2 norm of W square. So if you can remember that for this Calderon-Zygmunt operator, this power was 1, but here in this result, the power is 2, and that one can expect that this result may not be sharp. So one can conjecture that maybe the true best possible constant should be this WA2 norm without any power, or power 1. And there is a result in support of this thing that's given by Lerner, where he proved that if you take the composition of this two operator, this M is the maximal function and T omega is this rough singular integral. So if you take the composition of these two operators, then what you get, again, this W, this is A2 norm of W square, but here we are taking composition of two operators, and M already gives, we know that gives the, satisfy the weighted estimate with the norm of WA2. So one can expect that T omega will also give, satisfy the L2 weighted estimates with WA2 with power 1. So that's why one can expect that probably this conjecture is true, but still till now this conjecture is open, and I think one of the main open problem in this area. Again, all the proofs are given here is using this sparse domination technique. Okay, so now we go to this spherical maximal function on Rn. So suppose sigma r is a normalized spherical normalized surface measure on this sphere of radius r. Then this we will consider this following spherical average. So ARF is basically the convolution of f with this spherical measure, which is defined by this. And then one can define this spherical maximal function by taking the modulus of ARF and then taking suprema over r greater than 0, which is this. So in 1976, Stein started this spherical maximal function, and it is bounded on this LPRN. He proved that it is bounded on LPRN for n greater equal to 3 if and only if p is greater than n by n minus 1. For n equal to 2, this problem was open for a long time. And then in 1986, Bourgain solved this case for p is equal to 2, n is equal to 2. The main problem was that here we do not have this. So if you see this p, if n is equal to 2, then you can see that this is p is greater than actually 2, and that creates a problem. Okay. So now we come to the definition of lacunar spherical means, and here you can see that we are taking the supremum over all r greater than 0. For lacunar spherical mean, we take supremum over all 2j's, and j belongs to the integer. It is so in 1979, Calderon proved that this operator is actually bounded on LPRN for 1 less than p less than infinity for n greater equal to 2. So we can see the difference here. For full maximal case, we have boundedness for only for p greater than n by n minus 1. But if we take the lacunary, we have boundedness for all p. And this is because since we are taking over supremum over much smaller set, this quantity is much smaller than the full maximal function. So recently, this Michael Lacey revisited this problem, this spherical maximal function, this lacunary maximal function, and using sparse domination technique. He reproved the Stein's and Calderon and Bourgain's result, and also prove a quantitative weighted estimates for the spherical maximal functions. Then, if we have two functions f and g, and we have the maximal function of f. If we take the inner product of g, is
Yeah, I guess there is some disturbance in the sound.
Yes, I think there is some problem with his network.
Maybe a headphone is some loose connection or something.
Can you hear me?
Your voice was breaking a lot, Cheyenne.
Okay, just a minute.
It's better now a little bit.
Is it?
And is the headphone connected properly? I mean,
yeah, let me see. Is it okay now?
Yeah, I think it's better now.
Okay. Okay, so shall I continue from here, or I go back a little?
Maybe one slide back, and maybe you can present like Control L your PPT as well.
So from this slide, maybe, or maybe I can start from. Maybe I can start from the spherical.
Yeah. I think yes.
Okay. Okay, so we start with again with the spherical maximal function. Suppose we have a surface measure. We have a surface sigma is the surface measure of the sphere of radius r. Then the spherical averages is given by this quantity ARF is actually convolution of f with sigma r. And then one can define the spherical maximal function by taking the modulus of a or f and then taking supremum over r. So this spherical maximal function is was introduced by Elias Stein in 1976, and he proved that this spherical maximal function is bounded on LP Rn for n greater or equal to 3 if and only if p is greater than n by n minus 1. And for n equal to 2, this problem was open for some time. And finally, it was fixed by Bourgain in 1986. Now one can come to the Lyapunov spherical maximal function. Here we are taking supremum over all Lyapunov points 2 to the power z, all the dyadic integers. And was proved in 1979 by Calderon that this Lyapunov maximal function is bounded on LP Rn for all p satisfying 1 less than p less than infinity. So one can see that we get a bigger range of p because this quantity, we are not taking supremum over a full R, so this quantity is much smaller than full maximal function, and that's why we get better result. Michael Lacey has revisited this spherical maximal function problem using this sparse domination technique and actually reproved the result of Stein, Calderon, and Bourgain, and also he give a quantitative weighted estimates for these maximal functions, spherical maximal functions. So here is his theorem. So suppose Ln is a triangle with vertices 1, 0, 0, 1, and n by n plus 1, n by n plus 1. Then this f and g, which are bounded and compactly supported. If you take two functions which are bounded and compactly supported, then there exists a sparse collection which satisfies this inequality. So we are taking the Lyapunov maximal function of f and then take inner product, L2 inner product with g, and this is dominated by constant times the PQ sparse form of fg. And this is that for all 1 by p, 1 by q belongs to this triangle. So this triangle is actually looking like this. So if 1 by p and 1 by q lies in this region, then one has this sparse bound. So the similar analog for full maximal function also proved by Lacey, and in that case the triangle is replaced by some another trapezium. Okay, so we have considered this problem for Heisenberg group. The Heisenberg group is basically Cn cross R, and then we have this group operation. We have ZT composed WS. In the first Cn variable is just an addition, and then the last variable, it is T plus S plus half of imaginary part of this. And this term make this group a non-commutative group, and it is an example of two-step nilpotent group. Okay, so here also one can define a one can consider the surface measure mu r, normally surface measured for z is equal to r. We take this surface z is equal to 0, mod z is equal to r, and suppose our measure is supported on this. The measure is actually surface measure of this. Then one can consider the associated spherical means, spherical maximal function in this way. So take this f, convolve with mu r is s, and then take suprema over all r. So this function was, this spherical maximal function was first considered by Nebo, Amos, and Thangavelu. and then Narayanan Thangavelu and Muller and Seeger. So this is the result of Narayanan and Thangavelu. It says that M is bounded on LPH, and if and only if P is greater than 2n by 2n minus 1, provided this n greater or equal to 2. And this n is equal to 1 is still an open problem in this area. So one can check that this actually given by this Euclidean dimension of Heisenberg group. Okay, so now one can define this Lyapunov spherical beams. So here also we can, instead of taking supremum over all R, we can take the supremum over all dyadic integer. And so it was not considered earlier, and our main objective was to use this Lacy's technique of sparse domination and to prove an LPA boundedness for this maximal Lyapunov maximal function, and also to get some weighted boundedness. So here is the theorem we get. So suppose 1 by P, 1 by Q belongs to this triangle, interior of this triangle, this 0, 1, 1, 0, and n by n plus 1, n by n plus 1, these are same triangle of Lacy. Then we have this estimate that, I mean, for any compactly supported bounded function Fg, we have a sparse family such that this estimate follows. So one can assume that so here actually that one can define this cube. For Heisenberg group, there is an abstract way of defining dyadic cubes by Michael Christ. I mean, that's given by Michael Christ, and so that way one can actually define a sparse family. So one can expect that this triangle is not a very sharp triangle, because here this is same as the Euclidean, it matches with Euclidean dimension, I mean the dimension of Rn, but we should get a better estimate. It should be 2n by 2n plus 1 and 2n by 2n plus 1, something like that. And we do not get this sharp triangle because of technical reason. So so in proving sparse bound, we of course closely follow this Lacy's technique, but of course for Heisenberg group there are some additional challenges, and we have to deal with that. So first, let's review this Lacy's proof and what is the idea. So the Lacy's proof is basically depends on two main ingredients, and the first ingredient is LP proving property of AR. That means he proved this LP-LQ bound for this ARF, which we'll come to in a while. And then there is a continuity property of AR, and that means that we will estimate this AR minus tau y AR, where tau y is the translation operator. And once we get these two estimates, there is a way to get the sparse bound for the spherical maximal function. So here is the LP improving property proved by Stickers and Littman, which says this. So suppose Ln prime is the dual of the triangle we defined earlier. It is 1 by P, 1 by Q, where 1 by P, 1 minus 1 by Q belongs to Ln. So this is the triangle we're talking about. So here it is 0, 0, 1, 1, and n by 1 plus n, 1 by n plus n. So if 1 by R and 1 by S belongs to this triangle, the triangle I have shown, then AR satisfies this estimates. Okay, so this R and this R are different. So this AR is bounded from AR to LS. So just as proof of this estimate. So here we use this something is well known in harmonic analysis called Stein's interpolation theorem. So if you take the Fourier transform of ARF, this is given by this formula, the Bessel function, and by this, and this is bounded for if you take this. Okay, sorry. So the Fourier transform of ARS is given by this, and in order to apply this Stein's interpolation theorem, we have to extend this operator, and we can easily extend this operator analytic to get an analytic family of operator, and this can be obtained by this. So we just instead of this Bessel function, we replace this by generalized Bessel function. This J alpha by 2 minus R1, and then we define this operator as T alpha F. And it is well known that for real part of alpha greater than minus n minus 1 by 2, this function is bounded. So this L2 bounded estimate follows from alpha is equal to minus n minus 1 by 2 by just applying this Plancherel theorem, and it is also bounded from L1 to L infinity, and thus that can be obtained by just observing the kernel. It is very easy to prove this estimate. And once we have that, we have the LP-LQ estimate, which is given here. So this is the LP-LQ estimate using the Stein's interpolation theorem. And then we have this continuity property. Continuity property says that so if you take A1 minus tau by A1, this is bounded for LR to LS, where 1 by R, 1 by S are taken from the same triangle. Then it is bounded by, so this 1 by R, 1 by S is taken from the interior of this triangle. Then A1 minus tau by A1 is bounded from LR to LS with this decay mod y to the power eta, where eta is a number between say less than 1, and so this is the continuity condition. And once we have this continuity condition and the LP improving property, so actually LP improving property gives this continuity property, and once you have this continuity property, one can prove this sparse bound. There is a way Lacey developed. Using that, one can prove the sparse bound for the Lafner spherical maximum function. Okay, so for Heisenberg group, we have this irreducible representation, which is called the Schrodinger representation, and this given by given function L to Rn. This Schrodinger representation is defined by this. Here, this J is is x plus Iy, and J variable, the Y variable act like a translation, and then we have this modulation factor. So one can prove that these are all the irreducible unitary representation of Heisenberg group, infinite dimensional irreducible representation for Heisenberg group. And then using that one can define the Fourier transform for the result. Lambda is from R minus 0, and then by the lambda x.
Sorry to interrupt, Cheyenne. I think your headphone is again creating a little bit of trouble.
It okay now?
Yes, yes. It was only some sort of interruptions, so I think it should be fine now.
Okay, so one can define the Fourier transform like this. So here, as pi lambda is the operator on L2 Rn, this is also a operator on L2 Rn, f at lambda. And then one can, the spherical maximal function that we have defined earlier, one can check that the Fourier transform of ARF lambda is given by this multiplier, where mu r lambda is an operator, and that is given in terms of the spectral that's actually spectral multiplier associated with the heartbeat operator. So heartbeat operator is given by this minus Laplacian plus mod lambda mod x lambda square mod x square. This is the usual heartbeat operator we know. Then one can write the spectral decomposition like this. Here 2k plus n mod lambda is the eigenvalue of h, are the eigenvalues of h lambda, and then so this mu r hat lambda is given by so in order to define this mu hat at lambda, one has to define certain special function called this Legard function, which is defined by this. So I'm not defining this, but these are very standard in harmonic analysis out of the theory of special function. So once you have these functions, one can define mu lambda in this way. So here, instead of this 2k plus n lambda, we replace this by this psi alpha k. And this is called the Hermite multiplier. And then one can prove that if real part of beta is greater than, so one can then similarly extend this operator as an analytic family of operator in this way. So here instead of psi k, I take beta plus n minus 1. And then one can check that if beta greater than minus n plus half, then this t tilde beta, the analytic family that we defined, is actually on. The problem is to prove the other part, that is when we want to prove that for when real part of beta is greater than 0. Then this t beta is given by this formula, integral formula, and it doesn't seem to give any L1, L infinity boundedness for whatever large beta we can take, because there is some problem in this t variable. So in order to overcome this, you have to find a new, create a new family of operators in this way. So we take this k beta t by this, and then we take this function f and then convolution with this k beta on this t variable, and this then take this integral formula, and that is for beta. So you can say that here we are taking, instead of t tilde beta, we are taking convol f with this k beta. So that this multiplier and this of, then we get this multiplier, and this is also for beta. So this is for beta greater than minus n minus 1 by 2. This L2 bounded that one can prove by some work. And then we also have this this estimate, this L infinity L1 partial estimate for this family. And once we have this two estimate, one can, using analytic interpolation, one can get this LPLQ estimate by this. So this is the result. If you take A1, so you take R is equal to 1, it is bounded from LP to LQ, whenever 1 by P and 1 by Q lies in this triangle. And once you get the A1, one can also get for AR using this violation. And then one can prove this using that LP improving estimate, one can prove the continuity property by this. So first one have to prove that this A1 minus tau, if you take L2 to L2, then this is bounded, it is bounded by C mod Y. And this gives this continuity property, that's 1 by P, 1 by Q. If it lies inside this triangle, then we have this estimate. The A1 minus A1 tau Y LPLQ estimate is bounded by C mod Y to the power eta. And this proof is not as easy as basis case. One has to do some work and one has to use the structure of HN. So once I have this LP improving property and this continuity property, one can then try to use the basis proof, and one has to somehow develop this develop this idea for homogeneous type space, and then one can prove the sparse bound for this surface maximal function. And once this sparse bound, we get the sparse bound, we can prove the, it's a routine method to prove the unweighted norm inequality and the weighted estimates for Laplace.
Thank you, Shayan. That was like wonderful collection of beautiful results. And it was good to see all in one, and the flow was very nice. So now let me see if we have any questions for the speaker.
So anyone can unmute and ask questions.
Okay, so if there are no questions, then we'll thank we'll thank Shayan for.
Just a minute.
Yes, I'm sorry.
Yeah. Do you have uncertainty principal type inequalities or results?
For that, no, I don't. I haven't seen any result. Uncertainty principle and weighted inequality? No, I don't see any results.
Okay, all right. Thank you.
Thank you, Professor, for your question.
Very good talk. Very good. Very good.
Thank you.
Okay. Yeah, so let's thank Shayan, and let's hope there is no more glitches of sound from the next talk onwards. So we were sorry for some sort of sound glitches. So we'll take a break for 10 minutes, and then we will start continuing by 3 p.m. Is Prashant Goel ready? May I know if Prashant Goel is online?
Yes, ma'am, ready.
Oh,
Am I
okay.
audible?
Yes. So I hope there's no other background noise or, like the audio is proper for this talk.
Hopefully so, ma'am.
Yes.
Yeah, Prashant Goel, you can share your screen, maybe.
Sure, sure. It is visible, right?
Yes, it is visible. Well, there are 3 more minutes, but shall we start or?
No, let's wait for the time.
Okay, sure.
Some people may join for this talk.
Sure, sure.
Yeah, we can start now.
Okay. So the next talk is going to be by Prashant Goel from IIT Delhi on global attractor for weakly damped forced MKTV equation in low regularity spaces. So let me hand it over to Prashant Goel.
Thank you so much, ma'am. Good afternoon to all. And I would like to thank the organizer for giving me this opportunity. So the title for today's talk is Global Attractor for Weakly Damped Forced MKTV Equation in Low Regularity Spaces. So in this talk, first of all, I will describe what is a global attractor briefly. Then we introduce the problem and the MKD equation as well as the known results with some notation, and then I give a brief summary about all proofs. All right, let's start with the definition of semi-group. A collection of operator ST for t greater than 0, greater than equals to 0 is said to be semi-group if it maps the phase space H to itself. So basically, for our convenience, the semi-group we consider is the generated. It is generated by the solutions of ODEs and PDEs. So basically, this is the definition of trajectories. That is, if you consider a point U naught, then the orbit or trajectory starting at U naught is defined by this. The next definition is for every bounded set V, there exists a T such that this set is relatively compact in H. In other words, the operator STR relatively compact for T large. Now we define the omega limit set of U naught. That is, if you consider a point in the phase space H, or if we consider a set A in H, that is a subset of H, then the omega limit set point of this point U naught or the set A is defined as this. Now, we say that X contained in H is positively invariant if it satisfies this property. Okay. So this is about the absorbing set. Let B be a subset of H and U an open set containing B. We say that B is absorbing in U if the orbit of any bounded set of U enters in B. That means after a certain point of time, this set is actually contained in B. Now let's come to the definition of attractor, which depends on the definitions which we have done. An attractor is a set A contained in H that enjoys the following properties. A is an invariant set, that is ST of A is equals to A. A possesses an open neighborhood U such that every U naught belongs to U. ST of U naught converges to A as T tends to infinity. Alright. So what is the global attractor? Global attractor is something like a set A contained in H for the semigroup ST. Okay. If A is a compact attractor that attracts the bounded sets of H. Now let's see the main theorem which we are going to use from this theory in our problem. That is, let H be a Banach space. For T large, we divide the semigroup ST into two operators, that is L1T plus L2T, where the operator L1 are uniformly compact for T large and L2 is continuous mapping from H into itself, such that every bounded set C contained in H, if we define this property, it tends to 0. We also assume that there exists an open set U and a bounded set B of U such that B is absorbing in U. Then the omega limit set B is actually maximal compact operator, that is global attractor, which attracts the bounded sets in B. Alright, we consider the modified KdV equation, which is defined as delta TU plus del x cube U plus minus 2 del x U cube plus gamma U is equals to F. So this is MKdV equation with damping and forcing term, where damping term is gamma and damping constant is gamma and forcing term is F, where F is coming from H1. Here we are assuming T is greater than 0 and X is coming from one-dimensional torus. This is our initial data, which is coming from homogeneous Sobolev spaces. Okay, Mura in his theory have given a Mura transformation which actually converts the solutions of MKdV equation into KdV equation, and hence we can, from inverse transformation, we can say that if we know the solution of KdV, we can get the properties of solutions of MKdV equation. That's why KdV equation is extensively studied, although there is not much studies about MKdV equation. Now what's the issue? The issue comes when we add the damping and forcing term in the MKdV equation. when we add the damping and forcing term in KdV equation, the actual Mura transformation does not work here. That's why we have to consider this problem separately. Yeah. For global solution of KdV equation, the I team, mainly known as CKSQT in 2003, has shown that KdV equation has global solution for s greater than equals to half using Mira transformation actually. Now, these three authors in 2009 use the energy method for ux and uxx, that is first energy and second energy method, to show that there exists a global attractor in H2 space. From the articles of Gidalgia, we can show that directly that there exists a global attractor for s greater than equals to 1. 2 years back, I have shown that there exists a global attractor for s greater than 11 by 12. That is, there exists a global attractor of KdV equation below energy space. Now, this problem is actually about when your s lies between 9 by 10 to 1. If you consider initial data u0 in Hs, then St is, if you consider semi-group solution of KdV equation, then there exists the operators L1 and L2, which satisfies the following properties with this constant depending on these terms. All right. So if we show this theorem, from the theorem of global attractor, we can show that there exists a global attractor for s greater than 9 by 10, because again we are actually splitting the semi-group into two operators having both the properties as given in theorem 9. Let's see the notations which have been used in this article. So basically C and C are various time independent constant, and A plus A minus means A plus epsilon and A minus epsilon for a very small epsilon greater than 0. A less than equivalent to B means A is less than equals to CB, where C is some positive constant, and A equivalent to B means A is less than equivalent to B, and B is greater than B is actually less than equivalent to A. Sorry for that mistake. Okay. So now we define the space XSP, mainly known as Borgen space, as this quantity. So this is basically L2 norm with some derivatives. Basically derivative in X variable S and in T variable B. So to ensure the continuity of local well-posedness, we are restricting ourselves to some smaller subspaces of this. Now, let's come to the brief summary. So to go for the KdV equation, the first thing we have to do is renormalize the equation, because there is a big difference between KdV and modified KdV. That is, in KdV equation, the resonant term have integral 0, that is, it has measure 0, but for KdV equation, the measure is non-zero. That's why we have to consider the non-resonant term separately, and to do that, we have to renormalize the equation again. After renormalizing, to go for the priori estimate, we need to rescale the equation. Then we define the operator I, which is a Fourier multiplier, with the help of Fourier multiplier, and we use the trilinear estimate, which is nothing but the estimate for the non-linearity of KdV equation. So by using first four quantities, we give the local well-posedness result, and with the help of local well-posedness and bilinear estimate, we give the modified energy, and with all these three combinations, we can get a priori estimate, and hence we can easily prove the theorem there. All right, so this is our actually renormalized modified KdV equation. Okay, so basically we are removing this term, which is the resonant part, and this is our rescaled version of this equation. Now we consider a smooth function phi with this definition, and we define a Fourier multiplier M with this definition. All right. So with the help of this Fourier multiplier, we define the I operator as this one. Now, the trilinear estimate, that is the non-linearity of the equation, which is of order 3, is really, really important, and it is quite different from KdV equation, as I said, because of the resonant term. So we have actually two quantities, that is, one is resonant quantity and another one is non-resonant quantity, and we have to consider both things separately. So if we consider the Fourier transform of the non-linear term, we can define this as this operator, and for this operator in ys space we define this we have proven this trilinear estimate. Now, so the main difference from the earlier proof and this one is this bilinear Stikka's estimate. So for n1 and n2 belonging to 2 to power z with n1 strictly greater than n2 and lambda greater than equals to 1, we define the following. We have proved the following bilinear Stikka's estimate, which is actually not a general version of Stikka's estimate, a little bit weaker version, but still quite useful for us. So we can also define a kind of corollary for the bilinear Stikka's estimate, which is very useful in the bound of multilinear bounds functionals. All right. So this is the result for our local well-posedness result. Local well-posedness in terms of y1 and h1. All right. So this is the definition of multilinear function. Okay. It is just a function. We say that a function is symmetric if I operate any element from the symmetric group of an element, it does not affect the my multilinear. Okay. And hence we can also define the symmetrization of this multilinear variable. All right. Similarly, we define the multilinear functional as defined as this one. So if we make the same copies of this, we just write it at like this. All right. So now let's define the modified energy. So we have already know that there are conservation laws for modified KdV equation. In fact, there are infinitely many conservation laws which have already been proven. So we just consider the E1 and apply the operator I with this. Okay, so this is our first modified energy, which is actually used in earlier proof also. Now, if we use the Plancherel's theorem and for a transformation, we can see that we can write it in the form of multilinear functional, which is this one. Okay, where mi is equal mi represents m of ki. Now, consider this operator as your second modified energy, and if we took the derivative of this second modified energy, we get these quantities. So basically, to solve this problem, all we have to do is find a suitable bound for these operators. Now here the things which are unknown for us is M4 and M6. Those multilinear are actually defined as this one. We consider M4 as this one and M6 as this one. So this comes with the condition which we have, which is given actually in the modified energies. All right. So this is the bound for multilinear M4 and this is the bound for multilinear M6. Okay. So basically main growth we are having in the form of M6 only. So if we have M4 bound and M6 bound, we can also get the bound for multilinear functional also. Okay. So for delta 4, we don't have a decay, but for delta 6, we have a decay of order 1. Right. So for our priori estimate, this is an important lemma which we have proven. So basically, this result is in the form of H1. And it also has a multilinear bound, which we have already shown. It has a decay of order 1, sorry. All right. So this is the priori estimate, which has been proven using the previous lemma. So these two conditions we have assumed. And if we assume those two conditions, we can show that we have following bounds on these two in the form of L2 and H1. Again, we can just rescale this proposition because after rescaling, doing the proof is quite easy. So that's why we have rescaled this proposition. And if we rescale this proposition, our bounds actually change into this form. Okay. So now let's see how we have proven the theorem. So first of all, because we have not chosen any cutoff for the operator I, so first thing we have to do is we have to choose a suitable cutoff and a time. If we have both of them, we can directly use the priori estimate. After using the priori estimate, we will reach to a bound. We iterate it one time, and if we iterate it, we again have to choose the cutoff and the time. After choosing that, we can again use the priori estimate, and if we use the priori estimate, we can directly get back to the theorem. Alright. So now I'm just giving a brief about what is the cutoff and the time we have chosen. So this is the time t1 which we have chosen in the form of exponential of 2 gamma t1. Alright. So this is the choice of t1 and this is the choice of n. So for these two choices, we have shown that the our proposition, that is a priori estimate is satisfied. So basically these bounds we got directly if we implement the conditions of priori estimate. Now, what is the difference between the two proof which I have done till now? So basically first proof was for s greater than 11 by 12 and second one is 9 by 10. Although in the sense of bound there is not big difference, but in the sense of proof there is lots of differences. So first thing is modified energy of first generation we have used in our first proof, and in the second proof we have used modified energy of second generation. That simply means that if we go beyond third to modified energy, that is third generation of modified energy, the system will get more complicated, although it is very unlikely to get a so much better bound. That is, our main aim is to reach up to 1 by 2, but it seems difficult even if we go to level 3 with lots of complications. Second thing, the difference is in the first proof we have used the resonant term, that is the term which does not have measure 0 to find the decay, but in this proof we have not used any resonant term. In fact, we cannot use it. The third difference is in the first proof we have not used any kind of bilinear Stikaz estimate, and in this proof we have used the bilinear Stikaz estimate. Thank you so much for your time.
Thank you, Prashant Goel. It was a nice talk. Let's see if we have any questions from the audience. Okay. Let me check if there's any chat messages. Okay, if there's no more questions, let's thank the speaker again, and let's come back for the next session after 10 minutes at 3:30 p.m.
Thank you.
Thank you.
Maybe we can ask Vishwesh Kumar to start the presentation now, or?
Yes, I can. Maybe I can share the slide. Okay. Screen. Senthil, can you see my screen now?
Yes, we can.
And my voice is audible? It's
Yes.
not glitch? Okay.
No, at present there's no glitch or any background noise. Thank you.
Okay, thank you. Sometimes it happens actually with Zoom and net connection. It's not in our control.
True, very true.
Okay, let me set it up.
Maybe we can start now.
Yeah, sure. So the next talk is going to be by Vishwesh Kumar from Ghent University, Belgium, on the topic LP-LQ boundedness of Fourier multipliers associated with an harmonic oscillator. So, Vishwesh,
Okay.
please.
Yeah, thank you, Senthil, for your kind introduction. And I would like to thank organizer for this wonderful event. And it's nice to see, especially Professor Thangavalu, because he's expert of this topic. And I'm very happy that he's here. So today I will talk about LP-LQ boundedness of Fourier multiplier associated with anharmonic oscillator. And thanks to Cyan for setting the platform for LP-LQ boundedness of Fourier multiplier, especially for spherical maximal functions, which is also a Fourier multiplier. So let us start with the definition of the Fourier multiplier. So an operator on suitable space is called a Fourier multiplier with symbol sigma. If you apply the Fourier transform on the image of the function, it gives to a multiplication by a complex number to a Fourier transform of that function, where hat represent the usual Euclidean Fourier transform. And in this talk, we also discuss LP-LQ boundedness of a spectral multiplier also. So let us define a spectral multiplier. So first so yesterday we had a talk about on a spectral multiplier, and so we take a non-negative self-adjoint operator on L2X. So X is a sigma finite major space with a spectrum containing inside 0 to infinity. Then for any function from 0 to infinity to C. Using the spectral theorem, we can define the spectral multiplier, because for the spectral theorem, we decompose L as the integration over the spectral and then lambda and d E lambda, where E lambda are the spectral projections. And then using the functional calculus, we can define this operator P of L. So E lambda are the operator valued projection valued measures. So the main problem in harmonic analysis to study boundedness of Fourier multiplier or spectral multiplier, that means to find the sufficient conditions on the symbols. So two famous condition on the symbols is one is Hormender type condition, and second to study LP boundedness, each second is Marcinkiewicz type condition. So these type of condition has been studied for a long time. It's a good tradition, and also they are very hard problems. So, and many people work in this setting. So few name it started with Hormender in 1960, and for a Euclidean case, LP boundedness, then Stein, Taylor, Pepperman, and Anchor for the non-Euclidean setting for symmetric spaces. Then few name Colling, Meda, Mosheri, and of course Sayan and Thangavelu said proved this LP boundedness for pseudo multiplier, which is kind of more general version of more general than free multiplier. And my advisor here, Ruzhansky, also have many results in this setting for compactly group, for nilpotent, for gradally groups, and other setting. So despite of having LP boundedness, so many results in the LP LQ boundedness somehow is not studied much in the past. So although in 1960 in the same paper which appeared in Acta Math, it's a seminal paper in this direction. So Hormender gave this condition on the symbol. If symbol satisfy this condition, then A can be extended from LP to LQ, and this theorem is recently extended to many different settings by Ruzhansky in collaborator. For example, Akiljano and Nursultano and Ruzhansky extended it to compact homogeneous spaces, and more generally, and then Majid they extended to compact quantum groups, which we study in one of the plenary talk, compact by Sotanu Roy, and then very recently they extended they proved it for locally compact groups. So and I extended this with Ruzhansky for compact hypergroups as well. So the main technique here to extend for locally compact groups was to prove fundamental algebra techniques. So all these terms we heard in last two talk, like yesterday or day before yesterday by Ved Gupta. So now let us get back to our main object, unharmonic oscillator. So unharmonic oscillator is given by this operator where delta is Laplace Bell trinomial operator. So usually unharmonic oscillators are the is a family of operators, but this operator is a prototype, and we call it unharmonic oscillator. And unharmonic oscillator is usually called its red part, and this can be thought as a generalization of harmonic oscillator. But we consider this plus one because this operator is studied by very recently by my collaborator Jaco and Ruzhansky and Delgado, and they study a spectral property of this. So we consider this operator due to that. So this harmonic oscillator is quite well known, and many people work on that. It's very well known. Professor Thangavelu is expert in this, and so I would like to make some more comment about this. So unharmonic oscillator can be thought of as a pseudo differential operator. Pseudo differential operator is kind of a Fourier multiplier where the symbol not depend only on psi, but also depend upon x. So this can be thought of as a well quantization. I will not explain it too much because I don't have time, but it's just to give a connection to different field. And this unharmonic oscillator also occur as a symbol of sub-Laplacian on Heisenberg group. We just heard by Baxi, and So Heisenberg group is a two-step nilpotently groups. This also occurs this also appear as a symbol of in the case of three-step nilpotently group, which are the Engel groups and Cartan groups, and all these connection can be found in this paper. So, okay, so it is well known that the eigenvalue problem for the harmonic oscillator is completely settled, but despite of many effort, this eigenvalue problem for the anharmonic oscillator is still not known. But what we know that this anharmonic oscillator is a compact operator on L2M. So spectral theorem, we can get a eigenfunction consisting of the basis which will be basis of L2Rn, and we do know the corresponding eigenvalue by lambda j, and we have the eigenvalue counting formula which we will use later. So this is the estimate, asymptotic estimate for the eigenvalue counting formula for anharmonic oscillator, which is given by this formula, and this can be derived using something called Weil harmonic calculus, and you can find this in paper of Toft, and this anharmonic oscillator and this asymptotic formula can be derived in some good techniques by this book. Okay, so now we will explain some Fourier analysis using this. So we have eigenfunctions. So using the eigenfunction, we can define the Fourier transform. So Fourier transform is a bijective homomorphism from the space C infinity. C infinity is defined as the intersection of all domain of the all iterative power of the anharmonic oscillator using this. So here we replace in a usual setting we have exponential. So here we replace the eigenfunctions of the anharmonic oscillator is the usual setting when we have eigenfunction expansion. So we define like this, and then to have we need some estimate. We need some inequality like Hausdorff-Young inequality and other things. For that we need some weighted space on the dual space. That is, in this case, dual space is on S or iron in N. So on natural number we have weighted LP spaces. So let's define the weighted LP spaces like this. Is a usual, but we need here weight condition. Okay, extra weight because we don't know, and these L infinity norms are bounded here, so we don't have any problem with that. So having these spaces, so we define the Hausdorff-Young inequality. So which say the Fourier transform is bounded. Okay, by if you take the Fourier transform LP function. So now the analysis I presented here can be has been developed in more general setting by Rozhansky and Tukmagambatov in these two papers, and this is the recent paper we got result for more general version of this what I will present here, and with some application to PD as well. So now the main inequality in this the technique we adopted is the technique of Hormender itself. So the first inequality we prove here is a Pally type inequality. So the classical inequality, Pally type inequality, was proved by Torres for little Pally, and then Hormender proved it for Rn. So what it says if you have a positive function phi on Rn, it satisfies this condition. So you get so this is LP weighted LP bound. You get this one between P lie between 1 and 2. Now this inequality was extended by Rozhansky and collaborator and by Johan, and this inequality is kind of very useful for a different purpose, not only for LP-LQ bounded Fourier multiplier, but also to obtain Hardy-Dayton inequality for groups. And especially in this paper of Johan, he proved sharp Hardy-Dayton inequality and also derived many interesting things in contrast of quantum groups. So this is the version of Pally inequality for anharmonic oscillator. So if you take a positive sequence and it satisfies this property, so we have this estimate, and all the result which I will present here can be found in this paper. And this is kind of a part of that paper. We have more things in that paper. So the second inequality is the Hausdorff-Young inequality, and how we get this. So we have Hausdorff-Young So we have Hofstadter inequality, and then we have Parry inequality, and we do interpolation between these two, and we get Hofstadter Parry inequality. So for example, if you see if B equal to P prime, then you get Hofstadter inequality. If B is equal to P, you get Parry inequality in this setting. So now we apply this inequality to get LP-LQ boundedness of Fourier multiplier. This is the main tool in this setting. So we define the Fourier multiplier in this setting also. Instead of Euclidean Fourier transform, we have now AKL Fourier transform using the eigenfunctions of anharmonic oscillator, and then we get this is our main result here, that between this range P and Q, between this range we have if the symbol of Fourier multiplier satisfy this property, then A can be extended from LP to LQ. And this is the main result. Using that, we prove a spectral multiplier theorem. So it says if P lies between this range, then you consider if decreasing function from 1 to infinity. I consider from 1 to infinity because the spectrum of anharmonic oscillator lie from 1 to infinity. So that's why. And such that it once at infinity, then the LP-LQ norm of this spectral multiplier of anharmonic oscillator is dominated by this quantity. So proof is quite simple. I will explain the proof. So it is easy to observe that this spectral multiplier is a Fourier multiplier with the symbol phi lambda j, and so we apply the previous theorem to get this estimate. Now it's matter to estimate this inside term. So what we do, we obtain some for eigenfunctions using some known results for a more general setting in Weil harmonic calculus, and then we plug up this inside the last inequality, and then we get this. Now to estimate this term, we use Weil eigenvalue counting formula, and that's what we done. So now as a corollary of spectral multiplier theorem, we get the boundedness of negative power of anharmonic oscillator. So it's bounded from LP to LQ if M is greater than this quantity. In particular, it's bounded on L2. So now as the applications of this, we get Sobolev type inequality by choosing Sobolev type estimate by choosing the function P. In particular, if you choose 1 upon U A minus B, then apply this on the spectral multiplier theorem. So we get here A power B minus A F is less or equal to some constant which can be which will be finite, you can prove, and then we get as a consequence of this, we get this inequality, normal inequality, and if B is equal to 0, so this is kind of Sobolev type estimate. Okay, Sobolev space related with anharmonic oscillator, of course. And now we also derive some time asymptote for solution of the heat equation. So first one, we consider the heat equation related with anharmonic oscillator. So instead of Laplacian, we have here anharmonic oscillator. So this is the solution. It can be checked. This is the solution of this initial value problem. So now by choosing this function phi as t power exponential power minus tu, we get this estimate using the spectral multiplier theorem. And now using the simple calculation, we can calculate the supremum over all this, and the supremum turns out to be this quantity, and then plug up these full things here, and you get LQ bound of this is bounded by this number. So we get a time asymptote of the solution of the heat equation in this setting. And that's all. I think I am not over the time. Thanks for your attention.
Oh, thank you for that quite interesting talk. Let's see if we have any questions from the audience.
Actually, I have a question. So you have got some. Yeah.
I can't hear you properly.
Can you hear me?
No, I can't hear you properly.
Hello.
Sorry.
Can you hear me now?
Yes, please.
So you in the last slide you got some heat kernel heat estimate, right?
Yes, it's a kind of time institute for the solution of the heat equation. Yes.
Yeah. So do you have any kind of heat kernel estimate? I mean, the kernel, the alien heat estimate, Gaussian type estimate for kernel?
No. I don't have. Yeah, I don't have.
What are your main techniques?
Techniques are here actually developed by Hormender, but later we for a spectral multiplier theorem we derived this using Weil-Hormender calculus, which I did some little bit cheating here because I don't explain anything about Weil-Hormender calculus because I don't have here time. So I just hide all these things because I don't have time to explain those things. This is the things which is area of his own study. So so I did little bit cheating and present you direct the result. It's not behind the recipe, what is the behind going on. So it looks simple, but it uses lots of various known results which are developed in very general settings, especially for spectral multiplier theorem. Up to Fourier multiplier is quite easy, standard techniques which are developed by Hormender.
Any other questions? Okay, so if there's no other question, we'll thank the speaker again, Vishwesh. Thank you.
Thank you. Okay, so may I take 1 minute?
Yes, sure.
So from 18 August to 20 August, we will organize a conference on non-commutative harmonic analysis. So here I see many people on that topic, so you can connect, and we have very nice speakers there, including Professor Thangavalu. So it's nice. So you can check our website, Analysis and PD. So maybe you see you there.
Sure.
If possible, could you please put the link in the chat?
Yes, I will. I'll put it right now. Okay. Yeah. Thank you. Thank you. So I will stop sharing now.
Yeah, sure. So we'll take a break again, and we'll meet at 4. Do we have Animesh here? I do not see Animesh in the list.
Yes.
Yeah. So
I can see though the next participant, I think Asimani Tamiragan is there. Yeah. But what do we do now?
yeah, let me check if he has sent any email.
Okay, sure.
Yeah, I guess we should start with the next talk, and then if Animesh comes, we'll have the talk afterwards.
Yeah, I am here. Yeah.
Sure. Okay, so
Okay.
Is this Animesh? I mean, or the person who's under the name of Anup is Animesh, right?
No, ma'am. Actually, I am using my brother's laptop. That's why.
Oh, I see. Okay. Sure.
Perfect.
Sure. Yeah, great.
Now my screen is visible.
Yes, your screen is visible, but maybe you can share these slides or no, just to check if the presentation is on.
Share screen.
Yes, it's visible. Yeah.
Now, is it visible?
Wonderful. Yes, thank you. Let's wait for a minute and then we will start the session. Okay, so let's continue the session with the next talk by Animesh Bhandari from ISI Bangalore, who's going to talk on the topic on openness of K-fusion frames. So Animesh, please continue.
Yeah. Very good afternoon. First of all, many thanks to the organizers for giving me the opportunity to present my talk, present my work here. My research area is frame theory. Now the question is why people will study frames. Originally, frame theory was introduced on a separable Hilbert space, and if there is a separable Hilbert space, then it guarantees the existence of orthonormal basis. And using orthonormal basis, the Hilbert space elements F can be explicitly represented by means of respective Fourier coefficients, like F is equal to summation inner product F EI, where EIs are orthonormal basis. Now, in practical circumstances, when Hilbert space elements F are characterized as signals, and when a signal is transmitted through a noisy channel, if due to some technical reason, any one of the frame coefficient, that is Fourier coefficient in our product is removed, then at the receiver end, the receiver cannot reconstruct the original signal. Due to this fact, an overcomplete system was required. Such an overcomplete system is called frame. This overcomplete system is more flexible because of basis elements. The basis elements are linearly independent, but frame elements need not be. Title of my presentation is on openness of K-fusion frames. There are several generalizations of frames, like fusion frame, K-frame, and we have worked on intertwinedness of K-frame and fusion frame. We named it as K-fusion frames. My total presentation is divided into 5 sections. After discussing preliminaries and background results related to frame theory, then we will discuss K-fusion frames, properties of weaving K-fusion frames, and then we will discuss some of the applications. And to work work on K-fusion frames, we have gone through so many research articles, papers, books. Here we are acknowledging some of them in the reference section. This is the brief history of frame theory. The concept of frame theory came in the year 1946 by Gabor by introducing the construction formula. After a couple of years, in the year 1952, Griffin and Shepard, they first introduced Hilbert space frame. And after several decades, in the year 1986, Davichis and Grossman and Mayer, they first realized the importance of frames in different applications like signal processing, image processing, data processing, and many more. This is the mathematical definition of frame. Suppose we have a sequence xi in a separable Hilbert space H, then it is said to be a frame for H if there are two positive constants A, B, such that every Hilbert space element X, the given sequence satisfying this inequality, then the sequence is said to be frame for H. Here A and B are called frame bounds, where A is called lower frame bound, B is called upper frame bound. Frame bounds are not unique, so supremum of all such lower frame bound is called optimal lower frame bound, and infimum of all such upper frame bound is called optimal upper frame bound. Now, depending upon the nature of frame bounds, we will get specific types of frames. For example, when A is equal to B, that is lower frame bound is equal to upper frame bound, the given frame is called tight frame. In addition, when A is equal to B equal to 1, then the sequence, the given frame, satisfying the Parseval identity, and that's why the given frame is called Parseval frame. And whenever removal of a single frame element seizes the frame condition, this frame conditions, then the given frame is called exact frame. And whenever a sequence satisfying this right-hand inequality, then it is called the Bessel sequence. And in frame theory literature, there are so many generalizations. One such generalization is K-frame. This is the mathematical definition of K-frame. Suppose we have a bounded linear operator K. Then if a given sequence xi satisfying this inequality, then it is called the k-frame for h. Now, if we replace k by the idempotent operator, then the given frame becomes our classical frame. These are the examples of sequences which are framed, which are not framed. If En is orthonormal basis in L to N, then the first example shows that it is a frame for L2 with frame bounds 1 and 2, whereas second example is a Parseval frame for L2. Since it is a Parseval frame, so optimal frame bound is 1, that is optimal lower frame bound and upper frame bound is 1. Whereas the third example shows that it is not a frame for L2 because for this sequence, we will never get any upper bound, that is right-hand inequality of frame condition. So it is not a frame for L2. And throughout this work, we have used several times Moore-Penrose pseudo-inverse. This lemma shows the properties of Moore-Penrose pseudo-inverse. What it says, suppose we have two separable Hilbert space H and K, and if we have a closed range operator T from H to K, then the Moore-Penrose pseudo-inverse is denoted by T dab from range of 2 to H is satisfying these three conditions, these three properties. Also, for a given frame, it is a natural question, it is a natural interest that what are the characteristics, what are the properties for a frame operator for a given frame. To define a frame operator, first we will define the preframe operator or synthesis operator. The preframe operator P from L2 to H is defined by this identity, and the adjoint of the preframe operator is called analysis operator, defined by this identity, and the composition of preframe operator and analysis operator gives us the frame operator. One important observation that the frame operator is always bounded, positive, and invertible. And using the invertibility property, we can reconstruct the Hilbert space elements by this expression, where the collection S inverse Xi is called canonical dual. Here we must say that duality is a very important thing in frame theory. This is the mathematical definition of general dual frame. If we have a frame Xi and if there is a sequence Yi, then this Yi is said to be dual of Xi if for every X in H, every X satisfying this identity, then Yi is said to be dual of Xi. This is definition of K-fusion frame. If K is a bounded linear operator and if we have a collection of closed subspaces with a collection of positive weights Vi, then the weighted collection Wi Vi is said to be K-fusion frame for H if there are constants, positive constants A, B, such that every Hilbert space elements F satisfying this inequality, then the given weighted collection is called K-fusion frame. Here, PWI is orthogonal projection on closed subspace Wi. And here, if we replace K by the identity operator, then the given K-fusion frame gives us the definition of fusion frame. So, K-fusion frame is also generalization of fusion frame. And this is the mathematical definition of weaving K-fusion frame. Here, one may ask a question, what are the importance of defining ovenness of frames? Now let us consider a scenario. Suppose we have a collection of sensors, say X1, X2, Xn, and these sensors produce some result. Now, if some technical reason, any one of the sensors, say Xi, is removed, then the resultant may contain some error. So, to resolve this problem, if we consider another set of sensors, say Y1, Y2, Yn, which is having the same job as Xi is, then in place of Xi, Yi can replace and removal of Xi, Yi will serve the Xi's job. Such an intertwinedness between two sets of sensors or in general between two frames is called oven frame. This is mathematical definition of weaving K-fusion frame. Suppose we have a bounded linear operator K, and if we have two K fusion frames, Wi, Wi, Vi, Vi, then it is said to be a K fusion, open K fusion frame or weaving K fusion frame if for every sigma index set subset of I such that these two weighted collection satisfying this inequality. That is, for every sigma corresponding weaving satisfying the K fusion frame condition. Then these two given K fusion frame is called weaving K fusion frames. These two theorems shows the properties, some properties of weaving K fusion frames in different spaces. Here, we wanted to study the properties of one K fusion frame to another K fusion frame by defining a new bounded linear operator. First theorem says that if we have a bounded linear operator K in H, and if we have two K fusion frames Wi, Wi, Vi, Vi in H1, and if we have operator, closed range operator T from H1 to H2, then this weighted collection, image of this two weighted collection under this closed range operator T forms a K fusion frame. Here K is special operator Tk T star under these two conditions. And this theorem shows that this theorem is basically converse of this theorem. What it says, suppose we have two weighted collections, and if we have a 1-1 closed range operator T, and if we assume that for a given bounded linear operator K in L2, H2, LH2, such that the image of these two weighted collection under this 1-1 closed range operator are weaving K fusion frames for range of T, then these two frames, the original weighted collections are also weaving K fusion frames. Here K is T dab KT with universal bounds. Here we will study the properties of weaving K fusion frames. What it says, suppose if we have a bounded linear operator K and consider two weighted collection of closed surfaces, and if we assume that these two weighted collections are weaving K fusion frames, then these are also fusion frames for H, and if range of K is closed, then these two weighted collections are weaving fusion frames whenever they form weaving K fusion frames for range of K. So in second condition, from K fusion frame, weaving K fusion frame, we will get weaving fusion frame. Here we study the properties of weaving K fusion frames in the context of perturbation theory and in presence of eraser. The first theorem says that if we have two bounded linear operators T and K in H, in addition, let us assume that K has closed range, and if we give the perturbation in between adjoint of T and adjoint of K by this expression, then the two weighted collections are weaving T fusion frame if they are weaving K fusion frame for range of T. And this theorem says that if we have weaving K fusion frames with respect to a bounded linear operator K with the universal lower bound A, and if there is a operator, bounded linear operator T, satisfying these conditions, these two conditions, then if we have an index set J, then the new weighted collection, these new erased weighted collections are also K fusion frame. Here K is T star, and this eraser is erasing by J components. And if this collection satisfying this condition, this inequality, then these two erased weighted collections forms T star fusion frames. In frame theory literature, there are so many applications. Here we mention some of them for signal processing, image processing, data processing, sensor networks. These are very practical like applications. Also in theoretical case, we can extend our work in reproducing kernel Hilbert space because in literature we have studied that people have done the properties of reproducing kernels by means of ridge basis. Also, we can study the properties of reproducing kernel by means of frames, because frames are more weaker condition than ridge basis. Because if we have ridge basis, then ridge basis automatically imply is a frame, but frame need not be a ridge basis. Why? Because there is a standard theorem, sequence is ridge basis if and only it is an exact frame. So if we consider any non-exact frame, then definitely it is not a ridge basis. So in theoretical case, we can study our work in reproducing kernel, also in case of wavelet analysis. And these are the references of our work. Thank you.
Thank you, Animesh. Let's see if we have any questions from the audience.
Yes.
Yes.
So your weaving frames are more like replacements of Schauder decompositions.
Yes, ma'am. Yes.
Your weaving frames are more like replacement of Schauder decompositions.
No, ma'am.
I mean,
Hello.
Yeah, I mean, you have bases and there is orthonormal base. You have Schauder decomposition and your replacement for that is these weaving frames.
No.
What is it?
Actually, frame, no, if there is a Schauder basis, in basis, yes, in basis elements are more restrictive case are there, because basis elements are always linearly independent. But frame
Right. But your frames, when you take subspaces, WIs and weights, they are more like Schauder decompositions.
So basically, these are closed subspaces are spans of given frames.
Thank you.
Yes.
Thank you, ma'am. Let's see if we have any other questions. Okay, so if we do not have any more questions, let's thank the speaker again. Thank you, Animesh.
Yes.
So before going into the next talk, we will have a quick break. We'll start at 4:30 p.m.
sorry to interrupt, but I think our scheduled time is 4:25, so that we can finish at 4:40.
Oh, sure. I have not updated, I guess. Sure. So in that case, we can ask the next speaker to present their screen.
Right.
Well, thank you, though it's clear now.
Thank you.
So let's wait for a couple more minutes before we start.
Sure. Sindhi?
Yes.
Is my audio okay?
Yes, it's perfect.
How are things at ISR Barampur?
Good. I'm sorry I couldn't recognize you.
No, we never met, but I was just looking over institutes over India. It's about the time I should start applying for.
Oh, I see. Okay, I see. Yeah, right now, COVID situation is quite, creating a lot of hiccups because of that, the construction is being stopped and things like that. But yes, but other than that, pretty good.
Okay. Is there a PhD program there?
Yes, of course, we do have a PhD program, and in fact, we might start integrated PhD as well from the upcoming semester. So we are entering 5th year actually. So.
Oh, yeah. I'm a nicer alumni. I was looking. I don't. Oh, time passed by so fast. I don't even realize that it's been 5 years. ISR Parampur.
So when did you leave NICER?
In 2016.
Oh, okay. So it just started then.
Yeah.
Okay, so let's start. So the next speaker is Asaimani Thamizhalagan from University of Waterloo, and he's going to talk about on the structure of invertible elements in Fourier stages algebra. Please go ahead, Asaimani.
Thank you, Sandhya. I would like to thank the organizing committee for providing me this wonderful opportunity. And also, I would like to register my thanks to my supervisors, Dr. Nico Sprong and Dr. Brian Forrest. This talk concerns about the structure of invertible elements in Fourier series algebra. Before getting to know what these Fourier series algebras are, let's recall what is an abstract index group of a Banach algebra. If we consider a commutative Banach algebra with identity, and if we collect all the invertible elements and give the norm topology, it becomes a topological group with exponential as an open subgroup. These exponentials is exactly the connected component of the identity. If we quotient out these exponential from the set of all invertible elements, what we get is abstract index group, and we denote it by H1 of A. The notation comes from the study of cohomology. If we consider any Banach algebra homomorphism between two Banach algebras A and B, then the homomorphism maps set of all invertible elements of A into set of all invertible elements of B, and it maps exponential into exponential. So this map induces a map at the level of index group. A very deep theorem about this is Arons-Royden theorem, which states that if you have a commutative Banach algebra with identity and spectrum delta A, then the induced map, the map induced by the Gelfand transform on the level of index group is an isomorphism. Okay, we'll come back to this consequence of this theorem a little later. This concerns the talk concerns about saying something reasonable about the index group of this Fourier series algebra. A little bit history, like around 65 to 72, Joseph Taylor was mainly invested in studying the structure of commutative convolution measure algebras. The definition is irrelevant, but think of these algebra as a measure algebra of a locally compact abelian group or a locally compact abelian topological semigroup. He used certain semigroup techniques and serious cohomological calculation on its maximal ideal space to provide very general factorization theorem. In fact, he produced two factorization theorem, and one is well-known Cohen's idempotent theorem, and other one is about the set of all invertible elements. So if you take any invertible element in this math frac A, there are distinct maximal group algebras. Maximal here by the group algebra, we mean that it is isomorphic to some L1 of locally compact abelian group, and maximal means if you have any intersection with any other group algebra, it has a non-empty intersection, it has to be contained inside these group algebras. So the idea is if you have any invertible element in this math frac A, then there exist elements nu i's from the unitized group algebras, and these are invertible in the unitized group algebra, and we can represent this measure as a convolution product of nu1 to nu1 with an exponential. So this essentially says that the index group of this math frac A is exactly the direct sum of index group of certain maximal group algebras. The spectrum of the measure algebra is quite complicated, but the spectrum of these, the Gelfand spectrum of the group algebra is a group, it's a dual group itself. So it's tractable in a sense that each of these, he is able to describe these invertible elements in terms of more approachable guys. For example, if we take a locally compact abelian group, and if the math frac is measure algebra, then these maximal, each of these maximal group algebras are L1 of G tau, where G tau is G as a group, but its topology is finer than that of the group topology. When G is real line, there are only two topologies that is possible. One is the usual topology, the ambient group topology, and other one is a discrete topology. Okay. There are certain non-commutative analogs proposed for this L1 and L1G and the measure algebra M of G. In 1964, Ahmad introduced for any arbitrary locally compact group certain algebras, namely B of G. This is called the Fourier-Sturgis algebra. It's a collection of all the coefficient functions of continuous unitary representation. And A of G is Fourier algebra. It's nothing but the collection of coefficient functions of the left regular representation. Left regular representation is one of the important representation for any arbitrary locally compact group. And by the way, L1G is an ideal inside M of G. A of G is also an ideal inside B of G. A of G is Fourier algebra and B of G is Fourier-Sturgis algebra. And B0G is called Rachman algebra, which contains the B of G, those functions in B of G which vanish at infinity. Okay, there are several developments made since 64 to ensure that these guys determines G. If B of G1 is isometrically isomorphic to B of G2, if G1 and G2 are topologically isomorphic, and so for A of G and so for B0 of G. And Bochner's theorem says exactly why these are the wonderful candidates for the analogous wonderful candidates in the non-commutative setup for L1G and M of G. When G is abelian with dual group G hat, the Fourier-Sturgis transform, and Fourier-Sturgis transform is nothing but the Gelfand transform of M of G restricted to the G, and Fourier transform is nothing but the Gelfand transform of L1G. And Fourier-Sturgis transform maps M of G isometrically onto B of G hat and L1G onto A of G hat. So in sense, these guys are the dual objects. The philosophy is that B of G corresponds to M of G hat and A of G corresponds to L1 of G hat. So the properties of M of G would correspond to B of G, and the properties of L1 of G would correspond to Fourier algebra A of G. So in that angle, so when we try to ask this factorization for general Fourier-Sturgis algebra, certain developments were made based on a spectral approach and also based on topological approach. Spectral approach is quite complicated to present in a 10-minute talk, but the topological approach is by my supervisor Nico Spronk and Monica Ellie. In 2007, Spronk and Monica Ellie developed the non-commutative dual analog of the spine of the abelian measure algebra. By spine is exactly, if we consider these maximal group algebras, we can take the closed linear span of these maximal group algebra. Taylor called this closed linear span as a spine of the spine of the abelian measure algebra. So they developed the non-commutative dual analog, the spine of the measure algebra, and the conjecture. If you take is every invertible element U in B of G is of the form, if we can factorize them into V1 till Vn, so that Vi's are in a tractable object, and tractable objects are this Fourier algebras. So the Vi's belong to unitized Fourier algebra and they are invertible in it. But because of the duality, this topology now becomes a coarser topology, coarser than the ambient topology. For the case in M of G, we had finer than the ambient group topology. Okay. So let's get back to Arons-Roden theorem. And what does Arons-Roden theorem says is that the induced map by the Gelfand transform at the level of index groups is an isomorphism. There's a fairly decently easy corollary that can be said about this is if you have two Banach subalgebras such that the spectrum are the same, we can consider radicalizer algebra of A in B, their spectrums would be the same. Okay. If you have Banach subalgebra such that the spectrum is same as the bigger algebra, then all the invertible elements in B can be expressed as invertible element of A times some exponential. Okay. So in general, this B0G, which is called Rachman algebra, This is far bigger than A of G. But there are some cases where B0 of G becomes A of G. And those when B0 of G becomes A of G, then we call it a regular. It happens only when B0 G is a regular Banach algebra. So when you have regular Rachman algebras, then so the spectrum of B0 of G is exactly same as the spectrum of A of G, and the spectrum of A of G is nothing but the group G itself. Then we can express the invertible elements in B0 G as exponential in B0 of G times A of times invertible elements in A of G. A fairly easier example comes from the Euclidean motion group, and any decomposition of the Fourier series algebra is intimately related to how the representation decomposes. So the B of G can be decomposed in such a way that it's B0 of G plus the all the decompositions are L1 direct sum, and it can be decomposed in such a way that it's B0 of G plus Fourier algebra of the compact group SON. And the spectrum is the same, and the spectrum of B0G is same as spectrum of A of G, which is G, and the spectrum of B of G is union of two groups. And SON here is also the something called as the Bohr compactification of this group. So when this, and there is a reasonable another remark that follows is whenever we have such decomposition where one is ideal, where A is equal to I plus B and I is an ideal and B is a closed subalgebra, we can easily, with a simple calculation, we can represent the invertible elements in A through the items in I and B. So this follows automatically. So from this example gave a structure to where to look at, what kind of example to look at. So we developed certain examples later. We collected several literatures that said examples. The first example, you can think of this as a compact group acting on the vector group such that the action has a non-trivial fixed points. The action at the levels of Lie groups has a non-trivial fixed points. And there are something called as totally minimal groups. These groups are such that the minimal group is such that there is no Hausdorff topology on the group coarser than that of the group topology. And totally minimal means if you consider any factor group, if you consider any factor group that is the quotient ordered by the closed normal subgroup, even that is minimal. Okay, so these have a structure theory that they always look like semi-direct product of a simply connected.
Sorry to interrupt, Mani. I think the talk was for 10 minutes. So maybe you would like to wrap it up a little bit faster. So
there are several examples that evolved looking at this structure, and this structure looks like B of G can be represented as the decomposition of these algebras. AR means that the radicalizer of the Fourier algebras, and each of these have an ideal structure, and the spectrum splits as the semilattice of these groups, and these groups can be determined by some central idempotence inside the spectrum. And the theorem is that the index group of B of G can be described exactly as the direct sum of index group of the Fourier algebra of these smaller groups. So hence we have desired factorization. And A of AX plus B, the group AX plus B with the Taylor's analysis can also have a desired invertible element characterization. Thank you.
that was quite a challenge for giving a 10-minute talk. So thank you for that. And let's see if we have any quick questions from the audience.
Sorry for going over the time.
That's okay. So yeah, 10 minutes is quite difficult. Okay, so I don't think there is any chat messages as well. So if there's no other questions from the audience, I would like to thank the speaker again. Thank you, Asim Manithamralagan. So thank you.
Thank you. Thank you.
So now I'll give over the session to the organizers. Thank you once again, organizers, for this wonderful, the fest. It's really delightful. Thank you so much.
Thank you. Yeah. Go on, Soma.
Yeah. So we would like to thank Professor Senthil for chairing this session. Thanks a lot for your help.
Thank you.
Yeah. Okay. See you. See you all.
See you. Yep.
Start admitting people.
Oh, wow.
I'm audible, I believe.
Yes, very much.
Yeah. Okay.
How did the other panel go? Was it good?
Yeah, it was very good.
Soma, could you make Saurabh a co-host?
Yeah, I'm doing.
Yeah.
So one query, Tulsi, when others are speaking also, you want all of us to keep our audio and video on, or?
I think it might be better if everyone turns it off except for the person who's speaking, just to help with the connection.
That's what I thought. So you're already doing your admissions for your programs, or?
Yeah, we are being optimistic and assuming there will be a new year in which to admit students. Let's see how that goes.
When are you planning to start your session?
Maybe mid-September. I'm not sure.
What about you, Geeta?
Our current students, we are going to start classes for them in August. The first week is orientation, and then we are supposed to start online teaching. But for the new students, we are kind of bound by the UGC regulations to some extent. So it seems to be like 1st November for undergrad programs and 1st December for postgrad programs.
I see.
I'm just wondering how the academic year is going to play out. I have a feeling that we'll be teaching every month of this year and the next year, because we'll finish with one lot and then the next lot will start and so on. So
You should take some tips from us.
You'll be speaking at length about this today, right? So
yes.
Maybe, yeah.
And what about the current batch students, the students of 1920? How are you going to evaluate them?
We finished. We declared our results 12th June.
Oh, final year students also.
Yeah. We have a continuous assessment, no?
Right.
Already completed quite a lot, and then we completed, assessments. We have freedom to decide how we want to conduct our assessments. It doesn't have to be a sort of final exam type of thing. But in maths, we all conducted exams for them. It was more or less, it was open book in a sense because we couldn't proctor them. They were in a Google Meet with us, but we couldn't really keep an eye on what they were doing. But they were expected to, the time wasn't too much for them. And the questions weren't really of the sort where they could just copy it off something or the other.
Okay.
And they had to upload their answer sheets. I mean, even if it was multiple choice, there was, you had to upload the justifications for it.
Okay.
So, mix of things, Viva, there was a mix of Viva, assignment, small tests, slightly longer tests, multiple choice. So it was like, but still in the entire university, about 400 odd students didn't complete their assessments.
Oh.
So they're getting a chance now.
Okay.
To finish it. So I think that we'll have to keep giving. The ones who had problems, couldn't finish.
What's your total student strength?
We are about 2,000 and more.
Okay, so a good percentage.
All undergrad, postgrad, research scholars. Altogether, we would have, I think we may be heading towards 3,000.
Okay. So it was a sizable group that couldn't finish.
Well, this includes all levels. I mean, undergrad and postgrad, yeah.
I'm just wondering, Soumya, if maybe we should begin now?
Yeah, okay.
Yes.
So, welcome everyone for this panel discussion today. We're at the 5th day of our conference, Virtual Maths Fest 2020. For this panel discussion, we have with us Dr. Tulsi Srinivasan from Azim Premji University. She will be the chair for this session today. Okay, over to you, Tulsi.
Okay, thanks, Soumya. I just want to welcome everyone to this panel, which is on educational challenges in undergraduate mathematics. I hope everyone can hear me.
Yes.
Okay. So the thinking behind holding this session is that we have such a variety of undergraduate programs at which mathematics is taught, from the programs hosted by research institutions to those at state colleges, private colleges, maths taught at engineering colleges, and so on. And while the aims of these programs and the type of students who join them are very different, as instructors, we seem to face a lot of extremely common challenges. And there's maybe not so much literature in pedagogy at the undergraduate level and not so many resources. So I would really like to thank the organizers for deciding to add this session to the conference. So this includes the core organizing group of Shoyon, Soumya, and Saurabh, but also Jam, Arul, Prathamesh, and Divakaran. I also want to thank the panelists. So we have Dr. V.V. Acharya, Dr. Amber Habib, Dr. Fozia Kazi, and Dr. Geeta Venkatraman. And I think we are extremely fortunate to have a panel that brings such a wide variety of experience. So between them, they've taught maths in multiple contexts at the university level, but they've also been involved at MTTS, Maths Olympiad training, teacher training workshops, events for school children, and they've also contributed to curriculum design at, again, university as well as school level. And because of this wide variety of experience that they have, they're going to share their thoughts at this panel at both the large scale, so structural problems and possible solutions there, as well as small scale, which I think is going to be very useful for undergraduate instructors who are present, including me at this conference. So experiences by their students, experiences by themselves and their department members, classroom practices, experiments in pedagogy and assessment, advising, mentoring, and so on. Given the theme of this panel, it would have been nice to have a kind of free-flowing conversation, but I think we collectively decided that Zoom is not the correct medium for that. So instead, what we'll do is that each of the panelists will speak a little bit about one or two sub-themes under this broad umbrella of educational challenges. And then we'll go around again so panelists can respond to what other people said. And then finally, we'll open it out to questions. We should have at least 20 or 25 minutes at the end for questions from the audience. So we'll begin with Dr. Geeta Venkatraman. So Geeta has an MA and a DPhil from Oxford University. She's currently Professor of Mathematics and Dean of Research and Consultancy at Ambedkar University in Delhi. She has interests in group theory as well as in mathematics education and in popularizing mathematics. And she's also interested in issues related to women in mathematics. And she's on the executive committee of Indian Women in Mathematics. And today, Geeta is mostly going to focus on the difficulties students face when they transition from school maths to college maths, though she will probably touch on many other topics as well. So thanks a lot, Geeta.
Thank you, Tulsi. I guess I can start now.
Yes,
somebody
please.
needs to keep an eye on the clock because as teachers, we suffer from the problem of not wanting to stop once we start. So please let me know.
Yeah, I suppose that is unfortunately my duty, so I will try and do that.
So good evening to everyone. I'm not able to see all of you, but I guess I'm hoping that you are able to see me. I wanted to thank the organizers of VMF 2020 for having a panel of this sort, because I really do believe that undergraduate education and undergraduate maths education in particular are key areas that our country needs to focus on, not just our country, but education systems worldwide. But there's a peculiar problem that we do face in India in the way we've structured our undergraduate curriculum. I'll touch upon that briefly during my conversation with you. But thanks to the organizers for putting together such a panel, and thank you for inviting me to be part of this panel. I just wanted to say that I have now for more than 25 years been engaged with teaching at the undergraduate level, starting from tutorials that I did as a grad student at Oxford. And then I spent a long stint in St. Stephen's College, where I primarily taught undergraduate students. And now I'm at Ambedkar University, Delhi, which is a new university, relatively new, I should say. It's completed 10 years now. And we have an undergraduate program in mathematics, a maths honors program. And then we also have research programs, MPhil and PhD programs. So what I'm going to say is, in a way, garnered from all these many years of being engaged with undergraduate maths education, in that sense of teaching maths to maths students as well as to non-maths students. I'm going to touch on a few points, but one key point that I want to mention, and I would hope that it gets all of you thinking about, is that undergraduate mathematics education must be seen as part of the larger schematic of undergraduate education. What I mean by this is that you cannot focus on mathematics education at the undergraduate level as a continuum in just mathematics. It has to be thought of much more holistically as part of what an undergraduate takes away from the system when they complete their degree. Before I go into more details, look at the kind of students who are entering into undergraduate education. They are very young, they've just finished school, they are 18 plus. Most of them our school system is such that it herds students into streaming even before they can know what those streams are: humanities, commerce, and sciences. And when they finish 12th, even before they finish 12th and 11th and 12th, they are already being made to decide what kinds of careers they want to enter into, what subjects they want to decide to study, and so on, without actually having any experience with that discipline at the higher levels, or even knowing what it entails. They're also moving from, so it's a very key period in their life, the undergraduate period. That's when they're taking first steps into being an adult. They're preparing for life. They're moving from a very fixed school routine to an apparently open and free system at the university level. And the other feature that you must remember is that for most people entering undergraduate education, it is a terminal degree for them. They are not going to continue with the subject or any other postgraduate program. I don't really have the figures, but from my experience with teaching mathematics per se, I would say that in a class of about 50 students, just about 10 would continue for some kind of a postgraduate program or so. And out of that 10, this is in a college like St. Stephen's where I taught for many years, you would have at most 4 or 5 students who were doing mathematics honors who were going to continue to study maths further at the next level. I mean, one doesn't even know whether they would continue to do research in mathematics, but this is the kind of basic situation that you have at the undergraduate level. However, when we design things for the undergraduate level, when we are talking about the syllabus or what we're going to teach them, I think all of us, I mean, me including at many times, we've thought about it primarily from the point of view of mathematics. So in a sense, what's happening is that we have our notion of what is required to be able to do research, to do a research degree in mathematics. That kind of decides on a certain syllabus at the master's level. There is the school syllabus in mathematics, which is decided by different methods, modes, and so you have school maths ending at a certain level, and you have masters in maths starting at a certain level, and it's like the undergraduate period has to somehow bridge the gap between these two things. And this is only from thinking about maths and thinking about the fact that everybody there may end up being going on to research in mathematics. So the first point I want to mention is the problems that we have in transitioning from school to college level maths also have to do with the way in which we have designed or we've thought about mathematics at the undergraduate level. We have not thought about it in keeping with general undergraduate education. We have mainly thought about it as the means to create people who will ultimately study PhDs. And look at the unfairness of it all. I mean, in a class, as I mentioned, of about 50 students, I would have just about 4 students thinking about continuing with mathematics. However, the syllabus that has been primarily made is for those 4 students and not necessarily for the larger set of students who have opted to do mathematics at the college level. So that's something that we should be looking at. And, how do we design? The key question in my mind is how do we design an undergraduate maths experience which can both take care of the needs of mathematics as a discipline as well as take care of undergraduate education, the needs that must be fulfilled via undergraduate education. If we have more time in the question answer session, I will take up issues on how this can be done. I just want to mention very briefly that at Ambedkar University, Delhi, we have tried to do this. We offer a lot of choice in the courses. There are core courses which every math student has to do. But when it comes to elective courses, they can choose from non-maths options as well. So here's a math student. If they want to continue with maths, they can choose maths electives, which will help them for their masters. But if they don't want to continue with mathematics, they have the choice of taking things from elsewhere. They also have the choice of changing their major if they have started with maths and they find that it is not something that they are happy with. And this brings me to another question that we should be addressing, which is that when we have integrated master's programs or even integrated PhD programs without exit options at appropriate times, then it's really something where you're trapping a student and maybe dooming certain students to failures. So whenever you're thinking about creating integrated programs, and a lot of institutes have that, ISAs have them, they must think about the student who after 3 years does not want to continue with mathematics. What do they have to offer to such students? Now coming back to what happens when students come from school to college. School at the secondary level becomes extremely focused on cracking board exams and cracking various entrance exams. As a result, students end up learning methods largely, rather than they've not really thought about why the mathematics works, what mathematics that they're learning is about, or even delving at any deeper level into it. It's largely about learning methods to solve difficult integrals or trick problems and so on and so forth. On top of that, the board examination system also has what is called a marking scheme. So unless you write things in a particular way, you won't get the marks. So a lot of time is spent in schools and so on in trying to teach the students how to do those, make sure those steps are in place. And this leads to a very, very strange situation when those students come into college, because they've come into college, not knowing what college maths is about. They have actually no experience that a lot of college maths is about why maths works. Why is it that it is so effective? We are delving into deeper concepts in everything. And the last time they met something like that was possibly when they did some kind of geometry in middle school or late middle school. And I'm not even sure whether now they still do theorems and proofs and riders like we used to do when we studied. But that's about the only place where they've really seen that kind of thing. And then they've come into college. You throw a very difficult integral at them, they will know all the tricks to solve it. But you ask them what a derivative is, they have no clue. So you're getting a set of students who've come into college who are, when you're about to hold your first test or something, the first thing they ask you is, ma'am, how do we write a particular answer? They're very worried that if they don't give the steps as was prescribed in the board exam type of thing, they're not going to get marks. So there's this concern about, so I end up telling them, look, you have to make an argument. As long as you are arguing correctly, it doesn't matter how you write it. There is no one fixed way of writing things, but that's something, it takes a long while to tell them that, to kind of get them used to thinking about mathematics, being able to communicate mathematics. They have to learn that writing mathematics is writing mathematics in a language. When they come to you initially in college, all you get is lines of symbols with no connectives between them, and that is supposed to be an argument of how they've solved something. The other thing that you find them doing a lot is proof by example. I mean, it takes a long while for you to again communicate to students that, what a proof really is. So being able to think about mathematics, write mathematics, communicate in mathematics, these are all skills which are very low or largely absent in students who are coming from school. Tulsi, how much time do I have?
If you could just wrap up in a minute or so, and then I think you raised some very important points which we can come back to in the discussion.
Yeah, so the point is that there is a vast divide between the way mathematics is tackled, particularly at the secondary school level, and the kind of things that is expected when students are coming into a maths degree at the university level. The other issue that I want to bring up here is, what is the maths that should be given to them at the undergraduate level? Along with it, what else do they need so that their need as citizens going away with an undergraduate degree from the system are fulfilled? And that is something that we are really not thinking about at all. The other question I want to really raise as part of this transitioning is, why are we in a hurry to fast track researchers? I mean, I don't know about people now, but it took me a fairly long time before I decided that I wanted to do research in mathematics and choose mathematics as a career. But a lot of the newer institutions that have come up in the last 10 years or so, all of them, including the institutes which run undergraduate programs, all are single-minded with one fast track a person, an 18-year-old who probably does not even know what they want to do, to, okay, they are the ones who are going to do PhDs in maths and then continue to mathematics as a career. Now, a few of them may be wonderful examples of people who could do that. But I would argue that even in their case, they should have the experience of what it means to be an undergraduate in a liberal education rather than having a fast track. The last thing that I want to say is that we also as mathematicians ought to be thinking about how we teach maths or how maths should be communicated to non-maths people. The bulk of the world comes with very bad experiences from school. They hate maths, and sometimes that hate transfers to not knowing how to deal with a mathematician. And as mathematicians, as people doing mathematics, we are also living in this real world. We are part of society. Any job that we do, we have to work with others. And I think it's time that people involved in designing curriculum, designing syllabi, creating undergraduate programs should be thinking with a larger perspective and thinking about how people coming through the system, even if they go on to do PhDs in mathematics, can actually live as citizens in this world and actually have a sense of many things that are happening around us. Last point, COVID-19, I think all of us have encountered online teaching, and for me it was an abrupt, one day, I was teaching in class and some 10 days later one had to start teaching online, and I didn't have the equipment available, and it's really, I think, I don't know about others, they can probably come in on this, but as a person, when I teach mathematics, there is something very special about writing on the board. When you write on the board and you're talking and you're looking at your students, you're explaining things, you're discussing it with them, I think the slow speed at which that happens, it really helps students to understand concepts. And I'm not sure how well online teaching, particularly if we don't have access to such things, works. And also assessments, that's a big issue. Maybe these are things that will come up later. And with this, I will ask Tulsi to take over and hand it over to the next panelist. Thank you.
Thanks a lot for that, Geeta. I think there are some points which you raised which are extremely important, which hopefully some of the other panelists will be covering too, other things which we should return to in the discussion. So the next panelist who will be speaking is Dr. V.V. Acharya from Fergusson College, Pune. In fact, he's the head of the maths department at Fergusson College. His master's and PhD are from Pune University, and he has 28 years of teaching experience. And over 28 years, he's also been very deeply involved in activities related to the Maths Olympiad. So he's been the regional coordinator for Maharashtra and Goa, the deputy leader for the Indian team at the International Maths Olympiad in both 2003 and 2004. And he was an observer for the same in 2013. He's also conducted various training programs for the Olympiad across the country and written and edited a book for the Maths Olympiad called An Excursion in Mathematics. In addition to this, Dr. Acharya is a life member of the Deccan Education Society and a trustee of Bhaskaracharya Pratisthana. So we are very happy to have Dr. Acharya with us today. He's going to be mostly speaking about challenges that we encounter when teaching large classes. And some of this is also going to be relevant about the difficulties that people will face teaching during this pandemic. So Dr. Acharya, please take on.
Good evening. I thank all the organizers for inviting me for this panel discussion. I thank Dr. Geeta for saying some of the issues which are being faced in this entire process of learning. There will be some common points between me and Geeta. So one of the important issue is pre-knowledge of the student. And what we want to do is we get some students who have passed their 12th standard, and we want to teach them something. This is desired by quite often by UGC. So UGC tells that, you know, such and such things should be taught to all the students. And pre-knowledge to this of these students is something which we cannot really decide, because for example, in my college, we have about 400 and odd students in first year BSc. They come from different backgrounds from across the country, and everybody has his or her strong points in mathematics, quite often restricted only to problem solving. So that is one point. And the point number two here is language. So some of them have studied in Marathi medium, some of them, so in the regional languages, Bengali or whatever. And when they come to the first year BSc, they have to learn everything in English, and that becomes an issue. Moreover, the 11th, 12th standard structure in our entire country is broken to pieces. I don't know how we can join it, because everybody wants to write some entrance exam and want to get good score there. And that creates an issue, because one doesn't know what has to be written, how to read, how to write, but we know how to write on the exam. So basically, all these things are part of rote learning. It's you learn something and then go to the examination hall and vomit it. It's nothing different than that. So the point is that going back to the first point, we should understand that in education, we should concentrate what the student knows and where we want to lead them. So from known to unknown. And in huge classes, this is difficult. In a small class, you can possibly take some 2-3 tests, but when the number is huge, it becomes almost impossible. Secondly, this forces us to develop the methodology to identify what students know and what they do not know. And the most important thing is when we say that the students know, what do you mean by they know? So they quite often know how to, as Geeta said, that they know how to integrate, but what is integration is not known to them. So quite often I ask a question that what is the limit of sin x upon x? So they say that the answer is 1. And then I say, oh, where is x tending to? Then they say that, oh, you didn't tell us that. So this realization comes in a different way. The second aspect is, if you know that certain problem can be done in one way, can you do it in some other way? School geometry writers offer an excellent facility to do this. But unfortunately, not much is done. Quite often, the syllabi of school is diluted, and this creates lots of jumps or gaps in education. So for example, the first gap which I can see is going from 4th standard to 5th standard. Then the next jump comes from 8th standard to 9th standard, where quite often that's this place where the notion of proof is introduced. The next jump comes when the student goes to 11th standard. And the major jump which comes is in first year BSc. As one of the participants suggested, that in first year BSc, what happens is the maths which is being taught till 12th standard is problem-based, and all of a sudden it becomes a proof-based mathematics. And this creates lots of problems. Students do not know how to read mathematics, they just know how to solve mathematics. So this is my personal experience also, that in the school, what I used to do was you read the exercise set, solve it, but never read the entire textbook. So even now in good colleges across the country, if you ask this question that read a mathematics textbook, that becomes a challenge for most of the students. They do not know how to ask questions, and partly the reason for that is rote learning. And there are several questions. So for example, do the students ask these questions? What, where, when, why, how, who? And I think this is the place where we as educators have to work a lot. Quite often, there is an issue here that we are highly qualified, but untrained teachers. Some of us take efforts to get the training. You know that how to do mathematics, as Geeta said that, yes, we know how to write thesis, how to write down the research papers, but how to educate the student, that's a skill. And in some countries across the globe, there is a special training program that, okay, you have finished your PhD, you work with somebody for a year or two, and after that you can teach. But in India, this problem is there that you can finish your MSc, you can then write down NET set. If you have cleared NET and if there is a job, you will get the job. If you are lucky, of course. But there is no way where it is being taught how do you teach higher level mathematics. We have training programs for school teachers where they do D.Ed or B.Ed, but nothing for high school, for university teachers or for college teachers. There are various issues after this, and these issues are about the assignments and their evaluation. Quite often we give the assignments to the students, we evaluate them, but the later part is missing. Who will do the analysis where our student is good or our student is bad? And if some place the student is lagging behind, how do you improve the students, or how do you improve your teaching style, or how do you change your teaching style? So these are the issues. Quite often students tell me that, we have a difficulty, but we do not know how to ask the question. This is partly responsibility of us to make sure that students come out of their zone and are comfortable with us. Sometimes bright students, of course, help the weak students, but there are issues in this entire process. There are, in the current scenario, there is a pandemic across the globe, and we have issues here. One of the most important issue is teacher-student connection for fresh students. As Dr. Geeta pointed out, there is already a fear about mathematics. I quite often call it as a mathophobia. Because of the mathophobia, people are afraid of talking with the teacher. They think that, oh, this person is math teacher, so how do I connect with him? During the pandemic, this scenario is going to be more difficult, especially for fresh students. The person doesn't know who is their teacher and how do I communicate with such a person. Similarly for the teacher also will face lots of issues in this. There are several other issues which are there. one of the important issues is network connectivity. We have our students who come from small villages in Maharashtra as well as from other parts of the country where internet has not reached, and somewhere on the top of a tree or some such place they may get the signal. How do you communicate in this scenario? There are other issues like electricity, especially during the monsoon. This will be a real issue. One of the important point is live feedback. In the class, when we are teaching, if student doesn't understand something, she may ask a question or he may ask a question. So we can go back and forth. When we are giving these lectures online, there is no live feedback. I gave about 20 lectures during this pandemic, and very rarely students ask me a question. And therefore, it becomes a real difficult scenario because teachers don't understand. And this is not only my personal feeling. Other day, I was hearing a webinar where people from IMSC, ICERS were speaking, and they also said that, oh, live feedback is missing. So I believe that the pandemic scenario will make really a difficult thing about this live feedback. Instruments, there are about 40% of the students who are learning in Ferguson College who have issues with these instruments. I do not know what will happen for a smaller college where Android phone or tab or laptop or desktop is missing. Then in this case, how do you teach the student online? And especially when the classroom is big. Another issue is screen duration, how long you can teach. So for example, in third year BSc students in our regular class, we teach them for about a period of 6 hours every day. Screen duration for such a long time is a challenge from the student's perspective. I think this will be a big issue. Yet another issue here is the freedom to learn from the experts. I believe that by using this online methodology, students will not get the freedom to learn from the teacher of his or her choice. Quite often it will happen that the parents may not leave the child to the places where pandemic is in at highest level at this point of time. And choice of the learning platform is an issue because some teachers will use possibly Zoom, somebody will use Big Biblioton, somebody will use Microsoft Teams, somebody will use some different platform. So choice of the learning platform will create a problem. And most importantly, Tulsi, how much time I have?
I think you're running a little over, but please feel free to finish and we'll try and reorganize the time. So yeah. I don't want to interrupt you here.
Yeah. So but I'm almost towards the end. One of the last thing which I have written here is in Devanagari, which is in Sanskrit, which says that Acharyat Padamadatte Padam Shishya Swamedaya Padam Sab Brahmacharibhya Padam Kalakramena. So about the literal meaning is that you can learn about 25% of the study from your teacher, 25% you can learn on your own, 25% you learn from your colleagues, and 25% of the knowledge you learn over a period of time. I believe that in this scenario, all these aspects will be taught cannot be used by the students because he doesn't have a direct contact with the teacher. He has to spend more time for learning on his own. He possibly doesn't know who are his colleagues, and that will really create a problem for overall understanding of the subject. Possibly, we will have a more discussion in the question answer sessions. I again thank the organizers for giving me an opportunity to participate in this session. Thank you.
Yeah, thanks a lot for that, Dr. Acharya. I think the last couple of lines that you put up especially really resonated with me. So I am going to make a suggestion. We are running over, but I also think maybe it was the original suggestion to the panelists to speak for just 8 minutes was not very realistic. So what I'm going to suggest is that Fouzia and Amber, maybe you can also spend maybe 10 to 12 minutes, and then rather than an internal discussion, we can go directly to questions from the students. Then there's not going to be so much time pressure. I hope that's okay with everyone. So the next speaker is Dr. Fouzia Qazi. She's a professor of mathematics and the department head at the Islamic University of Science and Technology. She has a PhD in maths from Syracuse University and has worked as an academic in the US for many years. And after this, she returned to Kashmir in 2009, since when she's been with the Islamic University. So Fouzia was instrumental in starting a job-oriented maths program at the Islamic University, as well as conducting maths outreach programs for school children, maths festivals, teacher training programs, and so on. And her current research also involves studying symmetries in shawls and other traditional patterns of Kashmir. Fouzia is going to talk about her very unique and difficult experiences in the last year teaching maths at a time of political turmoil in Kashmir, and maybe also touch a little upon the further problems caused by the pandemic. So, Fouzia, would you like to begin? Fouzia, I think you're muted.
Am I audible now?
Yes, thank you.
Okay. Well, thank you, Tulsi, for the introduction and for the invitation to be part of this panel. I will focus primarily on my experiences of teaching in Kashmir over the last 11 years. But a lot of what I'm going to talk about may be unique to Kashmir, but it is also a question of access. It is also a question of having different student groups who may or may not have access to the same resources that everybody else does. So what were the challenges that we have faced over the last 11 years? I'll sort of highlight some of them. But when we started the math program, this was in 2009 at Islamic University, we had primarily two objectives. And one was that we wanted the program to be sort of job-oriented. Employability was one of the issues. And it addresses what Geeta had earlier talked about, that when we think of undergraduate programs, we tend to think of all the students wanting to do a PhD. So the syllabus is often designed in that way. But we wanted at Islamic University for the course to be more job-oriented and not just be a regular, what was taught in most other colleges locally. And so we started an actuarial mathematics program. But the other objective was that there has to be some flexibility. Flexibility in terms of, again, Geeta touched upon this issue also, that you have an 18-year-old who comes into the university or the college for an undergraduate program. At that time, they may not really know what they're interested in doing further. And so we wanted, at the end of the 3-year program, we wanted to the student to have the flexibility to either just go for a job or go for a postgraduate program in not just mathematics. They could do a statistics, economics, or a few other options. But we also wanted to reach out to the student who maybe catches the math bug in those 3 years, which is a student who may want to go for a research program later on in mathematics. And Amber is familiar with the sort of the early discussions we've had, because Amber has been on our board of studies, and we had a lot of discussions, and we designed the program keeping these objectives in mind. And at that time, the challenges that we thought we were going to face were the challenges that the panelists that came before me have sort of touched upon. You think of math phobia, you think of the level of preparation of students who are coming in from school education into a college or a university. They may lack the basics, sort of understanding of the fundamentals of some of the basic concepts. These are some universal issues or challenges that you think you're going to face as a math teacher. So the other challenge was sort of, if you think of, and again, Geeta already touched upon it, is that students who are coming from 10+2 come from a system where there is a lot of focus on exams. And so education tends to be test-centric, getting the answer right, the correct answer that will get you the points that you want, rather than sort of understanding of the concepts. So those were some of the issues that we thought. So again, pertaining mostly to teaching of mathematics at an undergraduate level. The other challenge, which was going to be important for us, because our university is located in a rural area. The campus is outside of the main urban area. So our catchment area is mostly rural. We do get urban students also, but some of the issues which are unique to students from rural areas, which is that their access and exposure to technology, for example, was often limited. When you talk to teachers, I mean, I have talked to teachers during teacher training programs, for example. More often than not, the teachers who are teaching in rural schools often talk about the issues of a person who may not have a math background has to teach mathematics to school children, because there is non-availability of teachers, who are math teachers in rural areas. So that obviously has an effect on the quality of teaching. Also, when the students from the rural areas come to university, sometimes their sort of introduction to the university is different than the experiences of a student from an urban area. So we were sort of thinking we need to have certain courses in our first semester which would help the students who came from backgrounds where they didn't have access to technology necessarily, sort of ease them into the program. Having said that, and this is 2009, and now it is 2020, and if I sort of look back on this and look at the challenges that have been most critical for us over here, and this is not specific to Islamic University, but specific to our region, our main challenge has not been teaching of mathematics. Our main challenge has been basically teaching, because there is such a regular disruption of classes in our part of the world that the issues that I thought were going to be important were not as important, in the sense that some of the problems that Geeta was talking about, in some sense, is almost a luxury when I look at it now. I wish that this was all that we had to face, that we have students who have sort of whose experiences basically come from rote learning in high schools. It is true, we do have those students, but we don't get to teach them as regularly as we would like to. Just to give you a few examples of what has happened, and Tulsi, you just mentioned that we have had a lot of challenges since or in the past year. But the fact is that it's not just 1 year. It's been sort of consistently going on for almost a decade now, on and off. We've had 2010, where we had extended sort of shutdowns in 2010, and we had 2012, we had 2016, and then just to give you an idea of what has happened in the last year, our autumn semester usually starts beginning of August and ends in December. So we have 5 months in the autumn semester. So last year, in 2019, during those 5 months, we could only have roughly about 20 days of classes. We could not have online classes because internet was shut down also. So imagine 20 days of classes instead of 5 months. We just finished exams by the end of June, but those were not exams for the spring semester. Those were exams for the autumn semester. So when most of you are actually getting ready for the next autumn semester and next admissions and bringing in new students, we've just started our spring semester. Literally 1 week or 10 days ago, we started our spring semester, which was supposed to have started in March. So this is one of the problems. The other problem is even when you do talk to the students, even when you are there in person in a classroom, even for 20 days or 10 days, the students are traumatized. There is with all the, the problems that our region has faced, there is a lot of mental stress that our students face. So we as teachers, as their advisors, often, if you have an advising session, that may not be just about mathematics, that may be about the trauma that the student is facing, the stress of the sort of being and living day in and day out in a conflict zone. Another issue, which most of you are familiar with, that we have faced is the issue of lack of internet. We have, since August, I think for almost 7 months or so, we had internet shut down. I think I wrote it down somewhere. 2G network was started on the 3rd week of January, roughly. So between August and 3rd week of January, we didn't have any internet access. And even in January, you could only access certain quote unquote whitelisted websites. So teaching sort of online, like on Zoom or whatever else, was not possible. And it's only in March that that restriction was lifted. But we still to this day only have 2G internet access, which is majority of the students who may have a smartphone, who may have access to some sort of technology to be able to join a Zoom class or Google Meet or whatever it is, are doing that on a 2G connection. There are very few people, primarily in the urban areas, who may have a broadband connection, but if you look at the speed of the broadband these days, it is less than 2G sometimes. So I have a broadband at home, but sometimes I have to shut it off. I mean, the Wi-Fi I have to shut off because it's so slow. Then I use the 2G network. So the network itself is an issue. Access to information, access to online classes becomes difficult for students who are, and in some sense, it has been an equalizer in the sense that whether it is urban or whether it is rural student, the access to the internet is often very limited for both of them. Those are some of the major challenges. Now, how have we tried to overcome some of those challenges in the last few months? What we've done, for example, I remember in 2010, we had an extended shutdown, but it was done in a way where internet was still on. So we could, through email, talk to our students and send them notes. And then whenever we were able to meet with them in person, we would sort of go over that. That was impossible in August because everything, as I said, even the phones and internet was shut down. But what did work is that once the phones started working and once we were able to connect with our students, whether on the phone or in person, we were able to arrange some internships for them. They have an internship requirement. And this happened in many places, not just in our university, that the time period which was normally would be utilized for classes during the semester was utilized for internships because normally the internships would happen in the winter months. So we sort of switched and then were able to again restart classes in February. And then we had, I think, about a month of classes, month and a half of classes between mid-February and I think it was March 23rd or so when the lockdown happened, the COVID lockdown. So we have had, I think, about 50 days of classes when we should have had at least 10 months of classes. So those are some of the issues. We have become, I think, in some sense, counselors also for our students. We have to not just teach them mathematics, we have to also counsel them, become their psychological counselors. It's difficult. I don't have all the answers. We have sort of facing a lot of challenges in terms of connectivity, in terms of access also, especially for rural students. One of the things that Dr. Acharya was talking about was that, the teaching platform that a particular teacher may like. And I just had 2 days ago, I had a student call and say that, such and such teacher is using this platform, but I'm in a very remote area and that platform doesn't work for me. So those issues are very real and they happen on a daily basis for us. I think do I have more time or I can sort of talk about it a little later? I mean, if there are any questions. Tulsi?
Yeah, maybe we can pause now, go to Amber and then return to questions. So yeah, thanks a lot for sharing your experiences, Fozia. I think some of the things you described of the difference between planning and reality and about having to deal not just with maths, but the other concerns that students have, something we all have to face, but what you've described is at an unimaginable scale. So it's really admirable to hear about it. So we'll now move on to our fourth panelist, Dr. Amber Habib. Amber is a professor of mathematics at Shivnadar University. And before this, he was at the Mathematical Sciences Foundation and at St. Stephen's College. Amber did an integrated MS in Maths from IIT Kanpur, and he has a PhD from the University of California at Berkeley. His research interests are in Lie theory and mathematical finance. So Amber has contributed to the curricula and the activities of several universities and also to the NCERT, and he's been regularly involved with the MTTS program. And he's interested in how mathematics education at the school and college level can be made more interesting or more fulfilling through multiple ways. So projects showing the link with other disciplines and so on. And today, Amber is mostly going to focus on how undergraduate students can be exposed to and prepared for different careers in maths, both the curricular aspects as well as other things. So Amber, would you like to start?
Sure. Okay. Yeah, I've been doing a lot of this online teaching, and the thing that is most awkward is that you end up seeing your own face a lot of the time. And one way out of that is to share the screen and show something else instead. So let me do that. Okay. All right. So as this cover slide shows, I did not actually have a very clear idea what I can do in 10 minutes. I couldn't come up with a snappy title, so I made a diagram instead. But let's start. There's a few things to talk about. The people before me have said many things, but there's still a bit more to add to that. Let me start. Okay. So the thing that I've been thinking about for this is, what do students want to do after their undergraduate education, and what we can do to facilitate that and to guide that. And maybe let us start by looking at some of the things that are out there where mathematics is used. I mean, there are basically two topics one could have used today, Google and COVID, in terms of something that impacts us constantly. So I've gone with Google. So I thought something more pleasant. And let's see what happens if you type VMF 2020 into Google today. At least if you do that from Delhi, it's very interesting because the first two sites are, the first two links that you get are the ones that I want. But then there is also something for a vending machine fair in China that's also called VMF, and there are many, many others. And if you look at this, it claims that it generated 1,270,000 results, and it took 0.23 seconds to do that. Plus, out of those results, it selected these few as the ones it thought that I would be most interested in. Okay. All right. So clearly, a lot is happening behind the scenes here. Let's see what that could be. Let's just see what Google says about itself. All right. So they claim that they store information about hundreds of billions of web pages in their index, and that this takes over 100,000 terabytes of space. They handle 3 billion searches every day. And every time they do a search, it involves various activities like the ones mentioned here. They have to look at the words of the query, the type of the pages, the reputation of the pages, and so forth. Okay. Also, Google shares with us a little bit about what they use to do all this. Now, of course, Google is more than just the Google search. And here are various things that they say that they use in what they do. They use linear algebra to rank pages. They use machine learning for their spam filters, time series to model the number of searches and users. Income, I guess, is related to their ad income, right? So they're modeling that. Signal processing for their voice recognition components. Geometry is used by Google Earth. Graph theory is used by Google Maps. Game theory is used by them again for the auctions of their ads. Okay. All right. So now these topics are, are kind of undergraduate or at the boundary of undergraduate and graduate mathematics, right? So it's at least certainly possible for an undergraduate student to have various skills in these directions when they graduate and be eligible to work on these things. And also, these are topics that are not just of relevance to Google. These are also the things that you would use for a wide variety of other applications of mathematics. Okay. Okay, so that's one. That a lot of mathematics serious mathematics is finding use in many directions, and undergraduate students can get off to a good start in learning this mathematics. Okay, that's not the final word on this, but let's take that as a start. I'll revisit this. But before I do that, let me show you some examples of what people might do following an undergraduate degree or a master's degree in mathematics. Okay. So this first example is a classmate of mine from long ago. Right? Both of us went through an integrated 5-year program. Then he did a PhD in maths. He did a postdoc. He was working in algebraic geometry. Sometime in his 30s, after in fact a very prestigious postdoc, he decided that was not the life for him. He went for an MA in finance, and now he's what's called a quant analyst on Wall Street, and he's working for an investment company, and he's working on numerical solutions of stochastic partial differential equations. Okay. Okay. The next are some students from my St. Stephen's College days. They did BA in maths there and followed it up with a master's and PhD, and again going in different directions. One became a risk manager. One first became an assistant professor in a maths department, but now is a data analyst for an insurance company. Another one followed up with a master's in financial maths and now works as portfolio manager for an energy company. Okay. All right. These are sort of colleagues of mine, and I thought I would include their paths as well, starting with their undergraduate degrees, followed by master's and PhD, and then postdocs are more standard. The first one, after his postdoc, he actually joined industry and worked on medical technology, specifically medical imaging, before deciding to come back to academia and becoming a faculty member jointly in computer science and mathematics. Okay. And these two are students of mine from my current university. So after their bachelor's in mathematics, both of them went for business analytics kind of master's programs. Well, one of them did, and then has worked as an analyst for an airlines and so on. And the other one actually took up a job as a business analyst for an investment company. But after a few years of traveling the world and doing that, she decided that she needs to know more maths, and is just last year joined a master's in applied maths. Okay. And the last one is a little different. This is, sorry. Okay. So this is a student who actually had done a BTech, I think electrical engineering, and wanted a career in robotics. And when he started applying or looking at what it needs to become, to go for higher studies in robotics at good universities in the US, he found that there's a lot of maths you need to know, which had not been taught to him. So then he actually came and did an MSc in maths at my university. And for instance, I ended up teaching him a course on geometry from the book by Kumresan and Santanam, Expedition in Geometry. So it's sort of classical stuff, projective geometry and so on. And in fact, that became very crucial to him in the internship that he did in robotics after finishing his master's in maths. And then he did a master's in engineering with a specialization in robotics and so on. So what he really needed was some classical geometry, some differential geometry, some numerical techniques, some game theory, some graph theory, all right? And so that is what he got from the master's, and then he was able to return to his engineering career, and he is now actually a robotics engineer for a company. All right, so what else? I think also in the chat, people are asking a little bit about, maybe they're feeling a bit lost about what direction they're supposed to be moving in. What is it that they should focus on right now? And one thing I wanted to highlight from this slide was how there are many opportunities. You can do different things at different points of life. You can revisit your decisions and you can change them, and you can still continue and have really productive and interesting careers. Yeah. Okay, so I think what one is seeing is, okay, so there's the standard track to academia, which is bachelor's, master's, PhD, but you could leave off at any stage and go get a job doing something else, which I've just written as industry as a catch-all for anything outside academia. And you could do this after bachelor's or master's or PhD, and you could do this and you could come back to the academic stream, right? So the people that I was showing you are showing different paths of, through this sort of graph. Okay. So now the bachelor is the starting point here, right? So therefore, the task at the undergraduate level is to lay, on the one hand, a common foundation that could be useful for any of these potential paths, but then also have enough choice built into it to support these diverse possibilities. All right, so what does this require? Now, one problem that happens when you are creating a curriculum is that every one of us has a certain idea of what we consider to be necessary to a maths education, right? And then a curriculum often simply becomes the union of all the things that the different contributing people consider to be necessary. And you get a large number of compulsory courses, right? And so I think the very first thing one has to do is one has to take an opposite approach and in some sense go for the intersection rather than the union and be extremely restrained in what you consider to be core and something that everybody should know, right? And you have to do this so that you can create a variety of elective courses so that people can start exploring different directions, right? And can move back and forth and can start that during their undergraduate education. On the other hand, this should not just be random. If this is going to be really constructive and help them in any particular direction, then these courses sort of have to come in packages. You know, they should form specializations and so on, right? So groups of courses that a student can take as electives and explore different directions. Okay. It's also extremely important. I think Geeta pointed out that one should not look, at the maths education as the student doing a maths degree, and we just look at the maths part. We have to look at the whole package. And so one has to allow significant space for non-major courses, and one has to coordinate with other departments. And that is a very tricky thing, that you have to coordinate with other departments so that your students can go and take courses there and their students can come and take your courses. And apart from just the courses, this mixing of the students is extremely important. So one problem we have had is that if we expose our math students early to the things that we think are necessary for mathematicians, they tend to get isolated from other students. Okay. And that has various implications for them. To handle the maths program, they need to be strong, not just mathematically, but as human beings, as people who can take on stress and who can deal with it and who can solve life problems. So they need to know, they need a variety of social interaction as well, and the curriculum somehow has to provide and has to facilitate that. Okay. Now, students enter an undergraduate maths program, right, with various levels of clarity about their eventual career. Some come in with very clear sort of picture, right? So I might get 2 or 3 students every year who join and say, where is the course in algebraic topology? Why are you telling me about mathematical reasoning? So there are students like that. But and there are also students who come but with different interests. So there are also students nowadays. In fact, a big thing is that everyone is hearing about big data and machine learning. So there are students who will come and who will say that, well, I've joined a maths program because I've heard that maths is essential for machine learning. And so how soon, will you teach me the necessary maths, and can I take the necessary computer science courses? And it's not always fluff. Some of them, in fact, are quite serious about it, are quite good at it. And so it's a new challenge to see how to facilitate this desire that people have nowadays. So what they want to do, there are different levels of clarity. What relevance maths has to what they want to do, they're generally not very clear. For instance, someone says that I want to do research, okay, but right, what do they really know of what it means or what it means to do research in mathematics? But that is what they have, they have seen some options and this is what they have picked out. And they come in with different levels of commitment. For instance, what I see is that students who join engineering are willing to take much more for granted. So they are much more patient in terms of, okay, the engineering school is telling us to do this, so we will do this. Okay, what's interesting about students joining maths is that much earlier they start questioning. They're not very patient with their teachers. They want justification. Why are you putting me through all this? And it's an interesting challenge trying to answer that. Okay. So what happens is that, when we design the curriculum, we tend to, maybe have a few sort of what we consider typical or even ideal students in mind, and we plan a curriculum for them. The students we actually get are much, much more varied than we have planned for. Okay. And so many things matter beyond content. Okay. One problem is that most discussions about curriculum are about content, right? What should I teach them? What sequence should I teach them in? What book should I use, etc., etc. Right? And even what I've been saying so far has been mainly about that. Okay, but there are other things, many intangibles to take care of. Students have different learning styles, right? So the way I teach works for some students does not work for other students. When I was a teaching assistant for the first time, and I would see how so the university that I was in, you had large courses. You might have 10, maybe 20 sections, tutorial sections to a course. You might have 10 TAs. And the students had a couple of weeks to decide which tutorial they wanted to be in. Okay. So over the first couple of years, and this was kind of deflating for me at first, because what I saw was that my tutorial sections were full, but the students who were really into maths and were ambitious and so on, they were not coming to my tutorial. Somehow I was attracting the ones who were sinking and who wanted sort of a hand, who sort of wanted someone that they thought would help them get through. So those students were attracted to my tutorials. I was not so happy about that at first, but eventually I took a more positive sort of look at it and said, yes, that's very important too. Okay. So different things attract different students. And even when teaching the same course, for instance, I had a student for part of my linear algebra course, she was very engaged. And for part of it, she was not coming to class at all. It took a while before she figured out, what was happening to her. And a further time before she told me about what had happened. Right. So wherever there was some sort of pictures to be drawn, diagrams, and I was, talking about pictures, then she was engaged and she was actually very good. And when it became purely formal and I was saying, here are axioms, let's manipulate them, she could not tolerate that at all, I think. And right, so she would just then stop coming to class while that was going on. Okay. Right. Students come in with different levels of confidence and ambition. And so, and that's very important, that somehow one has to get to know these things early. Okay. I teach something and someone doesn't understand, someone will respond with a question, right? And will get their problem sorted out. And someone else will just say, oh, this is not for me, and they will give up. Okay. Maybe if I can somehow sense that this is happening to them and I can intervene, right, and have some time with them, then I can, solve this problem for them and we can move forward. But if I don't find out, then there's a lost student to deal with. Okay. The faculty's ability to advise and counsel, okay, that's a very crucial component apart from the curriculum. And I think this is a serious problem. And my fourth point is a bit similar. I think faculty are in some sense too uniform. Okay, and we need much more diverse faculty. When we are talking, we like to talk to students and say, there are many possibilities and you should be open-minded and you should explore and you should find your passion. And we have all these nice things to say to them. But ultimately, if we test them all in the same way for the same things and we have very similar expectations, then that is contradictory. But the way institutions are at present, the way departments are, the way we hire, we tend to also, the same way that I talked about having an ideal student in mind, we typically have an ideal faculty member in mind. And we tend to hire similar people. Maybe in maths, there is still a bit more diversity. We tend to be a bit weird and that automatically creates a certain diversity. But still, this is an issue. And what I find in my department and my programs is that different students are gravitating to different faculty members, and it's not always due to the content, due to the specific courses they are teaching. It's their way of being, it's their way of talking, it's the things they talk about, it's the things that they value, the things that the way that they nurture students, right? The students from different backgrounds and students with different likings are drawn to different faculty members. And so diversity amongst the faculty is extremely important. Okay. And so when we think about all these things, the transition from school to college, careers, et cetera, the faculty component, what we are like is something that I think doesn't get addressed. Hiring is individual. There are many factors, and we are much more uniform than we ought to be. All right. I think I'm going to stop here. Yes, that was the last slide. Okay. And so we can move to the audience. I think the chat box has been pretty active, so I think we can pick out many things from there.
Yeah, thanks a lot, Amber, for that. Yes, I think we have about 10 minutes left, so I think we can move quickly on to questions from the audience. And as you mentioned, there's been a very rich discussion happening in the chat window, and many of the questions the panelists have already responded to. I'm going to use my dictatorial powers and ask if anyone wants to respond to what I thought was a very nice question from Gautam Varali. So I'm just going to read this out, and anyone who wants to respond, please do that. So how would one reconcile the fact that for many students, the BSc, BA is their terminal degree, with the fact that teaching such things as critical thinking, analytical things, good citizenship, etc., takes time? So universities, after all, have to impart a large set of skills in a very short period of time to students who will not be in the university after completing their BSc, BA. Would anyone like to respond to that?
Maybe I can say something first and then the others. Yeah, I mean, the whole issue comes back to how would you design syllabi at the undergraduate level, say in a mathematics honors program. You do want to have critical thinking and all the other skills that a student needs to develop through their undergraduate days. And you also want them to gain enough knowledge in mathematics for the degree to be called a maths honors degree. And plus it has to handle students coming from varied knowledge bases into the undergraduate program. And they also want to leave the undergraduate program to take up various different careers, including the path which would go into higher levels of study in mathematics. The only way you can do that is to have a structure where there is a lot of choice for the student. The UGC choice-based curriculum is actually a misnomer. There is really, by the time it's implemented by the institutions, there's really no choice. So I mean, I'll just give a typical example of what we do in AUD, and of course, that's not necessarily the best way to proceed, but a maths honors students has to compulsorily do 12 maths courses. And there's no choice really in that aspect of it. But to graduate, they need to do something like 24 courses. 4 of these tend to be of the type which are critical thinking and so on and so forth. They have some element of choice in it and there's some compulsoriness built in it. They call it kind of foundation courses. Then you have these core courses, but that still leaves space. So for 8 courses, where if a student wants to continue with mathematics, then they pick the higher level maths courses, which will lead them in that direction. But say a student is not interested in continuing with mathematics, but wants to say, enter into journalism, wants to do a bit of history or political science, they can do that, or pick up languages, they can do that along with doing a maths honors. They can also do economics, for example. So the freedom, so there's a core that you think which is essential because your degree is also called a maths honors degree. But at the same time, around it, you build elements of choice and keep some kind of a foundational basket which handles these things. I think Amber and Fauzia and all have also probably done that in their universities.
Yes, I'll briefly talk about our program, which is again what I said earlier, is that one of the objectives was employability. So assuming that a student who isn't necessarily going to go for a postgraduate program, so we designed it with that in mind, and also we brought in a lot of flexibility in terms of electives, especially after their sort of in their 4th, 5th, and 6th semesters. They can take elective courses. Our students, just to give you an example, we have had students who've found jobs right after bachelor's, especially in the banking and finance industry. We've had students who've gone on to do PhDs, either in pure mathematics or in even actuarial mathematics. It's based primarily on the electives that they take. Some of them are more sort of theoretical math courses, if you want to do a PhD, or if you want to do mathematics. We've had students who've done business courses afterwards, who have gone to do masters in economics or PhDs, statistics, applied math. So not history, or there isn't that much flexibility in terms of them wanting to then do sort of social science. They can if the program is just requires a bachelor's degree, but they do have specialization within the 3 years of going into business, economics, math, statistics, actuarial sciences, or just stopping at the bachelor's level and being able to find a job. We've had students who work, a lot of our students are working as actuarial analysts. Just after a bachelor's degree, they took the actuarial exams and were able to find good jobs. But the point was, the main thing was you give them flexibility, especially sort of second year onwards, fourth, fifth, and sixth semester. We have done the same for our postgraduate program, which is actuarial statistics, but there are also students who want to do more statistics and less actuarial part of it. So there is flexibility there as well in terms of electives. We have also had one important point that I want to say is that I was talking about students, rural areas who don't necessarily have access to technology or exposure to certain things. We have incorporated courses on technology into our programs, even language, especially English language, so that they can catch up.
Yeah, thanks for that, Fouzia. Dr. Acharya or Amber, would you like to come in for, say, 90 seconds each, either responding to this question or something else?
Okay, do I have a stopwatch? All right. Yeah, so again, when you say, how do we impart different skills to students, when it comes to things like critical thinking and so forth, and, how to be a good citizen, one thing as Gautam sort of said and undercut his own question is, does it really matter anymore? But if we take the first question, then and again, what I would say is, of course, in terms of courses, there are things that you can do, but it's the overall experience. So if you want a math student to have some understanding of what it is to be a good citizen, then there must be something else going on in the life of your university where they can experience that. Not sure that it's fair to put the burden of that on the real analysis instructor and so forth, right? So do they have a role, do they have a say in what happens in your program, right? So can they influence the courses that you teach? Can they dispute that with you? Can they learn how to do that, right? In the sense, that's also a skill, how to negotiate and how to, put forward your desires, how to learn to express and communicate them. Do we give them an opportunity to do that, right? Are they represented in your committees? If they get into a fight with some university authority, what do you do, right? So I think these are the things, and if you really want, so this is what is involved in really saying that we will equip them to be good citizens. If you come to narrower things like, what are the things about understanding what a proof is and so on, then I don't think that calls for a lot of time. I mean, it doesn't matter that a BSc is just 3 years. What it took for me to learn really what a proof is, to whatever extent I've learned it took maybe 2 courses. One was a philosophy course and one was a real analysis course, where the instructor had a way of teaching where he would simply put conjectures on the board and would get the whole class to vote one by one on whether they thought it was true or false. Okay. So all the time you were faced with, Mr. Habib, is this true? Is this false? If it is true, you give a proof. If it's false, give a counter example. And a whole semester of that, and you are sort of sorted out. I don't think I don't think that my understanding of what is a proof has particularly developed beyond what happened in that course. Okay, so that's what I think about this question 1. If it's a narrower viewpoint of the technical things and what you need to do well in maths, then it doesn't necessarily take time, but it does take some intense experience. And the other, if it's the big picture thing about being good citizens and so on, then it has to be the entire life of the student in the university and not just what's happening in the math classroom. Okay.
I would like to answer this question of someone who is a 3rd year PhD student, I think Avinash Sharma. So he asked, is there a way to learn how to teach mathematics? I think there is a lot of thing which happened as far as this is concerned. We don't have any training program how to teach. We might be qualified, but I think there are some ways in which you can do this. As a PhD student, you can teach your juniors if you are in a university. And there is always a course where students are not very comfortable, because this has happened with me when I was doing my PhD. Several students came to me and they said that, oh, we are not following such and such course, could you give some lectures? And then I gave unofficially lectures, and that there they were comfortable with me, and then I learned how to teach also. I think this is something which a serious research scholar has to do, how to teach. And remember that you have to start what students know, and from there you have to lead them to what they are supposed to know. So this is a very, very tricky scenario, and by giving lots of symposiums, a student can learn it, at least at this point of time. We do not have any official mechanism except possibly some refresher courses to do that. Yeah, that's all.
Okay, thanks a lot, Dr. Acharya, and thanks again to all the panelists. Yeah, I'm sorry we couldn't take more questions. I see a lot more very good ones coming in the chat window, including an important one from Jayashri, some from Prathamesh, and so on. But I think we'll have to wrap up now. So yeah, I think maybe one of the most important things I got from this is that, as instructors, as Dr. Acharya said, we don't get any training, we just muddle through life. And I think the existence of a community like this where we can have conversations is probably extremely helpful. So yeah, thanks everyone. And Soumya, should we?
Yeah, so thanks a lot to all the panelists for this wonderful program today. I feel that we should have arranged a 3 to 4 hour program instead of just 1.5 hours. Yeah. So, and thanks to Tulsi for having this, chairing this session. Thanks a lot. And
yeah,
so,
thank you.
Yeah. So we have an announcement which is different from this one. So on Sunday, on 26th July, we have a quiz, mathematics related quiz coming up. And the quiz master would be someone from ISER Mohali. His name is Abhijit. And so we request everyone interested to register in the website. And the link would be available on the virtualmathsfest.in website from tomorrow. Okay, yeah, that's it. Thank you.
Thank you.
Okay.
Boy.
Hi, Subhajay.
Oh, hi. Hi, Krishnendra.
Hi, Ajay. How are you?
I'm fine, Krishnendra. How are
Yeah,
you?
great to see you after a long time.
Yeah.
Yeah, both of you. Subhajay and I have meeting once in a while, but I am seeing you after a long time.
Yeah.
Yeah. Who else is? Yeah.
Hello.
Yeah, so we can start. Hello, everyone. We're in the 5th day of our conference, Virtual Maths Fest 2020. And we'll be starting the symposium on topology, geometry, and dynamics. Today, we have with us Professor Ajay Singh Thakur from IIT Kanpur. He will be the chair for this session. Yeah, over to you, Ajay.
Yeah, thanks, Ramu. So, welcome everybody. So, it's my great pleasure to introduce today's invited speaker, Professor Subhajay Gupta. Subhajay is a faculty at IISc Bangalore. His research lies in technical theory and low-dimensional geometry. And today he's going to speak on surface group representation and geometric structure. So, I request Subhajay to please start.
Okay, thanks, Ajay, and thank you for the introduction. And I thank the organizers for the invitation and for organizing this wonderful virtual conference. So this is the title of my talk, and let me begin by saying what these terms in the title mean and giving a broad overview of what this is all about.
I guess you were muted.
Oh, okay.
Yeah. Okay.
Oh.
Somo, can you add Subhajoy as a co-host?
Yeah, maybe I was muted as because I'm not the co-host. Let me start again then. Yeah, so as I was saying, I was thanking the organizers for organizing this wonderful virtual meeting and for inviting me to participate and giving a talk here. And I'll sort of begin by giving a broad overview of what I'm going to talk about and these terms in the title that I have here. Okay, so a surface group is nothing but the fundamental group of a surface. And for most of the talk, S will be a closed and oriented surface of genus G bigger than or equal to 2. And here's a picture of a genus 2 surface. And the fundamental group of such a surface has this well-known presentation with 2G generators and one relation. And for a genus 2 surface, I've drawn these collection of loops that generate the surface group based at some base point that I've chosen. And such a collection of loops that generate the surface group will be called a marking on the surface. Okay, and later in the talk, this surface S could have punctures, and in this case, this fundamental group is just the free group. Okay. Now, if you fix a Lie group G, and you can just think of G to be one of these matrices, sort of GLNC, SLNC, etc. We can think of these as some of these matrix groups rather. So then a surface group representation is nothing but a homomorphism from the surface group into G. Okay, and the space of such homomorphisms, which here's this. So this homomorphism from the surface group into G, that's as an algebraic variety. After all, if you want to specify a homomorphism, let's say to the Lie group GLNC, you need to specify n, so 2G n by n complex matrices. And as long as they satisfy this one relation, which is a set of polynomial constraints, then you have a homomorphism. Okay, but what we'll be interested in is the space of representations up to conjugation. So you want to identify a representation and any conjugate of it, as I've indicated here. And it turns out that if you define the quotient correctly, and for that you need to do what is called the GIT quotient, then you do get an algebraic variety, a chi-G. So in this case, I mean, if you have a real Lie group, it would be a real algebraic variety. Okay, and this space of representations up to conjugation will appear a few times in the talk. And this is something that I'll be talking about. So so these representations, these surface group representations arise very naturally in differential geometry as the monodromy of a flat connection. And I'll just briefly describe this now. So if you start with a vector bundle E on your surface S and a connection nabla, which is flat. So flat here means that the curvature of the connection is 0. And that's a differential equation. And we'll see an instance of that a bit later on. And so remember that a connection allows you to parallel transport vectors around in these vector spaces corresponding to different points in the surface. And in particular, if you have this loop gamma on S, then if you take this black vector in the vector space associated with the base point and parallel transport it around, and when you come back to the same vector space, you might end up with a different vector. Okay, and so if you go around a loop and parallel transport, it defines sort of linear map of this vector space Cn to itself. And and it turns out, I mean, it's also invertible, by the way, because if you go around the other way, then you get the inverse map. Okay, so if you choose a basis of the vector space, this defines a matrix in GLNC. So corresponding to loops, you have these matrices, and if the connection is flat, then one can show that this matrix only depends on the homotopy class of gamma. Okay, and you get this surface group representation into a GLNC. Okay. And this is called the monodromy or the holonomy of the connection. And this representation is well defined only up to conjugation, because we have to pick a basis of the vector space which these matrices depend on. And we also chose a base point for these loops, and you want to be free of these choices. And so you actually get an element of the representation variety chi that we had on the sort of chi of G. Chi of GLNC that we had in the previous slide. And this monodromy map, via this monodromy map, you have a bijective correspondence between flat connections on a vector bundle of rank n up to what is called gauge equivalence and the representation variety up to conjugation. This is called the Riemann-Hilbert correspondence. Okay, and there's a version of all this where you, instead of GLNC, you have a Lie group G. In that case, you need to take the principal G bundle. Okay, so this is one way that these representation of this group representations arise. They also arise as the monodromy of geometric structures, which is sort of the other term in the title of the talk. And a geometric structure here is also called a GX structure. So X here is a homogeneous space. It's a space with an action of a Lie group G, and the GX structure on surface S is an atlas of charts, is a maximal atlas of charts to X, so that on the overlaps of these charts, these transition maps defined there are restrictions of elements of G. Okay, and so here it's sort of helpful to assume that the map is the action of G is analytic, so which means that, you know, if you know the map on an open set, then you know which element of G it's a restriction of. Okay, and so that's a GX structure, and everyone's favorite example of a geometric structure or GX structure is a hyperbolic structure. Okay, so here X is just the hyperbolic plane, and G is PSL2R. That's the Lie group that acts on the hyperbolic plane by orientation preserving hyperbolic isometries. Okay. Now, given a geometric structure, you can build a monodromy representation rho to the Lie group, from the surface group to the Lie group G, as I've indicated here in this in this figure. So you can cover, so if you take a loop gamma on the surface, you can cover the loop with a chain of charts and take this product of these transition maps on successive overlaps to define rho of gamma. And just like the parallel transport we saw on the previous slide, this measures the mismatch between the first and last chart when you go around a loop. And as before, this monodromy representation is well defined only up to conjugation, because, you know, you have to choose this base point, this first chart, when you do this construction. So we have this monodromy map psi from the space, the deformation space of all GX structures, marked GX structures, so GX structures together with the marking on S, to the representation variety chi G. Okay, and the
Subhajai,
yeah.
you're still in the slides, you're showing it still in the last page. It hasn't moved to the new one.
Oh, so it's slide 5, right?
Oh, it is 4.
Okay. So let me try mirroring again. So I'm sort of using two devices here. Now, can you see this?
No, still, now it is 5.
Ah, okay, great. Okay, so, okay, so, yeah, so let me then, I mean, this, if you didn't see this slide at all, I don't know why.
then so let me go over this quickly, right? So so you saw in the previous slide, you saw how given a vector bundle and a flat connection, you have a monodromy representation from the surface group into GLNC, and there's a version of it for any Lie group G, where you take a principal G bundle. Now, the other way that I was describing that these surface group representations arise is as a monodromy of a geometric structure, okay? And this was what this picture is. So you have a atlas of charts to this homogeneous space X, and the transition maps and overlaps are elements of this Lie group G, okay? And so you have this action of G on the space X, and so hyperbolic structures are examples, and whenever you have a monodromy, a geometric structure, you can look at the monodromy of the geometric structure, just as I've indicated below. It's sort of you look at how these charts differ if you go around a loop. So you cover a loop with these successive, like a chain of charts, and on the overlaps, you have this G1, G2, etc. These elements that they differ by, and once you look at this product is what this first and last chart differ by, okay? And so you have this monodromy representation corresponding to any GX structure. So if you look at the space of all GX structures on or with a marking, so these called marked GX structures on S, so this deformation space admits a monodromy map to the character variety chi G. Sort of the representation variety rather. Sometimes I call it a character variety because for matrices, I mean, since the representation variety is up to conjugation, the sort of the invariant functions that determine this, define this representation variety are actually the trace functions, and so it's a sort of this representation variety I introduced is also called the character variety. Okay, so so that's the broad problem in the field, is to understand this monodromy map, and the sort of the one example of the deformation space is space of deformation space of marked hyperbolic structures, and that's nothing but Teichmüller space. In this case, this map psi maps to the PSL2R representation variety, and that's well understood. Okay, but in general, it's an interesting sort of broad problem. So that was really the overview, and in the rest of the talk, I'll focus on some specific geometric structures called complex projective structures on surfaces, where the Lie group G is PSL2C, and the space X is CP1, the Riemann sphere, where G acts by linear fractional transformations or Mobius transformations. Okay, and I will tell you how this is related to the Schwarzian equation. It's a certain differential equation on the Riemann surface, and I will tell you what is known about the monodromy map in this case, and maybe include a certain recent result. And hopefully there'll be some time to talk about some specific open problems. Okay, so so the Schwarzian equation goes back to the 19th century. It is something that came up in the context of uniformization of surfaces, it's related to uniformization of Riemann surfaces in general. But let's first look at this Riemann surface, which is just the punctured Riemann sphere. Okay, and so in this case,
Vijay, I think I think the slide is still stuck.
Oh, I don't know why this is happening. So is it now progressed?
No. So we are still seeing this geometric structure.
Okay.
Yeah. Yeah.
Now it's okay.
Now it's fine?
Yes.
Yeah.
Yeah.
So is it in slide 7 now?
Yeah, we can see now.
Okay.
Yes. Yeah.
Okay. So maybe there's a lag between my my video and this slide turning on different devices actually.
Okay.
Okay. So right. So so the Schwarzian equation is I'll first sort of introduce it on the Riemann sphere with k points missing, and that's my Riemann surface sigma for now. And so it is this second order linear differential equation. And note that on the Riemann sphere, there's a global z coordinate. So this unknown quantity y that we are solving for is a function of z. And this coefficient q that's given to us is a meromorphic function, and it's allowed to have poles of order at most 2 at these punctures. Okay, and so from the theory of linear differential equations, you know that if you pick a base point x0, if you specify the value of y and its derivative at x0, then there is a unique solution in a neighborhood of the point x0. Okay, and so the germs of solutions at the space point that we've picked can be identified with this vector space C2, the two-dimensional vector spaces. So the value and its derivative identifies it with this vector space. And so if you analytically continue solutions along a loop, and when you come back to this base point, to a neighborhood of the base point, you might end up with a different linear combination of some basis that you started with. So if you start with y0, y1, 2 solutions that span the spaces, you might end up with this particular linear combination where A, B, C, D here are sort of complex numbers. So, and once again, this only depends on homotopy class of gamma. So this defines what is called a monodromy of the Schwarzian equation, which is a representation from the surface group to GL2 of C. Okay, and one can projectivize. So did the slide change?
No. No, so Pooja, no, it's still the same.
Okay. Okay, so I don't know what would prompt it to do this faster.
It is on 7.
Is it on 7? Okay, so it should be on 8.
Would you just exit the full screen mode?
Well, yeah, so let's see. So, right, so now have I exited? Can you see?
Yes, yeah. Yeah, we can see.
And now is it 8 now again?
Yeah. Now it is 8.
Okay, fine.
Yes.
So maybe next time it happens, I'll just exit and enter and see. Okay, so so in this slide, I've instead of looking at this identifying germs of solutions with C2, I've taken the ratio of 2 linearly independent solutions. So instead of an element of the vector space C2, I get an element of its projectivization, which is CP1. And now if you look at this analytic continuation of solutions along a loop, this defines a fractional linear transformation. Okay, so these numbers, complex numbers A, B, C, D that we had before, these are the coefficients of this linear fractional transformation M gamma. So this time you get a monodromy to the projectivized linear group PGL2C or PSL2C. Okay, so for me the two are the same. And the basic question that goes back to the 19th century is, what representations do you get? Okay, so in other words, if you fix the topological surface, the sphere with k punctures, and you can choose where the punctures are, and you can choose your coefficient function q, then the question is, what representations arise? Okay, so did the slide change?
Yes, it's 9 now.
Okay, fine, right. So so this question has been around for a while, and there's some history to it. So let me sort of briefly mention that. Let me first mention that this monodromy of the Schwarzian equation can also be thought of as the monodromy of a flat connection. Okay, and since it's a second order linear ODE, it's equivalent to a first order linear system, as I've indicated here. And then one can define a flat connection on the trivial vector bundle of rank 2 on the surface by defining nabla to be D plus this matrix here. And so the basic question in the previous slide about what monodromy representations arise can be thought of as understanding what monodromy representations appear for these special flat connections, okay, on a rank 2, trivial rank 2 vector bundle. Okay, so now sort of historically, the special case of this Schwarzian equation on a thrice punctured sphere is Gauss's hypergeometric equation, the solutions of which are hypergeometric functions, and that was an object of study for a long time. Historically, as I mentioned, the Schwarzian equation arose in connection with the uniformization theorems. In particular, if you're trying to uniformize a punctured sphere, it amounts to trying to find the right coefficient function Q so that the monodromy of the Schwarzian equation is Fuchsian. So it's a discrete subgroup of PSL2R. And this problem of finding the right Q is also known as the problem of finding the right accessory parameters. Now, this basic question was also addressed by Poincaré in a paper in 1883. And in that paper, he asserted without proof that one can in general get any representation. Okay, and this is a sentence from that paper in case you read French. And the only justification he gave was the dimensions of the spaces on either side of the monodromy map are the same. Okay, so if you consider the dimension of the representation variety of the PSL2C representation variety and the parameter space of this Schwarzian equation on the punctured sphere. So in other words, you have the moduli of the sphere as well as the choices of these coefficients that determine Q and so on. So these dimensions match. Okay, and if you look closely, he also mentions that he's interested in the second order equation without any apparent singularities. And this will come up later in this talk. This just means that, so no apparent singularities just means that you want the monodromy around each puncture to be non-trivial. So if you take a loop around a puncture, that's a non-trivial in homotopy, and you want the monodromy around it to be non-trivial. Okay, and so this was all this was for a punctured sphere, but one can in fact define the Schwarzian equation on any Riemann surface. So in general, you don't have a global z coordinate as on a Riemann sphere, but you can write down this equation if you pass to the universal cover. Okay, and you look at some equivariant solutions, and you can define the monodromy representation from the surface group to PSL2C as before. Okay. And this basic question of which monodromy representations arise, you can ask for a closed surface, and there it was answered by Gallo-Kapovich and Marden using the theory of complex projective structures. And we'll see the theorem in a bit. Okay, so did the slide change?
Yes, yeah.
Okay, great. Okay, yes. So so we already saw geometric structures in general, and so complex projective structure, as I said, is something that is modeled on CP1. So you have an atlas of charts to CP1. So locally, your surface looks like CP1, and the transition maps and overlaps of charts are Mobius transformations, elements of PSL2C, something of the form AZ plus B, CZ plus D. Okay, and so notice that these Mobius maps are conformal maps. So this also defines an underlying Riemann surface structure. Okay, and so as before for this geometric structure, you have a monodromy representation from the surface group to PSL2C. So just to remind you, along a loop, it sort of measures the mismatch of charts. So it's a mismatch of the first and last chart. Okay. And it's defined, well defined up to conjugation. There's also, in this case, something called a developing map, which is what you get when you try to piece together the charts to build a global map from the surface to CP1. You can't quite do it from the surface because, as I said, there's a mismatch of charts along loops, but you can do it if you pass the universal cover where there are no loops. Right. So, so this developing map is an equivariant map. There's this action of the surface group by deck translations on the universal cover. That action is transported to an action by this image of the of the monodromy representation, some subgroup of PSL2C acting on CP1 on the right-hand side. Okay, and there are many examples of complex projective structures, and these examples include all hyperbolic structures, because the hyperbolic plane can be thought of as the upper half plane, which is the upper hemisphere on CP1, and PSL2R is a subgroup of PSL2C. So this is a special example, and in this case, in fact, the developing image is equal to so it identifies the universal cover of S with the upper half plane if it's a closed surface, and you have this monodromy representation, which is a discrete representation of PSL2R, and its image is some subgroup that acts nicely on this upper half plane or upper hemisphere, and then you get a hyperbolic surface in the quotient. But there are other examples, and so one other interesting example, which is also important in its own right, are quasi-Fuchsian structures, where the developing map is not a round disk, but a perturbation of the round disk. Did you see the new picture, by the way?
No.
Yeah, quasi-Fuchsian picture is visible now.
Okay, great. Okay, fine. Right. So this is a round disk is is no longer there for a quasi-Fuchsian structure. You have this domain which is invariant under this image of the monodromy, which is some kind of which is a quasi, what's called a quasi disk. And in this case, again, there's the monodromy representation gives the image is a discrete subgroup that acts nicely on this quasi-disk, and you get a complex projective surface in the quotient. And there's another class of examples that I want to mention, which are Schottky structures, which I hope you're able to see all these circles. So in this case, the developing image is actually the complement of a Cantor set on CP1. And in these examples, the monodromy representation is actually discrete. So they're somewhat special. So discrete subgroups of PSL2C are called Kleinian groups, and they arise in the study of hyperbolic 3 manifolds. But in general, the monodromy could be indiscrete, and the developing map, which was an embedding in these 3 examples, could actually be quite wild. It may not be it might not be embedded in CP1, but it's just an immersion that wraps around CP1 many times, etc. Okay, so now all these structures are actually related to the Schwarzian equation that we had before, because these projective structures on any fixed Riemann surface, sigma, arise from our solutions of the Schwarzian equation. So if you solve the Schwarzian equation, let's say locally, and you get these linearly independent solutions, and ratios of linearly independent solutions define charts to CP1. And so these solutions always define a complex projective structure on the surface. And in fact, the converse is true, and I won't get into this converse construction, but if you're given a complex projective structure, it always arises from some Schwarzian equation. So you can determine some coefficient function Q in the Schwarzian equation so that the corresponding projective structure is the one that you started with. Okay, so, and you get this coefficient function Q by taking the Schwarzian derivative of the developing map. Okay, so there's in this case, there's this link between sort of analysis, so these differential equations we saw, the Schwarzian equation, and these geometric structures. So now, what is known about the monodromy map? So I'll start with the case where the surface S is closed. So I've changed slide, by the way, so let me know if you are not able to see it. So in this slide, you see this. Yeah, so you see this space script PG, and that's the space of all marked project.
Pooja, we haven't changed this. It's a 13.
It's still
13. Yeah.
Okay, so let me try to play. Okay, so is this visible now?
Yes. Yeah.
Okay, fine. So now we know what to do. I'll just have to exit full screen and come back. Okay, so let me tell you what's known about the monodromy map. So the monodromy map for a closed surface, the case of a closed surface, S for a couple of slides. So you have this map psi. It's from the space of marked projective structures where you vary the marking on S and look at all complex projective structures on S. So this is actually, there's a forgetful map down to Teichmuller space, which I'll ignore because you have some underlying Riemann surface, as I mentioned. But what we are interested in today is this map psi to the PSL2C representation variety. Okay, and this map psi assigns to it to any sort of projective structure. It's the monodromy representations. Right? So it kind of forgets about the developing map. And it's a general fact known as the Eresman-Thurston principle that psi is actually an open map. It takes open sets to open sets, and this is true for any GX structure on a closed compact manifold. And for projective structures, however, in this case, this map psi is more true. It's a local homeomorphism. This was a result of Hejal from the 1970s. And he also showed that it's not a covering map. Okay, so it's somewhat more complicated in general. However, it turns out that if you restrict your attention to quasi-Fuchsian representation, so that's an open set in the representation variety on the right. So these are the monodromy representations of quasi-Fuchsian structures. Okay, so then it is, so if you restrict psi to the pre-image of that open set, then it is a covering map there. Okay, and it's actually an infinite to one covering map. And so following Goldman's work in the 1980s, we understand the fibers of this map quite well. Okay, but the question we are interested in today is the basic question that we had earlier is, what is the image of psi? What are the monodromy representations that arise for these projective structures on closed surface? And for a closed surface, if you see the next slide, you'll see Galois-Kapovich-Marden's result, which I mentioned earlier. This sort of closed surface, this was solved, and this is their theorem. And so remember, so this is only for a closed
Can't
surface.
see it.
Okay.
Yeah. Still stuck, sorry.
Yeah, so is this better?
Yes, yeah.
Okay, fine. So this was solved by Galois-Kapovich and Marden, and this is their theorem. So to state this theorem, let me just remind you of a definition. A representation of a surface group to PSL2C is said to be elementary if there is a set F of 1 or 2 points on CP1 that is preserved by the image. The image of rho is a subgroup of PSL2C. It acts on CP1. So if it has either it has a global fixed point or there's a pair of points that's preserved by all elements. So I say preserved and not fixed because elements are allowed to swap this pair, swap the elements of this pair. So then we say that this representation is elementary, and the theorem of Galois-Kapovich-Marden says that the representation is a monodromy of some projective structure in S if and only if it is not elementary and it lifts to a representation into GL2C. Okay, so do you see the next slide? Let me do this. Okay, so yeah, so here's sort of an indication of, so one of the directions, that the only if direction is actually easy. So it's easy to show that these two requirements that are necessary. Okay, so the second requirement we kind of already saw, because we saw that the monodromy of the Schwarzian equation to PSL2C is actually a projectivization of a representation to GL2C. Okay, and so for the first requirement, this is a taste of how one shows that the monodromy cannot be elementary. So one way that it can, is this elementary representation, is if all elements in the image are rotations, they're elliptic elements, which affix a fixed pair of points P and Q. So if that happens, then so notice that a rotation it preserves the round metric on a sphere. Okay, so then if you have charts to CP1, you now think of as the round sphere, and transition maps that are rotations, then you can pull back the round metric, and then this really defines a spherical metric, a metric of constant curvature plus 1 on the surface. Okay, and this contradicts the fact that the surface is genus bigger than 0, right? So so it contradicts Gauss-Bonnet. So that's this particular kind of elementary representation cannot arise, and there is a similar argument for the other kinds of elementary representations that could appear. So so this direction is easy, and for the other direction, the difficult one is the if direction. So if you are given a representation which is non-elementary and which lifts to a representation into GL2C, so how do you construct a projective structure with that prescribed monodrome? And this is what Galokapovich and Marden do, and their strategy was to break up the surface into simpler subsurfaces, pairs of pans, so that this representation restricts to a Schottky representation on each. So a Schottky representation is the monodromy representation of a Schottky structure, one of the examples I mentioned. Okay, and then they glue together these Schottky structures on a pair of pans to build the desired structure on the surface. So this was the theorem, the idea of the proof of Galokapovich and Marden. Okay, so now what happens on a punctured surface? If you see the next slide, let me just do this anyway. So if you see the next slide, so now
Subhajai, can I ask a question? Sorry. So what's the necessity of the lifting criteria to GL2C?
Let me go back. So so the lifting criteria, so we saw that the monodromy of the Schwarzian equation is actually, by definition comes from projectivizing a representation to GL2C. Okay, and then so this monodromy of complex projective structures is sort of equivalent to monodromy of Schwarzian equation, right? And so this is why that condition is necessary. Okay. All right.
Okay.
Yeah, I hope this answers your question. All right. So right. So in this next slide, let me sort of just flash this image of an example of a punctured surface equipped with a complex projective structure. So so there are many interesting examples. This is one class of interesting examples which are interesting in their own right. And these are spherical cone metrics. Okay, so these are sort of these Riemannian metrics of constant curvature plus 1 away from the punctures, and at the punctures there's a cone angle of some multiple of 2 pi. And for us right now, we are kind of avoiding integer multiples of 2 pi because we don't want any apparent singularities. Okay, and so such a thing is actually a complex projective structure on the punctured surface, because if you know, so from Riemannian geometry, so once you have a constant curvature plus 1 metric on the surface, locally you have an isometry to the round sphere. Okay, and these local isometries are the charts to CP1. If you now think of the round sphere as CP1, this defines a set of charts to CP1, and that's your projective structure. And it turns out that the corresponding coefficient function Q in the Schwarzian equation, which arises as from the Schwarzian derivative, actually has poles of order 2 at the punctures. Okay, so that's one class of examples, but there are many more. And for punctured surfaces, this is the result that clarifies Poincaré's remark. So first, let me sort of define this analog of an elementary representation in this sort of punctured case. So rho is a representation to PSL2C is said to be degenerate if there is a set F of 1 or 2 points that is preserved by the image. This is exactly as in an elementary representation. But this time we also have this additional requirement that this set F is fixed by the monodromy around each puncture. So it's not just in the case that there are 2 points, both these points have to be actually fixed and not just preserved. Okay, and in the case that there's it's a singleton, F is a single point, then we require that this monodromy around each puncture is either parabolic or the identity map. Okay, so that's the definition of a degenerate representation. The theorem is that on a punctured surface, this representation is the monodromy of some projective structure without apparent singularities if and only if this representation is non-degenerate and has non-trivial
Can't see the theorem.
Oh.
Yeah.
Okay, so now can you see this?
Yes.
Yeah, okay. So maybe I should just exit this full screen completely. Is this fine? Yeah, okay, so let me try. Okay, so a representation is a monodromy of some meromorphic projective structure, which means there's projective structure where you have this Q, this coefficient in that equation I had before. So that is poles of order at most 2, without apparent singularities, if and only if the representation is not degenerated, as I've defined here. Okay, and it's required to have non-trivial monodromy around each puncture. And the second requirement is just because we are interested in only those without apparent singularities. Okay, and so this clarifies Poincaré's remark. It sort of tells you which representations do appear as the monodromy of a Schwarzian equation, not just on a punctured sphere, but on any punctured surface. Okay, let me mention a few remarks about this theorem. So first of all, there is, in this case, there is also an analog of Hegel's theorem, where it is showing that the monodromy map is a local homeomorphism. And this was proved by Feng Luo in the 1980s. You can also talk of the case where this coefficient function Q has poles of order greater than 2. This is related to the Schwarzian equation with what are called irregular singularities. And this has been studied by people, analysts and people studying differential equations for a while, and in independent interest. And we use some of their work and deal with that case in some joint work with Mahan. Okay. And you can also ask what happens if you allow apparent singularities. And this is something that's in a paper we are writing. So this is work with Gianluca. And he'll be giving a talk on a related matter tomorrow, one of the short talks. Okay, so let me mention a few things about the ingredients, a couple of ingredients of the proof. And once again, it's the construction of the projective structure with the prescribed monodromy that is the difficult direction. And I wanted to mention these ingredients because so these are taken from developments in the subject that are related to other fields, and sort of there's a lot of activity that's going on in these, and sort of exploring these connections. And the first one is sort of a very important and influential work of Fock and Goncharov in the early 2000s. And so what we actually need is a very small part of what they do. Their paper is very long. It's probably more than 200, 250 pages. And then they relate representation varieties to cluster algebras. And that is part of a lot of activity in research and sort of connecting these two fields. But amongst other things, they show that they give these birational coordinates on the representation variety. And I should say it's a representation variety with the framing. And so these are all for punctured surfaces. So framing is so they look at some representations to SLN-C, and the framing is a choice of a flag at every puncture. So in any case, so they have these coordinates which we can use for the case of SL2C or PSL2C. And in this case, these complex numbers associated with an ideal triangulation are nothing but complex cross ratios. Okay? And so that's one ingredient. The other one is some recent work of Allegretti and Bridgeland. And once again, their motivations were different, and they were interested in something called Bridgeland stability conditions in algebraic geometry, and they're relating them in a special case with these Fock-Goncharov coordinates. Okay? But what they showed in particular, that these birational coordinates for SL2C, which are a priori defined only on some Zariski dense subset, are actually well defined precisely the space of non-degenerate representations. And we are able to use this. So it's because the Fock-Concher of coordinates, they define something called a pleated surface or a pleated plane in hyperbolic 3 space. So hyperbolic 3 space in a ball model is sort of the interior of a ball, and so the boundary at infinity is CP1, and so in fact elements of PSL2C which act on CP1, they extend to isometries of hyperbolic 3 space, and Thurston sort of exploited this this geometric fact, and he had a way of going from some pleated plane, as sort of pictured here, to a projective structure at infinity, and called grafting, and we use that to define the projective structure with a given non-degenerate representation. Okay, so that's just a quick idea of the proof. Now I'll just take 5 minutes. So I guess sort of we were interrupted a couple of times. So I'll go over time a bit and mention a couple of open problems. So the first concerns the action of the mapping class group. So all along, so remember that we were looking at marked projective structures and marked surfaces, and this marking is this extra choice of generators of the fundamental group. Okay, so so I guess now you can see the slide. So this marking is something like is drawn here, and if you can change the marking, and so the mapping class group does that. So formally, a mapping class group of the surface is the group of orientation preserving homeomorphisms of the surface up to homotopy or up to isotopy. And what your so in this description, what you're quotienting by here, this homeo of 0 is nothing but homeomorphisms which are isotopic or homotopic to the identity map. Okay, and so homeomorphisms of the surface that are homotopic to each other define the same mapping class. And such a mapping class, it sends a collection of loops as I've pictured here on the surface that generate the fundamental group to another such collection. Okay, and in this picture, you see that I've added a twist to one of the curves. Okay, so this induces an automorphism of the fundamental group, of the surface group. And so now if you compute, let's say you have a projective structure and you compute a monodromy with respect to this new collection, then you'll be going around these new loops, and the new monodromy representation would differ from the previous by a precomposition by this automorphism. So in general, this mapping class group acts on the representation variety, as I've indicated here, by precomposition with the corresponding automorphism of the surface group. Okay, and this not much is known about this action in the case that G is PSL2C. And here's a conjecture of Goldman. The conjecture is that the action is ergodic outside this open set of quasi-Fuchsian representations that I mentioned a couple of times. So I won't define what ergodic means, but you can think of it as saying that the action is chaotic outside QF. Okay, so so it's sort of in particular it would imply that almost every orbit is dense outside QF. Okay, so inside this open set of quasi-Fuchsian representations, this action is actually nice. It's properly discontinuous, and the conjecture is that outside it, it's chaotic. And this conjecture is wide open, and there are versions of it for other sort of Lie groups G as well. For a compact Lie group, it's known that it is ergodic. It's one of the motivations for this conjecture, perhaps. And this goes back to work of Goldman in the 1980s, who did it for G being equal to SU2. And then this statement was proved later using Goldman's ideas by Pickrell and Shea. Okay, so this is one open problem. And let me just quickly wrap up with another open problem, and that concerns higher order differential equation. So remember that the Schwarzian equation was a second order linear differential equation. You can consider linear differentials of higher order on a Riemann surface. So here this y to the power bracket, this just means you take n derivatives of y. And this time you have some more coefficients of these Q2 to Qns. And these now correspond to flat connections on a trivial rank n bundle over the Riemann surface. And these are called SLN opers. So in this language, these Schwarzian equation projective structures, they correspond to SL2 opers. Okay, and you can ask what monodromy representations arise in this case. Okay, so you have this space of SLN opers I've mentioned here by op n, which again you vary the Riemann surface, so it's sort of there's a forgetful map down to Teichmann space. You vary the marking and the Riemann surface, and you have a monodromy representation to the SLN-C representation variety. And it's an open question of what the image of this monodromy map is, and I think very little is known. Okay, so anyway, I went over time, sorry about that, but thanks for listening, and thanks for your patience.
Thank you, Subhajay. So we can take some questions, if anybody has.
I have a small question.
Yes.
Hi, Shubhajay, this is Chaitanya.
Oh, hi.
I have a very small technical question. So when you defined the monodromy,
right?
Is that a homomorphism into G, or is it into like? I somehow feel the multiplication doesn't work out. As in the fundamental group, we multiply loops by like alpha beta is do alpha first and then beta, right?
Okay.
So does that mean that the representation is actually into the opposite group?
No, so it has to be to G. So it's quite possible that I've reversed the order of the multiplication here. I tried to be careful, but it's what you get when you try to piece together the charts to define a map along the loop to CP1. Okay, so you start with the first chart and you look at where the second chart goes, but you want it to be sort of to just extend the first chart a little more, right? So you have to pull back the second chart by this element G1 in this what I've written here. So you have this product of these elements, so that you define your map to CP1 along the loop. Right now, when you come back to the base point, you might be somewhere else now. Okay, and so you differ from the initial chart with a certain element. Okay, and so that difference is precisely the monodromy of that loop.
Right.
Okay, and
perhaps.
Yeah.
Perhaps in the flat connection picture, if the monodromy is defined as the action by parallel transport. So it's like if you take two loops alpha and beta, and then alpha beta in the fundamental group is you go around alpha first and then you go around beta, right? So if you do parallel transport along alpha beta, then you're parallelly transporting along alpha first and then along beta. And since we want our Lie group action to be action on the left, or left associative or whatever, that means you're doing parallel transport along alpha first and then along beta. So rho of alpha beta is really P subscript beta composed with circle P subscript alpha.
That's right. Yeah, I think you should.
That sounds like it's opposite.
No, it's the same thing as what happens for a parallel transport. Okay, so actually, I should mention that the way I've defined geometric structures, it's there's a parallel way of defining this parallel transport here and for flat connections.
Yes, because, I am familiar with.
You have a co-cycle, right? So you have a co-cycle associated with this atlas of charts, okay, and that's the co-cycle that defines the holonomy, and it's actual representation to the group G and not anything else. And so to connect with the flat bundle picture, I should mention that so the point is that a geometric structure is something more than just this flat connection and the bundle that you
Right,
get out of this
section.
co-cycle. There is this developing map, and which is a transverse section of the bundle. So
Right.
so there's a way of going back and forth between these 2 points of view as well.
I have a question.
Yes.
So there are 2 examples that you have given as Fuchsian one, quasi-Fuchsian one, and Schottky one. So
That's
in general,
right.
if you have a projective structure, do you know what type of boundary behavior do you have? Like here, what you have for the hyperbolic structure, it's the upper half plane. For quasi-Fuchsian, you have a Jordan curve, and
Right.
for the Schottky, you have this Cantor set. So what I'm saying in general is the behavior of the complement is.
So in general, it is quite wild actually. So there's no real, this developing image is not necessarily an embedded subset of CP1. This developing map could really wrap around CP1 many times, and this representation could be indiscrete. So it's sort of going all over the place, and it's a mess. So there's so there's no real nice sort of object on CP1 that you can sort of relate to. There is, however, this object inside H3, which is this pleated plane. Okay, and that's what one exploits.
So the convex cone you take, the convex core you take.
There's a way of even if your developing image and CP1 is wild, you can make sense of something like a convex hull. Okay, so you look at sort of maximal round disks. So a projective structure is being Mobius transformation. They preserve round disks. Okay, round disks go to round disks. So that sort of is intrinsically it's well defined. So you look at the maximal round disks in the developing image, and then look at that convex hull, which is this hemisphere inside H3. And then you look at an envelope of those convex hulls of those maximal round disks. And that envelope will define a pleated plane in H3. Okay, and so that's the geometric object that's of interest when one talks of complex projective structures. And so it's not at infinity, but it's rather in the interior, in hyperbolic 3 space.
Okay, thanks.
Surya, I have a question.
Yes.
Yeah. So in Goldman's conjecture, you said it for PSL to C.
Right.
So what about when the target group is PSL to R?
Yeah, that's right. So even that is not known. So it's conjectured. He conjectured that other than the Teichmuller component, the action is ergodic on the other component. So I should mention that for those who don't know that. So the PSL2R representation variety. So actually has different connected components, and Teichmuller space sort of is identified with one of the connected components. So this monodromy map from hyperbolic structures actually lands up in one connected component. And so the other connected components are still mysterious, actually. So they have things like hyperbolic cone metrics and so on, and also indiscrete representations, of course. So the conjecture is that on the other connected components, the action is ergodic, and except for some special cases, this conjecture is open. So there has been some recent work by Marche and Wolf, and who I think prove it for certain connected components. But in general, it is not known.
Yeah, but for PSL to C, is the deformation space connected or is still disconnected?
That's a good question. So it's actually, it has. Yeah, I should have mentioned this. Perhaps this is only in one connected. There are 2 connected components. Okay, so there are representations that lift to GL2C or SL2C, and there are representations which don't. Okay, and this is sort of like some topological sort of invariant, the Stiefel-Whitney class. So there are 2 connected components for the representation variety in the case of PSL2C, and yeah. So this conjecture is about you can think of it as about the connected component containing the identity map, or containing the quasi-Fuchsian representations.
That means the discrete faithful ones.
Well, no. In this case, the connected component has indiscrete representations as well. Okay, so
the quasi-Fuchsian ones are discrete and faithful.
That's right. Yeah, exactly. Right, that's right. So the quasi-Fuchsian ones are discrete and faithful, and that forms an open subset. This time it's not the whole component, but there are other things, and that's right.
And the quasi-Fuchsian ones themselves, are they connected, or they are sort of fractal kind of thing?
Yeah, by the way, so quasi-Fuchsian ones are not the only discrete faithful ones. So anything as a limit, there's a limit of quasi-Fuchsian representations, also a discrete faithful representation. But yeah, so the quasi-Fuchsian space is that open set is a connected open set.
Okay.
Okay, so yeah. So
just one interruption. So there was a question mentioned in YouTube live.
Okay.
So some Mr. Balarka asked, can the GIT quotient, the representation variety, can be thought of as a symplectic reduction with respect to the corresponding moment map?
Yeah, of course. Yeah. So there's a symplectic structure on these representation varieties as well, which sort of comes from what you mentioned. And in fact, so this in the conjecture of Goldman that I mentioned, so when I said it's ergodic, it has to be ergodic with respect to some measure, right? And so the measure comes from the symplectic volume form. Okay, so so yes, answer to the question is yes. Yeah.
Okay, so maybe we can thank Subhajay.
Okay, thanks.
Thank you, Subhajay. Yeah, thanks.
Thank you.
Okay, so the next speaker is Harita Shi. Yes.
Hello.
So speaker is Harita from ICER Bhopal, and she's going to speak on the alternative definition for the Parry's measure. Yeah, so we can start, Harita.
Thank you so much. So good evening, everyone. First of all, let me thank the organizers for giving me this opportunity to talk. And my talk is basically about giving an alternate definition, a combinatorial definition for an interesting measure on a space called subshift of finite type. So this talk comes under the area of symbolic dynamics, which is a tool to model a large class of dynamical systems, such as expansive Markov maps and Anisov maps by a shift space. So to define a shift space, the ingredients required are a symbol set sigma, which can be finite or infinite, and a collection of infinite sequences with symbols from this symbol set. So let's define our setup formally. So we have a finite symbol set here, which is sigma, and then we consider the collection of all one-sided sequences, and F be a collection of words with symbols from sigma. So by a word, I mean a finite string. So a subshift is described by this collection F, which is defined as a collection of all sequences in sigma n where the words from F are forbidden, and it's denoted as sigma F. And there is a map on this space which is called the left shift map, and it is obtained as follows. So sigma of a sequence is given by deleting the first entry and shifting it to the left. So sigma is a finite set, it has the discrete topology, and sigma F is a subset of the product of this space sigma. Hence it has a product topology, which is a compact metric space with respect to this, and the map sigma is continuous. Let's see an example. So we have the symbol set sigma, which is 0, 1, 2, and the forbidden collection. So F will be called the forbidden collection because the words from F are forbidden in the subshift. And the forbidden collection here is 1. Then the subshift sigma F corresponds to all one-sided sequences with symbols from either 0 or 2. And this corresponds to the collection of ternary expansion of points in the standard middle third Cantor set in 0, 1. So one reason why this subshift is useful is that it has a simple representation in terms of a directed graph. So to get this representation, first thing that we need to have is this collection of forbidden words should be consisting of words of length 2. So first we start with collection of words of length p, then we'll see how we can get words of length 2. So when you have p is 2, there is nothing to do and it's called the one-step shift. And when p is greater than 2, then sigma f is conjugate to a one-step shift, where the conjugacy is obtained by defining a new symbol set, sigma prime, which consisting of all words of length p minus 1, and the conjugacy is defined as follows. So conjugacy is basically a one-to-one correspondence between these two sequences. So we have sequence with symbols from sigma here, and that will go to sequence with symbols from sigma prime here, where the first symbol here is obtained by the first p minus 1 entry of this sequence, and then you slide it to the next position, and then you consider the next p minus 1 entry, and that will be the second symbol here, and so on. So now you can see a word of length p here will correspond to a word of length 2 here. Also, a letter, this letter is adjacent to the next letter only if the last p minus 2 entry of the first letter is same as the first p minus 2 entry of the second letter. So that's what is written here. Note that x and y, two symbols in sigma prime, then the word xy of length 2 is allowed only if the last p minus 2 entry of x is same as the first p minus 2 entry of y, which is called overlapping progressively. And then the word of length p obtained by joining these two words is not a forbidden word. So the new collection will have forbidden words of length 2. So once we have this conjugacy with one-step shift, we'll see how this directed graph is obtained. So for p is 2, you associate a directed graph where the vertex set is given by the symbol set, and there is an edge from x to y if and only if the word xy is not forbidden. For p greater than 2, associate a directed graph which corresponds to the one-step shift conjugate to this subshift of finite type. So that means the vertex set will have all words of length p minus 1, and there is an edge from x to y if and only if they overlap progressively and this word of length p is not forbidden. So we have the directed graph now. So we can define the adjacency matrix to be there, to be a 0, 1 matrix indexed by vertices, and the xyth entry of this matrix is 1 if and only if there is an edge from x to y. Let's see an example. So we consider the empty set to be the forbidden collection. Then all possible collections are possible. It's allowed, and it's called the full shift. And the corresponding directed graph is the complete graph with q vertices, and A has size q with all entries equal to 1. Then next example is with the symbol set 0, 1, and the forbidden collection here is this. Here P is 3, hence vertices will be indexed by all possible words of length 2, and the associated directed graph is given as this, and the adjacency matrix is this. So we have a space now, and we have an association to a directed graph. So we'll use this to define a measure on this space, which is sigma invariant, where sigma is the shift map. For that, we need to assume that this subshift is aperiodic. That means the associated adjacency matrix A is aperiodic. That is, there exists an n such that A raised to n is positive. Once you have aperiodicity, then by Perrin-Frobenius theorem, A has a largest positive real eigenvalue theta, which is called the Perrin root, with positive left and right eigenvectors. And the topological entropy of sigma is given by ln of this Perrin root. And entropy basically describes the randomness of the space and of the map. And there are two types of entropies. One is topological entropy and other one is measure theoretic entropy. In 1964, William Parry defined a sigma invariant measure, probability measure, which is now called the Parry measure, on an aperiodic subshift of finite type, which is unique and maximizes the measure theoretic entropy. What do I mean by maximizing the measure theoretic entropy? There is a variational principle on continuous map on a compact metric space, which tells us that the topological entropy is the supremum of the measure theoretic entropies, where the supremum is taken over all sigma invariant probability measures. And he proved that the measure that he defined is the unique measure where the supremum is attained. And the shift map sigma is ergodic and mixing with respect to this measure. Let's define it formally. So we have a finite collection of words of length P, and W be an allowed word of length N. We assume that it has length greater than or equal to the length of the forbidden words. It's a technical assumption. Then the cylinder based W is a subset of sigma F, which consisting of all the sequences that start with the word W. Then you define this Parry measure on this cylinder, which is U suffix the first P minus 1 entry of W times V suffix the last P minus 1 entry of W divided by theta raised to N minus V plus 1, where theta is the Perrin root and U and V are the left and right Perrin eigenvectors with U transpose V to be equal to 1. So, and this, you extend this definition to the sigma algebra generated by all possible cylinders. So we know that when you have forbidden collection with words of length P, then the adjacency matrix is indexed by all possible words of length P minus 1. So are for the left and right eigenvectors. And also it measure on a cylinder depends only on the first P minus 1 and the last P minus 1 entry of this word. And for the full shift, it's a uniform measure on all cylinders and it's given by 1 by Q raised to N, where Q is the size of the symbol set. So our aim is to get an expression, combinatorial expression for this Perrin root as well as the Perrin eigenvalues, so that we can redefine the Parry measure. So we'll obtain an expression in terms of correlation polynomial, which is defined as follows. Let's say you start with two words of length P1 and P2, then the correlation polynomial is a polynomial with coefficients either 0 or 1, which is defined in the following way. You place W under U and shift it to the right by L digit. Then you look at the overlapping parts, and if they match, then BL plus 1 is 1, otherwise it's 0. Let's say, consider an example of U and W here. Then you place W under U and then you look at the overlapping part and you can see that they do not overlap. So B1 will be 0. Then you shift it to the left, shift it to the right and see if they overlap. And here they do not overlap. But when you shift it again, then you can see that this word overlaps with this word and hence B3 will be 1 and so on. So this is, so what we'll have is we'll write Perrin root as well as the Perrin eigenvectors in terms of correlation between the forbidden words. So we have the forbidden collection and MZ is the correlation matrix, which is where ijth entry is the correlation between the words AJ and AI. And these are some terminologies. 1 by RZ is the sum of entries of inverse of M. Ri is the sum of entries of ith row of M, ith row of inverse of M, and Cj is the sum of entries of jth column of inverse of M. We'll see what these quantities are for the example that we already talked about. So we have alphabet size 2 and the forbidden collection given by 000 and 101. Then the correlation matrix is this, where you can see the first entry is the correlation of 0, 0, 0 with itself. And the other quantities are these rational functions. So all these quantities will always be rational. That is one thing. Then let's see how we can get parent root and eigenvectors in terms of the correlation. So we assume that the forbidden collection has words of length p, and M is the correlation matrix. And AI tilde is a subword of AI obtained by removing the first letter of AI. Note that AI has length p, so you remove the first letter, so AI tilde will have length p minus 1. Then the theorem tells us that theta, the parent root theta, is the largest positive real zero of z minus q plus 1 by rz. And the vectors u and v defined as ux equal to this and vx equal to this, where these things comes from the correlation between the forbidden words. For x of length p minus 1, then u and v are the left and right parent eigenvectors of A. So now note that parent eigenvectors are indexed by the words of length p minus 1. Hence, x is a word of length p minus 1. And it has an application to finding the parent root and eigenvectors for any aperiodic 0-1 matrix, because any aperiodic 0-1 matrix will correspond to directed graph that will then correspond to a subshift of finite type. And now we have the parent root as well as the parent eigenvalues, but the only thing that is missing is we wanted the parent eigenvalue to be normalized. So the next theorem gives the normalized form for the parent eigenvalue, and hence the definition, an alternate definition for the Parry measure. So again, we start with an allowed word of length n, which starts with the p minus 1 word x and ends with the p minus 1 word y. This is important because the Parry measure depends only on x and y now. And the measure on this cylinder based at W is equal to this quantity, where you can see this was the left eigenvector that obtained before, and this was the right eigenvector obtained before. So what we proved that we normalized this eigenvector and hence got the Parry measure on the cylinders. And this new definition explicitly brings out the role of forbidden words in the subshift, which was not clear from the original definition. So in the original definition, the only thing that we knew was a word that start and ends with the same p minus 1 words will have the same measure. But now what we know is, let's say you start with cylinder based at 2 words with with same correlation polynomials, then they both will have the same measure. So let's conclude by completing the example that we started with. So we have this forbidden collection. Then parent root is the largest positive real zero of z minus 2 plus 1 by rz, and it's equal to 1.456. And parent eigenvalues are given by these things. And then Parry measure, let's say you take W equal to 0.001, then the Parry measure is given by 0.1942. So these are the references, and thank you.
Thanks, Harita. So we can take a few questions if anybody has.
Hello, Harita, nice talk. I just wanted to know, you said something about the Q, I missed that. You know,
sorry, what?
Q, there was a Q when you defined a matrix. A small q.
So Q is the size of the symbol set.
Oh, okay.
Yeah.
Okay. I see. Because it suddenly changed from P to Q. So I was confused.
Yeah. P is the length of the forbidden collection and Q is the size of the symbol set.
Okay. And is this work preprint or what?
Yeah. This is, it's on archive. So it's not published yet. So it will be available in this. Yeah.
Okay.
Thank you.
I have a question.
Yes.
Yeah, you said that you can have sigma as finite or countably infinite, right?
Yes.
But I doubt that you can do this for countable because
This cannot be done for, no. What I was doing is I was defining this shift space in general beginning. Then we looked at the subshift on finite alphabets, and this is true only for finite alphabets.
yes, because the parent-Frobenius
Yeah.
theorem is
And
not that easy for countable
Parry
matrices.
measure is also defined only for finite alphabets.
So is there any attempt to do this for countable?
I don't
Because
know. We haven't tried anything.
so the parent-Frobenius theorem for countable matrix exists for recurrent matrices. And if from recurrent, I'm talking about the Markov shifts or the random box. In that, so maybe this work can be done extended to not every kind of shifts, but those shifts who have the matrices which are recurrent, maybe.
Okay. Yeah.
Because
I
I'm
can
trying
try
to
that.
do a similar work in Bratley diagrams. That's
Okay.
why I'm.
We haven't tried anything for infinite matrices. So sure, we can try that. Yeah.
Okay, so any other questions? If
One
not,
more.
let's. Yeah,
Just
okay,
one
Riddhi,
more.
yeah. Yeah, Riddhi.
So is there some implication from graph theory? Can you go back and forth with you know?
That's what I said
Once
here.
you said that, yeah. So
Yeah, so when you have a directed graph, then you can always find the forbidden words because you can look at the edges which are not possible. So that will be the forbidden collection. So there is an associated subshift for any directed graph given. So in fact, this can be applied to any aperiodic 0-1 matrices because that has a directed graph associated to it.
thank you.
Thank you.
Yeah, if there is no question, let's thank Harita. Yeah, thank you very
Thank
much.
you.
Okay, so our next speaker is Neeraj Dhanwani. Okay, so he will speak on commutativity of periodic mapping classes. So yeah, I request Neeraj to start. Neeraj, can you?
Hello, are you able? Yeah, are you able to hear me?
Yeah, we can hear now. Yeah.
Sure, thank you. So thanks for this wonderful conference, and when we can not do anything, then we can do a mathematics. That's like okay. So I'm before I go to the explain every word in the title, I am starting my talk with a little motivation. So what is the meaning of the commutativity of the periodic map, and why this problem is interesting? What I'm going to discuss, this is based on this paper, which is recently published in Geometry Educator with my supervisor. So consider this three diagrams. These all are the different embeddings of the genus 8 in the R3. So if you take this embeddings of genus 8 in R3 and you consider these as axes, which are denoted by the arrows, the x and y and x and z axes, then they all are the same kind. What the meaning of the same kind? I have that they all are going to be the fixed 2 points and the permute 4 genus in pair. So they all are the order 2 maps which are going to fix exactly 2 points where they are intersecting with the surface. What about their composition? So what about when they will commute? So it's not difficult to see in this diagram that whenever two involutions in R3 make a 90-degree angle, then they will commute. But in the third diagram, they will not. even though they have a same kind what the previous diagrams have. So they also have a 2 to 6 point. So this motivates us to find a condition when two mapping classes have commutativity in between them. So before again to make precise to definitions, let's recall all the definitions what we have. Throughout this talk, SG will denote a closed surface orientable surface with genus G. Homeo plus SG is a collection of the orientation preserving homeomorphisms. Mapping class group is defined as isotopic classes of the orientation preserving homeomorphism. Because here I'm not talking about the boundary and punches, so I'm not bothered about that definition, but this definition is defined for that too. For me, everything is very good. Then this is a very basic theorem in our direction is Nielsen-Kirchhoff theorem, which says about something about the finite order mapping classes. So Nielsen claimed in 1940s that if you take any finite subgroup of mapping class group, then there always exists a hyperbolic matrix such that under that matrix can be realized as a group of the isometries, which technically in the easy sum says for every finite order mapping class, you can associate a finite order homeomorphism. So the benefit of that is because this is an isometric group, you can talk about the quotients. You can talk about the properly discontinuous action of that. Before going to properly discontinuous action on the surfaces, we define some properly discontinuous actions on the known thing, PSL2R. So consider a discrete subgroup of PSL2R, which is a PSL2R is an isometric group of the upper half plane. So if you have a compact quotient, then it have this form. Whatever the form is written here, the group have to be this form. And when I'm talking about a quotient, compact quotient, that means this gamma is acting on somewhere, and this is acting on this natural choice of the upper half plane. So because I'm dealing with the PSL2R and everything, so I will restrict myself for genus greater than 2. Even when you are genus less than 2, this commutativity problem is pretty much easy because the group is very well known. For the sphere, the mapping class group is trivial, and for torus, the mapping class group is SL2Z, in which we already know there is no commutativity and something like this group is well known. So this problem is much more makes sense when you are talking about a genus greater than 2. So go ahead. This theorem is very classically known in the group actions, that a finite group act on the surface if and only if it satisfies such a sequence, exact sequence, where this phi is a, we say, is surface kernel, and this gamma is a friction group, which we generally know as a orbifold. So orbifold is a topological meaning to this group, which is given by the Thurston. This theorem is made more precise by the Harvey for the cyclic groups. What he proved that this homeomorphism friction group on the finite groups H is surface kernel. That means it's a surjective, and the kernel is phi1 of SG for some G, if and only if it preserves the order of the finite order element. That is, there is some elements which have the finite order and some have infinite order. So on the finite order elements, this map is injective. That is, if zeta 1 have order ni, then phi of zeta 1 is also have order ni. So now for the group, it's important to understand only this phi. So when the group is cyclic, you put H is cyclic. This map is technically can be achieved where the zeta i's are going, because this group is cyclic, is generated by one element. So every element can be written as a power. So you can write zeta I to be some power of the generator. So power is always you can write as a n over ni over n, where n is the order of Zn and ni is you are taking the order of this thing, and some multiple of the Ci. So you can map to your zeta 1 to ni over n times ci. And that is a precisely order ni word. So you get this type of tuple. So this n tells what is a group, order of the group. G0 tells what is a quotient or bifold. R is something which I am going to be explained. Ci, ni is that numbers. So this tuple is going to correspond this map whenever you have a Zn in the right hand side. But what about the converse? If I give you this tuple, can you always build up such a map? Yes, if this tuple is going to satisfy this 5 conditions. The last condition is a Riemann-Hurwitz condition, which is just a generalization of the Euler characteristics in the case of the orbifold. If you remove this part, if you remove all the cone points, then this is a precisely a Euler characteristic for n order cover, n sheeted cover. The condition 4 is about the generator condition. The map is onto. Then 3 condition is about the finite order preserved, and this is about to satisfy this long relation that the product of all the commutator with the product of all the finite order elements is 1. So all the images is also 1. That's this condition. So technically, this tuple is going to be correspond with the one this surface kernel map. And this is shown that this data set, now this I call this a data set, is 1-to-1 correspondence with the conjugacy classes of the finite order elements in the mapping class group. So now to give the conjugacy class of the finite order element in the mapping class group, I will always deal with this data sets, which are the easy to handle in the combinatorial expression. So now we have talked about some algebraic aspects, some going to be some topological aspects. So, okay, so before that, there is some notation. Let F be a mapping class, then its conjugacy class I am going to denote by DF, which is a data set of F. I will denote OH is a quotient orbifold by the group H. Whenever H is a finite group, even you can denote it for the infinite group. For me, always a finite group. So it's a quotient of SG, quotient by H. H is a finite subgroup of mapping class group. And by Nielsen-Kirchhoff theorem, I can correspond to the homeomorphism and the isometry. Okay. So now is some properties of the commutative map. What is the property they have? So first property they have, if they commute, they are going to be induce some action on the surface. And they satisfied such a property that induced action is also have to be order n if they are not power of each other. By this, what we have, that's some necessary condition, and that necessary condition we want to make the two sufficient also. So we put some conditions on the induced map, and we call these tuple to be the essential pair. If you can find a map on the homeomorphism on quotient surface such that it induced a map on the orbifold which satisfied the induced map property, which we have shown before, that it have to be respect something. The same with the G bar, G tilde also. So for the F, when you first quotient with the F, G have to be induced that map. If you quotient by the G, F have to induce that map. And they also together have to give the same orbifold when you're going to be final quotient. This property we go to call is the essential pair, and we define what the meaning of the weakly commutativity. The weakly commutativity is means when they commute in the conjugacy class. What that means is, if you take a two element, you say they are weakly commute if in the conjugacy class of X you can find a one element, and in the conjugacy class of Y you can find a one element such that they commute. With these two definitions, we have our main theorem. Our main theorem says you take F and G in the mapping class group, they will weakly commute if and only if they will form a weakly abelian pair. So what is the meaning of the weakly abelian pair? The weakly abelian pair is nothing, is just an essential pair with one more technical condition, and that's a little bit technical. But even most of the cases, that's not going to play a role. Even I will show in the one example of the involutions, there is no such a role. But that's a technical for the most of the examples which I'm going to be. I will not cover in this talk. Okay, so before go to the some more visualizations, first some applications of this theorem, some easy applications. Primitivity of the mapping classes, finite order mapping classes. So what the meaning of the primitivity is, if you are talking in any group, you can talk about the some h such that h to the power n satisfied the g. So this h we call the root of g, and the root degree of the root is n when this satisfied this condition. So for the finite group, it's always there is a thing, but for infinite group, maybe such a thing is not possible. For example, if you take z, then 1 is only have -1. Oh, yeah, -1 with a multiplication. Such a thing is always. So if you take a g is a non-trivial, have no non-trivial roots, then it is said to be primitive. What the meaning of non-trivial roots? When you can write g as a h to the power n, but their order is precisely same. Like in Z3, 2 and 1, both can be written as the power of each other in Z3, but they are the same order. So I will call the trivial roots. I only discuss the non-trivial roots, and if they have no non-trivial roots, we call it primitive. So again in Z3, 1 and 2, both are the primitive. So in Z4, all the generators are the primitive, and that's a meaning of the taking a Zn star. So in the mapping class group, we have shown that what are the we have given the condition to be the primitivity, which is kind of same to our main theorem, but much more easy sense, because in this condition you are dealing with the same f and f to the power something. So if you have order f is 6, then you are dealing with the f square and f cube, which are the same map. But the corollaries are the very interesting and easy to explain, that if you have a mapping class which is a free action means it don't fix any point on the surface. So this is we call as a regular map, regular cover. So if you take the orbit of the f of any point, it have a same cardinality, which is the order of the f. Then this have a non-trivial root only if the quotient orbifold is not spherical and the root only can be degree 2, and that is only if g minus 1 is not divisible by the 2. The second application is about the free actions. So again, when you have a free action, you can talk about the commutativity, but that commutativity is fine, but what you can achieve by that more, the achievement is more is this: when you have a free action and commutativity, suppose your f is free, then you have a g which commute with the f. So g induce a map on f, quotient of the f, which is again a compact surface. So what is the reverse? What is the reverse means? What is the liftability problem? So if you have a surface below, when can you find a lift such that the lift will commute, or the lift exists? So we are giving this problem, answer is there. So f is a mapping class of the finite order such that orbifold is not spherical. Then you can always find a lift of f in this finite sheeted cover. This liftability, I think, is well known in algebraic topology problem. Again, one more example is commuting involutions. Here the things are easy because involutions means order 2 map, and the problem I am putting like this: if you take a 2 involutions, when you are going to be commute, and if they commute, what about how many different ways? So these are the two problems are there. So our corollary of the main theorem is this: if you have these two involutions, one is this and other is this. This is saying just a permutation of the genus with this many fixed points and so on. Then they will commute if they satisfy this property. And this corollary is the proof of this corollary not only says they will commute, but also says how many times, how many types of different client for group they can make. So this is a calculation when the K3 is this, and for our example, these are the 3 possibilities, and I'm showing the pictures of that, how you can visualize them. So these are the 3 visualizations of the client for group. So our paper is going to be not only talk about the when they commute, is also give the hint that what is the visualization of that commutativity diagram. I think I am on time.
Okay, thank you, Neeraj. We can take some questions if anybody has. Okay, if there is no question, let us thank Neeraj again. Yeah, thank you, Neeraj.
Thank you, sir.
Yeah. So next speaker is Pooja Bansal. Pooja, can you share your screen?
Let me stop.
Okay.
Thank you. Yeah.
Yeah. Pooja Bansal. Hello. Yeah. Yeah, you can share your screen. Yeah, you can. We can see you and audible also. Yeah. So you can share your screen now.
Is it visible?
Yeah, screen has. Your slide has not come yet. Yeah. So.
I have shared my screen. Is it visible to all?
Yeah, we can see your screen, but not the slide. Can you just click on your slide and then?
Okay, so first of all, I would like to thank the organizers to organize such a wonderful virtual conference. So my today's talk, my title is Geometry of 10 Invariants in Statistical Product Manifolds. So in this talk, I will mainly outline a brief survey of statistical product manifold and results for curvature invariance and chain inequality for statistical submanifold of statistical product manifolds. Also, we construct two new examples for statistical product manifolds to support my results. So, first of all, the study of differential geometry with the geometry of
Pooja, sorry. So Pooja, is there a slide? Sorry, Pooja, is there a slide you're going to share or?
Sorry?
We cannot see. There is no slide. We cannot see the slide of your talk.
We don't see your slide. Could you please open it again?
So I think there's some technical difficulty or technical issue. In that case, I'd suggest, can you please stop share your screen and then try to share screen again? I think that will resolve the problem.
Is it visible now?
No.
No.
Not yet.
No.
So maybe while sharing, you are choosing desktop or the window.
Or you can just open with that Adobe.
Window.
Sorry, no. You should choose the whole desktop.
Ah, okay.
Oh, that's so. I think it's resolved now.
You please unshare and then again share. Yeah.
Is it visible now?
Yes. You can make it full screen maybe. Yeah.
Okay, so title of my today's talk is Geometry of 10 Invariants in Statistical Product Manifolds. So in today's talk, I will mainly outline a brief survey of statistical product manifold and results for curvature invariants for statistical submanifold of statistical product manifolds. Also, we construct two new examples to support my results. So first of all, the study of differential geometry started with the geometry of submanifolds. And to study this geometry of submanifolds, it is more convenient to immerse the given manifold into a Riemannian manifold with a known geometry and then study the induced geometry of this Riemannian manifold. So as my talk is based on Warp product manifold, so in 1969, R.L. Bishop introduced the concept of Warp product manifold as a generalization of Riemannian product manifold. And in 1985, Amari introduced the statistical manifold in terms of information geometry, and such manifolds include the notion of dual connection, that is two connections, which is known as conjugate connection also. So statistical manifold is nothing but Riemannian manifold Kellen along with a couple of torsion-free affine connections nabla bar and nabla bar star, which satisfies the Kotazi equations and the equation 1. For x, y, z are any vector fields on Kellen where gamma of T Kellen is the set of all sections of tangent bundle to Kellen. Now we define the Levi-Civita connection nabla bar naught, which is defined by equation 2. And if we take this dual connections nabla bar and nabla bar star as the same connections, then our statistical manifold is known as trivial statistical manifold. Now for any statistical manifold Kellen, the difference 1-2 symmetric tensor K bar of a torsion-less affine connection nabla bar and a Levi-Civita connection nabla bar naught is which holds equation 4. Now next definition is for holomorphic statistical manifold. So let M be 2n-dimensional statistical manifold, a two-form ohm on M defined by ohm of xy given by G of jxy, where J is almost complex structure on M. If here this ohm is nabla parallel, then our manifold M is called holomorphic statistical manifold. And this holomorphic statistical manifold is said to be of constant holomorphic sectional curvature C if it holds equation 5. Now next definition 3 is for Kenmotsu statistical manifold. Now recently Furuhata in one of his papers studied Kenmotsu statistical manifolds and Warp product manifold. So first of all, we recognize the special Warp product manifold Kellen defined by I cross M over the warping function F, endowed with the Riemannian metric given by equation 6, where I here is any interval in the real line and delta T represents the unit vector field tangent to I. Now we have one basic result for curvature tensors R bar and R bar stars for the dualistic structure nabla bar and nabla bar star for statistical Warp product given by lemma 4. Now let R be statistical manifold and M be 2n-dimensional holomorphic statistical manifold of constant holomorphic sectional curvature C. Then for a statistical Warp product Kellen defined by R cross M over the warping function F, the curvature tensors R bar and R bar stars are given by equation 7 and equation 8 respectively. Now we define the statistical submanifolds and some terminologies based on statistical submanifolds. So let N be m-dimensional submanifold of statistical manifold Kellen, then N is said to be statistical submanifold with induced connection nabla and nabla star. The corresponding Gauss formulas are given by equation 9 and 10, in which zeta and zeta stars are bilinear mappings from which the linear transformations A mu and A mu stars are defined by equation 11 and equation 12 respectively. The corresponding Weingarten formulas are given by equation 13 and 14, where the normal dual connections nabla per and nabla star per are the Riemannian dual connections on N per. Now let R and R star be the curvature tensors of the induced connections nabla and nabla star. Then we have fundamental Gauss equations given by equation 15 and 16. Now to know the curvature of a manifold, Gauss proved the curvature of a surface by taking two-dimensional manifold, and he said the curvature of any surface can be expressed in terms of a metric. After that, later on, Riemann generalized this concept of Gaussian curvature, and he gave a new notion which is known as sectional curvature for Riemannian manifolds. So for any orthonormal vectors x and y, the sectional curvature k on Kellen is defined by equation 17. Now its symmetric influence comes from the fact that this sectional curvature k determines the whole or the total curvature of the given manifold. So first of all, let E1 to EM and EM plus 1 to E2 and plus 1 be the standard orthonormal tangent and normal basis on N respectively. Then we define the mean curvature vector fields given by equation 18. Now we say our statistical submanifold to be totally geodesic submanifold in Kellen if our zeta, which is the second fundamental form, so if this zeta vanishes, then our submanifold is known as totally geodesic submanifold. Now the squared norm of mean curvature vector fields and second fundamental forms are given by equation 19 and 20 respectively. The scalar curvature is defined by equation 21. Now we come to our first result, basic result of my paper. So for a statistical submanifold n of a statistical warp product manifold Kellen given by I cross m over the warping function f, the expression for the scalar curvature is defined by equation 22. Also, this inequality given by 22 holds equality if and only if my submanifold n is totally geodesic with respect to the connection nabla naught, where t is the vector field tangent to n and alpha r are the smooth functions over n. Now we come to my main results, which is the chain inequality. So first result is, let n be m-dimensional submanifold of a statistical warp product manifold Kellen defined by I cross m over the warping function f with tangent characteristic vector field xi. Then the chain inequality is given by equation 23 provided it holds equation 24. Now we have a direct application of this result given in theorem 7. If we take my warping function f to be the exponential function e mu, then we have a direct consequence of this result given by corollary 8. And in corollary 8, if we take my curvature c of this holomorphic statistical manifold m to be 0, that is flat manifold, then we have another corollary as an application given by corollary 9. Also in corollary 9, we have proved that my manifold R cross Cn is locally isometric to hyperbolic space H of dimension 2n plus 1 with the curvature -1. Now, before coming to the next result, which is chain inequality for Legendrian statistical submanifold of statistical warp product manifold, first of all, I will define what is Legendrian statistical submanifold. So, according to the behavior of tangent space, under the action of the complex structure J, we have two special type of submanifolds known as complex or invariant submanifold, and second one is totally real or anti-invariant submanifolds. So in even dimensional case, a totally real submanifold of maximal dimension is called as Lagrangian submanifold. On the other hand, in contact case, or we can say in odd dimensional case, let n be m-dimensional submanifold of an almost contact metric manifold Kellen of odd dimension 2n plus 1, and phi be a tangent vector field maps any tangent space of n into normal space, then my submanifold n is called anti-invariant submanifold. And here, if my dimension of Kellen is 2 times of dimension of n plus 1, then the submanifold n is called Legendrian submanifold. So my next result is, let n be a Legendrian statistical submanifold of statistical warp product manifold Kellen defined by I cross m over the warping function f, where I is trivial manifold here and m is holomorphic statistical manifold for normal characteristic vector field psi. Then the chain inequality is given by equation 27 provided it holds equation 28. Now similarly, we have another application of this result. If we take my warping function f to be the exponential function e mu, then we have corollary 11. And in corollary 11, if we take my curvature c of holomorphic statistical manifold to be 0, then we have the another corollary to 12. So here I have given a link for my paper, which is published in International Journal of Geometric Methods in Modern Physics. So due to lack of time, I have omitted the proof of my results. So for that, I have given this link for my paper. Now we construct 2 new examples to support my results. So first example is for Kenmotsu holomorphic statistical manifold. So consider C2, which is the collection of 4 tuple x1, x2, x3, x4, where xi's are real numbers. Then we define an almost complex structure J on M4 given by equation 33. Now we assume my manifold C2 as a trivial statistical manifold and R as statistical manifold. Then we define statistical warp product manifold defined by R cross C2 over the warping function F. Then this statistical manifold has a Kenmotsu holomorphic statistical structure nabla bar whose vector fields E1, E2, E3, E4, E5 are defined by equation 34. Also on this, I have defined contact structure, in which we define structure vector field phi, metric, and one form eta given by equations 35 and 36 respectively. Then we have these equations based on connections defined in terms of nabla bar for the vector fields E1, E2, E3, E4, and E5, which satisfies k bar given by lambda eta of x, eta of y psi. Then we can say my statistical bar product manifold Kellen of 5 dimension as Kenmotsu statistical manifold, where C is 0 and the Lie bracket here k bar vanishes. Now my next example is for Legendrian statistical surface. So I take 2-dimensional Legendrian statistical surface N with defined statistical 1-to symmetric tensor K of xy is equal to k bar of xy for all xy are the tangent vector fields on N. And if E1 and E2 is orthonormal frame of N2, then we have equation, we let zeta of ij defined by zeta of ei ej, where ei ej are the tangent vector fields. Then using Gauss formula, which is I have defined in the previous slides, we find equation 38, and this structure support my previous result or the last one, chain inequality for statistical bar product manifold. So we have here two examples. We construct two examples, one for Kenmotsu holomorphic statistical structure and the second one is for Legendrian statistical surface. Here are some references which I have used to prove my results. Thank you.
Yeah, thank you, Pooja. So if there is some question, we can take now. Okay, if there is no question, let's thank Pooja once again. Yeah, thank you, Pooja. Yeah, thank you very much. Thank you. Yeah. Okay, so the next speaker is Anu Devgan, and she's going to speak on development of semi-Riemannian geometry. Yeah, is Anu Devgan there or?
Yeah, I guess she is not yet.
She's not around. Okay.
Yeah, I don't see her in the meeting.
Okay. So maybe we can stop.
Yeah, Orpunda, what should you do? Can we?
What's the problem?
The next speaker is not yet here.
Does someone have her phone number or something? Maybe she's having connectivity issues.
Yeah, that's the correct suggestion, I guess.
We still have 5 minutes for maybe 9:05.
Yeah, maybe she will join in the last minute. So.
We can wait for 5 minutes.
Yeah,
Soma, can you just send her a mail or something?
Yeah, I can send.
Just send a reminder mail that we are waiting.
Yeah, yesterday she sent the slides to me, but then
Shomo, are you calling her?
do we have her number?
Yes, we have a number. I've just
Then call her, please.
Okay, yeah, sure. Hello.
Yeah.
Yeah, I've just talked to her. She's saying that she has a very poor internet connection. That is why she is unable to give her talk, although she has sent her slides previously. But she has a very poor internet connection and she's unable to give her talk.
Okay. Yeah, so in that case, yeah. So there is no option.
will we call it a
we
day?
just conclude the session, I guess.
Yeah, okay. Okay, so thanks to all the speakers today, and also Professor Ajay Singh Thakur for chairing this session. Yeah, we conclude here today.
Thank you.
Thanks a lot.
Thanks.